Alright, you guys, so now for this second one, okay, we have that the function f is defined by f of x equals this whole thing, which looks a little bit nasty, I'll be honest. For x, x this, and x that. So let's explain this just for a second to understand what this is telling me. So when it says this symbol here, okay, it means that your values of x are within all real numbers, okay? And if it's within all real numbers, it's basically like there's nothing weird going on. See, it includes all real numbers. There's nothing like special happening here. It's just telling you that x pertains to all real numbers. See? So from negative infinity to positive infinity, you include all numbers in between. This might be important in another exercise if they tell you that x pertains only to, for example, z, which is like a very fancy z. This would be integers, okay? And integers are -3, -2, -1, 0, 1, 2, 3, okay? So it would be whole numbers, right? And so a detail like that can be very relevant, but if they tell you it belongs to all real numbers, it's nothing you need to like be careful for, okay? But that is what this symbol says. See, it's like x pertains to like this set of numbers or whatever, okay? So that is more of an intuitive way to put it, and I'd rather explain things intuitively. The x cannot equal 2 has to do with what your fraction has, okay? And so sometimes, because of how your function is set up, there are certain values that x cannot take. There's one or two classic examples, okay? On the one hand, 0 divided by 3, you guys, is how much? Is 0. 3 divided by 0 is how much? It's undefined. You cannot divide by 0. It is illegal. Don't do illegal things. Usually, I suggest that you should not do illegal things, okay? So if you divide by 0, it's illegal, it's undefined. So why can x not equal 2? It cannot equal 2 because in the denominator, basically this whole thing cannot equal 0, right? And so 2x minus 4 cannot equal 0. And if you get x alone from here, 2x cannot equal 4, divided by 2 to both sides, x cannot equal 2. Ah, so that is where it comes from, see? That is where it comes from. X literally cannot equal, sorry, the denominator cannot equal 0, so that means x cannot equal 2. So that is one example that can sort of show up that restricts the values of x that you can take. That is one classic example. The other classic example is, for example, like a square root. See? So imagine you have x minus 3 here. The point is you cannot have a negative inside of a square root. Okay? It's unsolvable without using imaginary numbers. Okay? Which is a whole other thing that I'm not going to get into, but usually the idea is whatever's inside has to be greater than 0. And so in this case, x minus 3 has to be greater than 0, x has to be greater than 3. Okay? So that is just a made up scenario, but point is sometimes your domain gets restricted. Your domain is values that x can take, okay? So this thing here is just helping you define your domain. It's all real values except for 2, all right? And this made up example of the square roots is something that I know can show up for you, so I'd rather tell you. Inside the square root, things have to stay positive. So greater than or equal to 0, now that I think about it. Greater than or equal to 0. Enough blah blah. For part A, we need to find the 0 of f of x. And so for finding the 0 of f of x, basically, when they ask for zeros, they are asking for the x-intercepts. And whenever you need to find x-intercepts, notice, here you have a y, here you have an x. All of these that I'm putting in red are x-intercepts, see? Now, what do they all have in common, you guys? Some of you are probably thinking, well, they're all x-intercepts, right? But what do all of these points What do all of these x, y's have in common? Ah, all of these, without a doubt, because they are x-intercepts, have a y equals 0. So whenever you're finding an x-intercept, okay, you just need to plug in x, 0. And on that note, if you ever need to find a y-intercept, it's the same thing but the other way around. If you ever need to find that y-intercept, notice how all of these points, what do they have in common? They have in common that their x equals 0. And so for the y-intercept, you will be plugging in 0, y. So your y-intercept is basically 0, something, while your x-intercept is something, 0. All right? So that is a little bit of an intuition of why we approach this the way we do. Whenever they ask for zeros, it is specifically about x-intercepts. And so that is something we need to associate in our brains right away. Zeros is for x-intercepts, okay? And so we plug in x, 0. So here we have, well, our original, right, is f of x equals 7x plus 7 divided by 2x minus 4. So if you plug in x, 0, that means your y is 0. Now, where is y? This whole thing is y. So this whole thing is now 0, so you end up with 0 equals 7x plus 7 divided by 2x minus 4. And the cool thing you can do here is that because it's a fraction, you can multiply by 2x minus 4 to both sides. And this is very useful because, this goes away with this, and anything times 0 is still 0. So you end up with 0 equals 7x plus 7. I want to get x alone, so I do minus 7 to both sides. So basically end up with 7x equals negative 7. Divide by 7, divide by 7. X has to be, for part A, x has to be equal to negative 1. So for part A, I'm just going to put it up here just to be more conservative with space. So for part A, x equals negative 1. Okay, so that is the 0 of f of x. If you get fancy, you can say that it's negative 1, 0. Okay, same idea. Nothing is changing there. So that is for part A. Remember that zeros makes reference to x-intercepts. A very specific thing you have to remember. For part B, part I, or for part B initially, they tell us that for the graph of y equals f of x, which is basically just this, right? So for your function, write down the equation of, first of all, the vertical asymptote. Now, there's a lot of buzzwords here. So on the one hand, you have vertical, on the other hand, you have horizontal, and then you have this special one, asymptote, asymptote. Now, what the heck is an asymptote? An asymptote is basically an equation or a line. Let's think about it as a line. So it's a line that your function will never touch. Okay, that is actually such a good definition. So an asymptote is a line that your equation will never touch. Is a line that your function, better said, will never touch. And so there are different types of asymptotes, but for us, they will always be vertical or horizontal. So if I go ahead and graph this here, okay, for example, onto Desmos, and I know that for this part you don't have calculators, so some of you might be thinking, oh, dude, why are you doing this? We don't have calculators, like, this is cheating. Okay, I'm only doing this so you guys understand what an asymptote even is, okay? And so if you graph your function, right, it looks like that. Okay, so you're gonna have two asymptotes, and I'm gonna show you how to find each. On the one hand, you have a vertical one on x equals 2. So notice how my red line never touches the blue one, not even close. Okay, even over here, yes, it gets very close, but it never actually touches it. Okay, so here's my vertical one, and my horizontal one is a y value. And I'm gonna show you in a second how to actually get that. Okay. And so your vertical one, your vertical one is an x value of 2, the one in blue, and your horizontal one is a y value of 7 over 2. See? Now, I know some of you might be a little bit confused by this. See? For example, why is my vertical asymptote, the one in blue, an x value? Like we have associated x values to horizontal stuff. So why is my vertical asymptote an x value of equals 2? It's an x value of equals 2 because all along the line, what does x equal? Ah, x equals 2 all along my line. And so for the vertical asymptote, you put in a fixed x value, which means that all along the line it's just 2. And for the horizontal one, it's the same idea. It's a fixed y value. It's always 7 over 2. Well, here it puts it as 3.5. See? So that is why I know it's a little bit counterintuitive, but okay, so for the horizontal asymptote, it's a fixed, for the horizontal one, it's a fixed y value. So you need to put y equals something. For the vertical one, it's a fixed x value, right? And so that is the idea of an asymptote. See? Now, how do you actually find them? Well, for the vertical one, it's a little bit easier because now we have associated in our brains that vertical, okay, is a fixed x value. And so once you find out the values of x that you cannot take, that is the equation of a vertical asymptote. And so here they actually tell you that x cannot equal 2, and the proof is the one I showed earlier, right? So you took the denominator, you said this can't equal 0, right? And so quickly you find out that x cannot equal 2, see? And so because x cannot equal 2, the equation of your vertical asymptote is x equals 2. So the moment you put x equals 2, the blue line shows up, okay? And so careful, it's very important that the equation of your vertical asymptote is x equals 2. You cannot put x does not equal 2 because this is not an equation. You need to leave it as an equation. So x equals 2 allows you to draw the blue line, okay? So that is for part B, part I. For part B, double I, you need to find the horizontal asymptote. And so for the horizontal asymptote, you would be saying it's a horizontal fixed y value. Now, for this one, it's a little bit harder to like figure it out. See? For the vertical asymptote, it's usually friendly because it has to do with, I don't know, you can't divide by 0 or something about like whatever, like it's a square root, so it has to be greater than or equal to 0. It's usually like a nicer approach. See? For the horizontal asymptote, we have to find the equation of this green line. And so the best way I can show you, and I know it's a cheap answer, but it's what works. Okay, the best way I can show you is that you just plug in a very big y value. Okay, because if you plug in a very big y value, like all the way out here, see, I don't know, let's do it like 100. See, so you plug in like 100, okay, you're gonna end up very close to your line, extremely close. See, and so all you need to do is that it's gonna be pretty apparent what number you're close to, what number you almost reach, and that is gonna be your horizontal asymptote. See? And so for this, I know it's a little bit cheap, but basically for horizontal asymptote, plug in really big values. Okay? And so if you plug in really big values, for example, so my f of x, as we said, is 7x plus 7 divided by 2x minus 4. So if I go ahead and plug in something like, I don't know, 100, right? You end up with 7 times 100 plus 7 divided by 2 times 100 minus 4. So that means that I pretty much, okay, end up with 700 plus 7 divided by 200 minus 4. See? So this is pretty much just going to be 707 divided by 200, sorry, 196. See? Now you might be thinking, dude, dividing this is insane. It's very hard. What do I do? Right? I just came up with a smarter way to do this. See? So technically, if you have your calculator, this is a nice approach, and you're pretty much going to end up with 3.5. But doing it by hand is much harder, see? And so let me go back a couple steps, and let's keep the idea of plugging in a really big value, see? So a smarter way to do this, and again, I'm leaving it in the video because oftentimes when we do our exercises, we figure out a smarter way to do it. It's part of the process. So I'm going to leave it. okay? Because I know you go through the same stuff. So if you go ahead and let's imagine for a second that you're like plugging in, I don't know, like infinity, okay? And I know this is kind of whack, but trust me, just trust me for a second, see? So if you go ahead and plug in infinity, think about it for a second. So we have 7 times infinity divided by plus 7 divided by 2 times infinity minus 4. And so when you have infinity going around, which is just a massive number, right? It's just a crazy massive number. And this is not actually how infinity works, but for us intuitively, for the vertical asymptote, I mean for the horizontal asymptote, it's going to help. See? So just think about it as 7 times a massive number plus 7 divided by 2 times a massive number minus 4. How much effect do you think these numbers are going to have? Nothing. They're going to have no effect because they're next to a massive number. So really, you can just think about it this as this, right? Once you plug in infinity, the 7 and the negative 4 don't really matter. And so technically, what you're really looking at is at 7 over 2. And so the equation for the horizontal asymptote is just going to be 7 over 2. Okay? Technically, it also works doing the thing I did by times 100, right? Or you can do it like times a million and then divide and actually figure it out, and you will end up with 3.5, okay? Or you're going to end up with 3.4999999. But for me, maybe more intuitively, it makes sense to do this approach. See, I know it's kind of whack to plug in infinity, but I just used it as an idea to like you're plugging in a very big number, and so once you plug in a very big number, this and this is irrelevant, and that's the whole point because you're going way out in your function, way out to the right, and the 7 over 4 just doesn't matter at that point. So it doesn't matter at that point, and that gives you a green line very close to the red one, and that is the equation you want. See? So again, that was a little bit of a cheap way to do it, but for horizontal asymptote, it tends to be like that. It tends to be plugging in a very big number, and usually with a little bit of imagination, you can get there much quicker. See? So there it is for part B. Last but not least, for part C, we need to find that, which they tell us is the inverse function of f of x. Now, for finding the inverse, thankfully, it is a very sort of straightforward approach, okay? And so, before anything, the inverse is like the mirror of your function, okay? And so, for the inverse, the steps are going to be always the same, see? And this is just the steps I suggest. I know there are others, but these are the steps that I suggest. So, the steps that I suggest is that first, you write down the OG. So, put the OG. The OG function, the original function, okay? So put the OG. Then put f of x as y. And so now I haven't done anything yet besides just putting f of x as y. And now the third step is going to be flip x and y. And this is the key step. The moment you flip x and y, you're now finding the inverse. See? So if you flip x and y, that means you end up with x on the left equals 7 times y. Ooh la la, plus 7 divided by 2 times y minus 4. And now that you flipped x and y, get y alone. Okay, so if you get y alone from here, well, again, because it's a fraction, I highly suggest that you multiply both sides like this. And so this first step of multiplying is usually going to be like that. So on the left side, you end up with 2yx minus 4x equals 7y plus 7. Now, because our mission is to get y alone, put all the y's on one side. So I'm going to do minus 7y minus 7y. That means I end up with 2yx minus 7y minus 4x equals 7. And so now you want to get y alone, so you do plus 4x plus 4x. So 2yx minus 7y equals 4x plus 7. And so from here, now that you have all the y's on one side, see? So notice how here you had a fraction, so you needed to multiply, right? Over here, you had the y's on both sides. And now, once you have all the y's only on one side, you can factor. And so if you factor on the left side by y, that means inside, like if you take y out from each, you end up with 2x minus 7. Ah, interesting. And so now to get y alone, right, you can just divide. So here, because it's multiplying, you can divide by 2x minus 7 to both sides. So that means that this goes away with this. You end up with y equals 4x plus 7 divided by 2x minus 7, right? And so now that you got y alone, your last step, just to be very organized, is put the inverse, or put y, sorry, put this new y as the inverse, see? And so this is just to be very rigorous in your approach. So you're just going to change the symbol here. So your inverse function is going to be this, see? And that is for part C, right? Now, the last step you have to do is that, okay, you need to put the detail, okay? You need to put the detail that the denominator cannot equal 0, right? So what value can x not take? Well, the value that x cannot take is that your new denominator cannot equal 0. So this cannot equal 0. So plus 7 to both sides. 2x cannot equal 7. So that means that x cannot equal 7 over 2. And so your final answer is putting the detail that x cannot equal 7 over 2. And that is for finding the inverse. See? So again, a little bit of an annoying process, but it's always the same. The big step you have to do is step number 3. Okay? Anyways, you guys, that is for number 2, and I hope it helped. Alright, and now for number 3, we have that on a Monday, happy Monday, at an amusement park, a sample of 40 visitors was randomly selected as they were leaving the park. And all these homies, they were asked how many times a day they had been on a ride called, whoa, the Dragon. The information is summarized in the following frequency table. So let's first understand this frequency table and what it means. So, for example, one of the persons they interviewed for the number of times they were in the Dragon, he answered 0, right? Now, how many people answered 0? 6 people answered 0. Of the 40 visitors that were surveyed, of those 40, the ones that rode only once were 16. The ones that rode exactly twice were 13. The ones that rode exactly 3 times were 2. And the ones that rode exactly 4 times were 3. Okay, that is a better explanation than to what I was about to do. So that's the frequency table. Okay? It can be assumed that this sample is representative of all visitors to the park for the following day. Alright, so for the following day, we can basically estimate using the same table. So we can trust the table as a good representation. So for part AI, we need to find the probability that a randomly selected visitor will ride the dragon. See? So guys, for probability, the name of the game is always the same. So for probability, it's your total cases in the bottom. So total cases. And up top, it's possible cases for what you're trying to find the probability of. And so the probability of ride is going to have all the possible cases. So all that ride divided by the total cases, which is all that went to the park. See? So intuitively, I can state it like this. Basically, you just need to sum all the possible cases divided by the total cases. So all the possible cases, right, of those that rode is going to be these, and these. And your total is going to be these. Okay? So notice, for the total, it's that in red. And for the possible cases, is just the ones in orange, in red, in blah, fuck, in green. Okay, so technically I can do 16 plus 13 plus 2 plus 3 divided by 6, which includes this guy, plus 16 plus 13 plus 2 plus 3. So you can spend some time doing math, but eventually you're just going to find that you have 34 divided by 40. And so that is one way to do it. The other way to do it, which is a more like quick maths sort of approach, if you want to cook this for a little bit, you can see that they tell you that it's 40 visitors. So your total has to be 40. All that went to the park were 40. And they're only asking for those that will ride the dragon. So which ones don't ride the dragon? 6 of them don't ride the dragon. So you can do 40 minus 6. It gives you this 34. See? So that is a slightly quicker way to just find 34 over 40. See? I don't know if it's that much faster, but I do want you to see it as an option. Okay? Anyways, for part AI, the answer is 34 over 40. That is a probability that they will ride the dragon. So let me make a little bit of space over here. And let me just write that real quick. The answer for part AI is 34 over 40. For part A double I, we need to find the expected number of times a visitor will ride the dragon. And so here we enter what we call expected values, expected number, expected. And so the big word, the big buzzword here is expected. Now, once you find the expected thing, okay, once you realize that they're asking for expected, it's suddenly very easy to do this. See? So all you need to do for expected is just a very visual approach. See? So you're going to be doing, for example, this times the probability of that. This times the probability of that. This times the probability of that, so on and so forth. Now, how do I know that you need to do this? I know this because it's actually in your formula booklet. So in your formula booklet, if you eventually find expected value, here it says, expected value of a discrete random variable x. Discrete, you guys, is just like a whole number, okay? And so here you have a bunch of whole numbers, 1, 2, 3, 4, right? So that's why you know you can use this. Now, what is this saying? It's basically the sum of your, it's going to be the sum of your x's times the probability of each x. So it's going to be each x, it's going to be the sum of all of these, right? The sum of your x times the probability of getting that x. So now it's a little bit more friendly because, okay, so basically it's just, for example, for this first one, it's 0, because that is my x, right? Times the probability of getting that x. Now the probability of getting that x is, so it's going to be 0. The probability of writing 0 times is 6 over 40, because the frequency is 6, right? And for the next one, because we're adding, right? It's a summation. See, we're adding. So this is for the first one, right? Then for the next one, we have that it's, okay, writing once, what's the probability of that? So writing once, the probability of that is 16 over 40. 16, because this is frequency 16. All right, interesting. So you can keep going from here. Plus 2 times, so what's the probability of writing exactly twice? 13 over 40. And you keep going and you end up with something that looks like this. So for 3, it's going to be 2 over 40. And for 4, it's going to be 3 over 40. Okay, because of this 3. And so that is for the expected values. If you do all the math, you're going to get the right answer. Now, I know some of you might be thinking, you're trolling. Why did you put this 0 over here? And I put it just to follow the procedures, just to show how you're supposed to do it. See? And so for this first one, yes, it ends up being 0. It doesn't really matter. But I would rather just show you the whole process. Okay? So on the one hand, that happens with that. This next value ends up being with 1 times this is just 16 over 40. Then the next one is 2 times 13, so it's going to be 26 over 40. Plus 3 times 2 is 6 over 40. Plus 4 times 3 is 12. Whoops. 12 over 40, right? So you go ahead and add all of these. It's pretty friendly because they're all in denominator with 40, so you can add them as a fraction. So you end up with 16 plus 26 plus 6 plus 12, all under the same 40, right? And this, with a little bit of quick maths, ends up being Ba ba ba. Damn, I cannot math right now. So that is 18. Then that is yeah. It ends up being 60 over 40. Okay? And so 60 over 40, if you were to, simplify this a little bit, on the one hand, they both have a 0 on top, so you can do boom, boom. You end up with 6 over 4. They're both even, so you can leave it as 3 over 2. So I'm going to leave it as 3 over 2. Okay? So for part A, double I, the expected number of times a visitor will ride the dragon is 3 over 2. If you want to get fancy, this is the same as 1.5. Okay? I'll leave it as a fraction because whatever. See, we're working with fractions. Then they tell us that it is known that 1,000 visitors will attend the amusement park on a Tuesday, and the dragon can carry a maximum of 10 people each time it runs. And so we need to estimate the minimum number of times the dragon must run to satisfy the demand. So let's take a moment to think about this. See? Usually for the IB, not always, but usually, and it's a big hint, what you do in part B needs something from part A. It's not always the case, but a lot of times it is. Okay? And so here, part A double I is something directly needed for part B. Okay? So, the expected number someone, a visitor, will ride the dragon, we said was 3 over 2. Okay, we said it was 1.5. And so, technically, if 1,000 people show up, then how many times will they ride the dragon? Well, one person, so one visitor, rides 1.5 times. So 1,000 visitors, you need to multiply this by 1.5 to find the amount of times that the dragon is ridden. And so 1,000 times 1.5, right? Well, quick maths, you end up with 1,500, okay? There's a chance that you kept it as fractions and you didn't realize the decimal, so you can leave it as times 3 over 2. This is just going to be 1,000 over 1, right? Times 3 over 2. Because for fractions that multiply, you multiply straight across. So I put a 1 over here just to make it more visually appealing. You end up with 3,000 divided by 2. This gives you the same 1,500. So this 1,500, you guys, let's leave very clear, is number of times the dragon is, I actually don't know the right word here, is ridden, is rode, is used, okay? So that is the number of times the dragon is used. And because the dragon can carry a maximum of 10 people, the minimum number of times it has to run to satisfy the demand is 1,500 divided by 10. So if you divide by 10, because they both have a 0, you can do couple out, 150 times. So that is for part B, and that is for number 3. All right, you guys, just a quick disclaimer here for paper 1 on May 2023 for higher level, okay? If we also look at the same paper 1 2023, but for standard level, you will actually notice that a lot of the exercises are exactly the same. For example, problem 2 for SL, sorry, problem 3 for SL, which talks about the dragon and number of times on the dragon, etc., is actually problem number 2 on HL, okay? And the same happens, okay, down here, number 4 for SL is awfully similar to number 3 on AAHL. Okay, so keep that in mind. This is a recycled video from the SL portion of it, but do not worry. What they ask for right there is also right here. Okay, so just be wary of that. If you want to skip to part B just to get like the HL portion right away, go ahead. I do think it's relevant to understand what happens in part A because it does add on to the context. So that's just a quick disclaimer. Because you are seeing the SL version, do not worry. It's still the same question that they're still asking for the same stuff. Nothing really changes. I'm just letting you know this is a recycled video. There's a part A and part B because it comes from the SL world. The exercise is technically the same, okay? So that's all. It's just a quick disclaimer so no one freaks out. Let's go ahead and enter the video. All right, you guys, and now for number four. Number four is hard. And so number four for part A asks us to show that the equation cosine 2x equals sine x can be written in the form of this, okay? And so from here, part A is relatively easy, and part B just goes crazy, which makes sense because part B is worth 5 points. So if you take the time to learn this, you can get a whole lot of flippin' points, okay? Anyways, so we're going to be writing a lot for this, and I'm probably going to need more space than this, so I'm going to be using my whiteboard over here, see? So here in this whiteboard, basically for part A, the main thing we need to notice is that we need to pass from cosine 2x equals sine x to this whole thing here, of course. But what is important about this, the thing that I'm putting right now in yellow only has sine. There is only sines going around, while originally we have a cosine. So if you get rid of cosine, you're good to go. Now, what are your tools for getting rid of cosine? Your tools for getting rid of cosine in your formula booklet, eventually, once you get familiar enough with it, and this is something I invite you to do. I invite you to study with your formula booklet. Get used to it, because the day of the test, you are walking in with the formula booklet. It is an additional tool that you can use. So get friendly with it because it's going to save your life. Anyways, eventually you find this. So these are the main tools you have for facing these type of exercises. Okay, anything that looks anything remotely like what they're asking here, you're gonna be using these tools. And so these tools I copied and pasted over here. Okay, yeah. So for part A, now that we understand our tools and our approach and everything, we have cosine 2x equals sine x. And my only objective for now, because a lot of times we're like, oh, we need to reach this, and you focus so much on this, and you get like confused or whatever. The main idea is just get rid of cosine. Once you get rid of cosine, everything will flow. And so let's get rid of cosine slowly but surely. So which of these properties, specifically this three, because we don't have tangent up here, so we're going to forget about that. Of those three properties, which ones could help me? All right, so we can start off with the one that is down here. See? So for the one that is down here, it literally has cosine 2 theta. Now theta is just what's inside the cosine. In this case, we have, the x, right? Well, actually, this whole thing is inside the cosine, my bad. But point is, instead of theta, here we have x, but the formula works the same. So cosine 2x can turn into this here, okay? So if I go ahead and do that, okay, if I go ahead and do that, I end up with, on the left side, right, I end up with cosine squared x minus sine squared x equals sine x. And you might be telling me, dude, you're trolling, you still have cosine, and I'm telling you, hold up. The IB loves when you use formulas from the formula booklet. There is something planned up ahead for us. So the moment you do this, now this formula looks friendly because this formula has the squares up there, the squared up there, right? And so this formula up here, you can rewrite it and leave cosine alone as cosine squared theta equals 1 minus sine squared theta. So all I really did was pass this guy to the right. Okay, that's all I did. And so once I apply that formula here, I end up with 1 minus sine squared x minus sine squared x equals sine x. And yes, this looks kind of nasty, but hey, look at that. We just got rid of cosine. So again, a lot of times, especially for show that exercises, people get scared because the final answer is super scary and it's super long and it's super hard and all this stuff. But at the end of the day, focus on the small things. You started with cosine and sine. you need to end up with only sine. So use all the formulas and all the tools you have to leave it as only sine. So once we did that, reaching what they asked for is much easier. So on the one hand, we have it equal to 0. And on the other hand, notice, you have a minus 1 and you have a positive for the sine squared. Okay, so we want to leave sine squared positive and have it equal to 0. Those are like the main things we have to do. So if I combine over here, I end up with 1 minus 2 sine squared x equals sine x. And so here, first thing equal to 0, but also keep the thing that's squared, right? I need to keep it positive. Right now it's negative. So here I'm going to go ahead and take the courage to do plus 2 sine squared x plus 2 sine squared x. So this makes me end up with 1 equals 2, here's a squared, sorry, sine squared x plus sine x. And when you have a negative 1, which makes sense because I do minus 1, I end up with 0 equals, and just to leave it as a show that, I end up with 2 sine squared x plus sine x minus 1 equals 0. So bada bim, bada boom. That is for part A. Not that hard. Just keep in mind the process. So with the show that exercise, you got to go from stuff with cosine and sine to stuff with only sine. So use all the tools you have. And this right here is very important. Know the tools you have. Study with the formula booklet. A lot of students don't do this as much as they should. So if you're listening to this video, whatever point in time it is, whether you have the exam in 30 minutes or 30 days or 2 hours, study with the formula booklet, get familiar with it, have it open next to you at all times. There's no reason not to. That is for part A. Then for part B, we have hence solve cosine 2x equals sine x where blah. Okay, and I know some of you might be thinking, what the heck is going on? So basically, on the one hand, it says hence. See, anytime the IB says hence, it's kind of just, it's a big hint that, okay, what you did in part A, you need it for part B. Okay, so having that in mind, what you got to do is, first I'm going to show you visually what's going on. See, before anything, here it's telling you the domain. All right, you guys, and domain is possible x values. And whenever it says solve, in this context, it's going to be for finding the x-intercepts. And so basically it's telling you graph this, right? Graph this and find the x-intercepts within this domain, right? Now, I'm going to go ahead and pull up Desmos, okay, just to show this more literally graphically. So if you graph it, it looks like this. Now here there are a lot of x-intercepts, right? There's this one, there's that one, there's this one, there's that one, there's so many, right? And so what they're telling you is that you need to find all the x-intercepts that are between negative pi and positive pi. So if I go back here, it's between negative pi and positive pi. So all you need to find are this one, and this one. And those are actually the answers. It's negative pi over 2, it's pi over 6, and it's 5 pi over 6. So this is just a bit of context of what we're doing and why we're doing it. Now, like any sine function, the cool thing about it is that it is an infinite cycle. It always looks the same. It always repeats. And so one of the main tools you have is that to visualize this more clearly, you can use the unit circle. And so because this is a repeating loop, so is the unit circle. It is also a repeating loop. And so the answers, the x-intercepts that we're looking for, are sort of hidden in the unit circle here. Okay? So that is the game plan. That is what's happening. That is the intuition behind the scenes. Now that we have that in mind, I'm going to show you the way to solve it, right? And so first things first, for part B, I'm using what I have from part A. So I need to solve this. Sine squared x plus sine x minus 1 equals 0. Now, because it equals 0, I mean, you're finding the x-intercepts because this thing equals 0. Okay, that's the other thing I forgot to mention. You find the x-intercept because this thing equals to 0. Now, from here, this should ring a bell. This should look a little bit familiar, and if you paid a little bit of attention in class, you might realize that this has to do with a quadratic. The IB loves to put quadratics hidden everywhere, okay? And here you have a quadratic because technically, if you go ahead, and this is something you do have to do, by the way, okay? Just to make it more friendly, technically, if you go ahead and call sine x, I don't know, let's call it m, okay? That means for this first part, I have 2m squared plus m minus 1 equals 0. And so, this makes a little bit more sense. So if I ask you to factor this, okay, if I ask you to factor this, find the x's, find whatever, see? Solving this is a lot more friendly, right? And so from here, there's two ways. So you can either do factoring, or you can do the quadratic formula. I'm going to use the quadratic formula just because, in my opinion, yes, it might take longer, but it always works, okay? Factoring is actually mega fast here, but I know some people just don't like factoring, so I'm going to show you the longer but more reliable way. So the quadratic formula looks like this. It looks like negative b plus or minus square root b squared minus 4ac divided by 2a. Now, what is a, what is b, what is c? This is all in the context of a quadratic. So your a is whatever is in front of the x squared. Your b is whatever is next to x, and your c is whatever is alone. So in this context, a is going to be 2, b is going to be 1, because there's a hidden 1 here, and c is going to be negative 1, of course, right? So if you go ahead and plug all of this in, and remember the quadratic formula is for finding the x-intercepts, okay, so is factoring. From here you can end up with negative 1 plus or minus square root of b squared, so it's 1 squared, minus 4 times 2 times negative 1, divided by 2 times 2. So this ends up giving negative 1 plus or minus square root of 1 plus, so it's 4 times 2 times negative 1. So it's plus 8 divided by 4. So from here you end up with negative 1 plus or minus square root of 9 divided by 4, same as negative 1 plus or minus 3 divided by 4. And so from here you need to apply the plus or minus because you gotta do what you gotta do. So once you apply the plus or minus, all you're really doing is saying, okay, there's one answer that has a positive and one answer that starts with a negative, right? So for the positive, I have negative 1 plus 3 divided by 4, and for the other one, I have negative 1 minus 3 divided by 4. So over here, you end up with 2 over 4, and down here, you end up with negative 4 over 4. So that means for your answers, on the one hand, you have 1/2, and over here, you have negative 1, right? Now, these are the answers thinking for m, right? So technically, because you replaced m earlier, technically what you just found is that one of the solutions is at m equals 1/2, and the other solution is at m equals negative 1, which is the same as saying that your zeros are at 1/2, 0, and at negative 1, 0. Now, because I replaced for sine, you gotta replace back. So technically, and you have to do this for getting full credit, here, one of your solutions is at sine x 1/2, and your other solution is at sine x negative 1, okay? So here, I just found my x-intercepts for what I'm looking for, right? Now, because they put it in this domain, it can come in two different ways, okay? This is technically like an angle. See, I know we thought about it as a domain, and visually it's very friendly to think about it as a domain. But in terms of the unit circle, which is the tool we have to use, this is really just an angle, okay? So angles can come as degrees, which is what we usually know, or as radians. And so follow the colors I just put. So degrees is going to be yellow, okay? Radians is going to be blue. And so in this image that I pulled up, okay, degrees is all these guys here. All of these are in degrees. It's usually what we face, okay? It's what normal people use. But sometimes radians is useful, okay? And so radians are here. Now radians and degrees are equivalent in their own way. What do I mean by this? For example, if you look at 30 degrees, okay, its equivalent is pi over 6. 120 degrees, its equivalent is 2 pi over 3 as radians, okay? And for 4 pi over 3, its equivalent is 240 degrees. And so, once we have that in mind, a very interesting thing happens that it's important to have clear, okay? Pi radians is 180. So pi radians equals 180 degrees, okay? So technically what they're asking for over here is the answers where you have negative 180 degrees up until x equals 180 degrees, okay? So these are saying the same thing. All right, that's just a bit of context because I know you've probably seen that somewhere, and I need you to understand that pi radians, okay, it's just pi radians equals 180. All right, that's what I'm trying to tell you. All right, anyways, so from here, how do I find my solutions? And so from here, you have some of your solutions, right? The thing is, you need to transpose your solutions onto the unit circle in order to get the answer. So one of my answers was sine x equals 1/2. Your other answer was that sine x equals -1. And so where is sine x equals 1/2 and where is sine x equals -1 in my unit circle? Guys, sine, cosine, tangent all have something associated to it. So sine and cosine and tangent is oftentimes called the famous so, ka, toa. What the heck does so, ka, toa mean? So is opposite over hypotenuse. Ka is adjacent over hypotenuse. And toa is opposite over adjacent. And so you can use this knowledge here to figure out your answers. Okay, and so I know right now it might seem very weird what is happening, but I assure you it's gonna click in a moment. See? So the unit circle, why is it called the unit circle? Why is it unit circle? It's called unit circle because the radius it has equals 1. It equals 1 unit. See? So notice all these different key points that I'm putting now. So this 1 comma 0, this 0 comma 1, this negative 1 comma 0, this 0 comma -1, right? All of these have a radius of 1. So all of these lines that are actually drawing onto it have a distance equal to 1. All of these have a distance of 1. Okay? All right, why is that useful to know? Because when you start thinking in terms of opposite over hypotenuse, well, all of these hypotenuses equal what? All those hypotenuses equal 1. Because the hypotenuse is the long part of your triangle. That is another thing I have to explain quickly. So your triangle, right? So you have a 90 degrees here. Your hypotenuse will always be this. Hypotenuse is always going to be the long side, period. Okay? So all of your hypotenuses equal to 1. So if you have sine x equals 1/2, that means that, thinking in so, right? If the hypotenuse equals 1, then your only option is that the whole opposite equals 1/2. Now, what is opposite in this context? So, the sine is always going to be, or all these angles, better said, is always going to be in respects to this. See? So, for example, you have this triangle here. Okay, so here you're doing sine theta in respect to that, and so the hypotenuse equals 1, and the opposite is all of this. And so the opposite, notice, it's my height. Ah, it's my y value then. So here, the height of this, the opposite of this, is 1/2. Oh, damn. So the opposite of this guy, right, just to practice, so the opposite of this guy is -1/2. Interesting. Okay. So now that we have that in mind, and you walk into the test having the unit circle memorized because it is something you have to do for this type of exercise, if you look at sine x equals 1/2, and you remember the SOHCAHTOA thing, and you say, okay, this guy on YouTube said all my hypotenuses equal to 1 in the unit circle. So that means I need to look at, for sine, I need to look at the opposite, which is y values. Okay, so technically it's just y values. You got to remember the unit circle and think, where do I have a y value of 1/2? Kapow, you have a y value of 1/2 here. Okay, so one of your answers, because it's in radians, is going to be pi over 6. So the first answer, let me just be very organized, see? So one of your first answers for sine x equals 1/2. One of your first answers, so I'm going to put x1, one of your first answers is pi over 6. Now let's not forget, we're always thinking between negative pi and pi. So the answer you just got, is it within that realm? Yes, it is, right? Pi over 6 is within that domain, see? So this is one of my answers for sure, okay? The other answer that you might have already noticed is that, okay, you have another y value that's 1/2. It's this one here. And so you say, okay, so my other answer is going to be 5 pi over 6. Now, I'm sure at least one of you out there is saying, dude, what the heck? I don't want to remember this whole unit circle. That is insane. And I will answer, yes, it's crazy. And you do need to memorize a part of it, but not everything. And so you can pass from this to this with simple logic. I told you guys way earlier that pi is how much in degrees? Pi is 180 degrees. And so basically, because the unit circle is filled with like mirrors and stuff, the angle pi over 6 here, the opposite of 1/2 here, is the same, if you think about it as a mirror, as the triangle over there. So how can you pass from one triangle to the other? Well, you can think about it as 180 degrees is this whole thing. So 180 minus this blue chunk here, right, makes you end up with the other side, okay? So basically, another way you can think about it is that you can do, if your first answer, the part you memorized, right? If your first answer was pi over 6, in order to find the other one, all you have to do is do pi, which is basically 180, so you're finding the other side, pi minus pi over 6. So for x2, you end up with, you amplify so that you can compare them, so it's 6 pi minus pi divided by 6. So your x2 is going to be 5 pi over 6. So all you really did is that you found your x1, okay? And you did minus pi to your x1. So you did, you did pi minus your x1. Sorry, so you do pi minus your x1. This gives you your x2. That is what I was trying to say. So if you do pi minus x1 for your x2, which is this line of math here, you can get the other side, okay? So again, you can either memorize the whole unit circle or memorize part of it and do the pi minus thing, okay? I suggest doing the pi minus thing, to each their own. So anyways, one of your solutions, as we said, is pi over 6. The other one we said was 5 pi over 6. Now, we're almost done, right? Because this is thinking about sine x equals 1/2. But the other answer that I got in my quadratic was sine x equals -1. So now we gotta go back to the unit circle and think about the scenario of sine x equals negative 1. So sin x equals negative 1, where would it be? Sine is for y values because it's the opposite, and hypotenuse equals 1. So where do I have a y value of negative 1? I only see 1. That was a lot of repeating. So it's right here. There's your y value of negative 1. There is no other. And so this one's a little bit more friendly. Basically, your answer for this one is 3 pi, or the x1 you got for this one. See, think about it that way. So the x1 you got for this one was 3 pi over 2. Now, is 3 pi over 2 one of my answers? Is it within my domain? It's not, because your domain goes from negative pi over to pi. If you want to see it graphically, so my domain is enclosed by the blue and green, there is my 3 pi over 2. It is to the right of the green, so it's not within my domain, so you do not consider it. Now, because this is a cycle that repeats always, you can do pi minus this guy, and you end up with the same sort of intersect, but here, which is going to be negative pi over 2. So visually, that's what we're doing. So you do pi minus this guy here, you're going to end up with the same answer, but over there, because it's a cycle that always repeats. That's why this works. So x1 gave you 3 pi over 2, which does not work, not within the domain, but your x2 for this solution is going to be pi minus x1. So it's going to be pi minus 3 pi over 2. You leave it all in the same sort of fraction denominator thing. So it's going to be 2 pi minus 3 pi divided by 2, which is just negative pi over 2. And so your last answer is negative pi over 2. So basically, if you're more rigorous in your approach or in how you express your answer, better said, you're going to be putting as your final answer, and this is what the answer key says, your x values are going to be negative pi over 2, because you put them in order, right? Comma, pi over 6, comma, 5 pi over 6. All right? So that is how you solve this exercise. It's very important to keep in mind for this last part, for finding the other solutions, you do pi minus whatever you got. See? So you do pi minus whatever you got, and that helps you jump from this to this here. See? Technically, in other exercises, you actually need to add or subtract 2 pi, and all that really makes you do is jump all the way over to like another sort of cycle, okay? And so adding or subtracting 2 pi just lets you go from one cycle to the next. And depending on your domain, because I mean my domain could have been much bigger, right? It could have been 2 pi. That's when that trick helps. The adding or subtracting 2 pi in case your domain is bigger. In this case, we didn't need to do that, but I'll point it out anyways because, well, I mean, I'm sure some of you out there need to figure that out. See? And last but not least, I would like to make uh, an observation. See? This last part was hard. This last part took a lot of time and took a lot of knowledge, and you needed to know about the unit circle and a bunch of stuff. See? So take a moment, look at the answer key. So looking at the answer key, well, part A is worth 1 point, and it's a lot of formulas and stuff, and you gotta know what's going on. See, so that is a hard point to get, in my opinion. But then for part B, it's worth 5 points. And 4 of the points, dude, it's crazy. 4 of the points is just doing the thing of the quadratic and finding the x values. Finding the initial solutions, right? But the whole thing about the unit circle and the sine and the cosine and all that stuff is only worth 1 point. So I'm just pointing it out, you guys. Especially if you're low on time, do the part that is quick. Do the part that is just factoring and the quadratic, right? Think about it this way, you guys. This that I'm putting now in, let's say, light blue. See? So this that is in light blue, this is worth 4 points. And this that I'm putting in purple, this whole thing is worth 1 point. It's crazy. It's actually crazy. So if you have time, study with the mark scheme and notice what the IB gives more points of or less. Okay? Now, it could have been that this was worth, I don't know, 3 and this other one was worth 2. That can happen. Okay? It can happen. I feel like sometimes it's subjective. I'm not sure how they define it. I have no idea, but I'm just pointing it out, you guys. Do the do the quick part first. See, the part that is in light blue is something you should be able to practice and manage pretty quickly. And the part in purple, well, it's harder, and I'm sure sometimes it'll be worth maybe more than 1 point, but it's much more time consuming. Especially for a test. This is not just a test of math, you guys. It's also a test for your test taking skills. It's also a test with time. Your time is not infinite. It's not a lot, actually. So prioritize. Do the fast parts first, the hard part later, or the more consuming part later. See? All you care about is points. You don't care about answering everything perfectly. You care about getting the maximum amount of points, so use your time wisely. You should be answering at least a little bit on each question. Don't get stuck on the hard part and not end up doing other questions. See? I just want to point that out because I don't know, this isn't just a math channel, this is an IB channel. And I know you're going to be giving the May exams, the November exams, and I'd rather give all the tips and tricks I can. See? So keep that in mind, use your time wisely, and yeah, I hope it helped. Alright, you guys, and now for number 5, we need to find the range, okay, the range of possible values of k such that this has at least one real solution. So I know that for a fact, a lot of you look at this and you say, alright, next question. But there is one big hint here that once you start noticing is going to help you to answer all exercises similar to this one. And it has to do with the last couple buzzwords, which say that this thing has at least one real solution. And so, of our tools that have to do with amount of solutions, there is only one. And your tool, which is in your formula booklet, by the way, is what we call the discriminant. And so the discriminant of a quadratic equation is this guy here. And so notice, where does the discriminant comes from? The discriminant, which is right there, comes from this right here. And so how do you interpret the discriminant? Anytime your discriminant is, for example, greater than 0, you have two solutions in your quadratic. If your discriminant is equal to 0, you have one solution. And if your discriminant is negative or below 0, then you have 0 solutions. Now, something I need to put a quick like disclaimer here is that it's two real solutions. It's one real solution and it's 0 real solutions. Technically, you can have imaginary solutions, okay? And this has to do with imaginary numbers. I'm not gonna get into that, but basically, whenever you have a square root that is, for example, negative, you can solve it because I, your imaginary number, equals square roots of -1. And so through this, you can actually solve square roots of -4. I'm not going to show you because it doesn't really matter for this, but that is why here it says one real solution, okay? It's not asking you to go into the realm of imaginary numbers and crazy stuff. It's just asking for you to find the discriminant when it is greater than or equal to 0. Why greater than or equal to 0? Well, we said that greater than 0 was for two solutions. We said that equal to 0 was for one solution. And so if it's at least 1, then it is either 0 or greater. So discriminant has to be greater than or equal to 0. So awesome. We just identified that we need to use the discriminant and that is the way to go, and you're going to find the discriminant when it's greater than or equal to 0. But you're probably looking at this and telling yourself, how the heck is this going to be a quadratic? This does not look like a quadratic. What is this guy on YouTube trying to tell me? And so generally, you shouldn't trust people online, but just for today, you can trust me, okay? And so from here, once you identify the thing of the discriminant, and that you want to try to reach something that looks like this, because this is where the discriminant comes from. It comes from a quadratic, right? Once you identify that, try to reach that, okay? And so for using the discriminant, it's also important, notice here, that they equal it to 0. Whoops, it's not letting me highlight what I want. For the discriminant, you need to equal it to 0. Okay, once you equal it to 0, you can use this guy here, you can use this guy there. I mean, it's not that you need to equal it to 0, but for our intents and purposes, for reaching what I haven't read, let's try to do that. Leave 0 on one side, okay? And so notice, your quadratic, its first term has an x that is squared. Its second term does have an x, but it's only to the power of 1. And your last term does not have an x. So if I try to replicate that, I can do minus 3e to the power of x to both sides. I end up with e to the power of 2x minus 3e to the power of x plus ln k. And this, believe it or not, is a quadratic. Now, I really want to explain why. See? So notice, a quadratic, as I said, its first term has something squared for x. Here is your squared x, okay? The 2x on top. For bx, you only have x, like 1 times x, right? So it's legit, right? And this last one does not have an x, so that is your c, okay? All right, I know this might be a little bit hard to like visualize or imagine, so another way that I can help explain it to you is imagine you're substituting just for a second, I don't know, that big A equals e to the power of x, okay? So if big A equals e to the power of x, that means this first term ends up as a squared. Because if you square both sides here, you end up with a squared equals e to the power of 2x. Ah, okay. So that means this first term can be rewritten as a squared minus 3. Oh yeah, so a is e to the power of x minus 3a plus ln k. This looks more like a quadratic now, doesn't it? But really, it's the same as this. All I did was replace big A for e to the power of x to make it easier to visualize it. Okay, but really, this is still a quadratic. So guys, I think the hardest part of this exercise is what I just explained, is realizing that when they say one real solution, you gotta be thinking immediately in terms of discriminant, and if you're thinking in terms of discriminant, you are in the realm of quadratic equations. So try to find that quadratic equation, as crazy as it might seem, and in this case, it was staring at us this whole time. And so from this step here, you can go ahead and define little a, little b, and little c. Okay, remember that this comes from ax squared plus bx plus c, and so little a is what's in front of x squared. So in front of my x squared, in this case a, we have a 1 times a. So little a is going to be 1. For this next part, we have minus 3 for b. And for this next part, as crazy as it is, your c is ln k. After all, ln k is just a number. And so from here, you can use the discriminant, right? And so the discriminant, we said, and from the formula book that we know, it's going to be b squared minus 4ac. So first, let's find out what my discriminant is, and then let's apply this thing here, the greater than or equal to 0, because we're talking about at least one real solution. So first, let's solve for the discriminant. So if you go ahead and plug in, you end up with b squared is negative 3 squared minus 4 times a, which is 1, times c, which is ln k. And so all of this equals your discriminant, okay? So your discriminant ends up being 9, because negative 3 times 3, minus 4 ln k. All right, interesting. And so from here, we need to apply our condition, which is the discriminant being greater than or equal to 0. So this whole thing has to be greater than or equal to 0. And so because we want to find the values of k, try to get k alone. So from here, what I would do, there's a couple different ways, but what I would do is just plus 4 ln k to both sides. That way you get k a little more alone, right? So this goes away with this. You end up with 9 being greater than or equal to 4 ln k. You want to keep getting k alone, so you can divide by 4, divide by 4. You end up with 9 over 4 is greater than or equal to ln k. Now, just because for me it's easier to visualize it, I'm going to flip it for a second. So ln k is less than or equal to 9 over 4. See? And from here, we're pretty much at the last step. And so from here, you need to find the value for k. You already got k alone as much as you can. And the last step is a little bit creative. Okay, you have to be familiar with logs and stuff like that. And so because we need to be familiar with logs, let's go to my formula booklet and look for logs. Oh, it's actually just right there. So as you can see here, first things first, the exponential function and the logarithmic functions are like inverse of each other. See? So for example, in math, you have plus and then you have minus. You also have multiply and then you have divide. Like all of these are opposites, right? And so you also have the exponential function and the logarithmic functions. Okay, those are also opposites. And so how do you like read the logs? Well, this is actually how the exponential function interacts with the logarithmic function. But technically the definition of log, I hope it's here, or else I'll just give it to you, but logarithmic. Is there really not the definition of log here? Wow, that's crazy. Well, you learn something new every day. Oh, there it is. Okay. So here, sorry about that. This is the definition of log. What I showed earlier, I'm going to leave it in the video because it's still relevant. It's how the exponent function interacts with the logarithmic function. But this is like the hardcore definition of log. See? So notice here. Basically, what's happening, start from this side. Okay? Start from this side. So basically, what you ask your logarithmic function is your base to the power of something gives you what's in parentheses. Your base to the power of something gives you that parentheses. It's the same thing. Okay? And so if I go over here, your base, what is your base here? It's natural log. And natural log always has a base of e. Normal log always has a base of a. I mean, damn, sorry. Normal log has a base of 10, unless they tell you otherwise. Okay? If they tell you otherwise, you have a different base. But the standard, the default, is that natural log has a base of e, log 10 has a base of 10. And so here you're asking, like this whole thing basically, is that e to power of something, something is on the other side, right? It's on the other side. So e to the power of that something, 9 over 4, has to equal k. Ah, okay. So now we're getting somewhere. And so this now gave me like how far k can go. Okay? If k goes anywhere beyond this, it stops working. But anywhere less than this, it's okay. See? How do I know this? Because ln k has to be less than or equal to 9 over 4. And so because it has to be less than 9 over 4, then k can go as far as 9 over 4. All right, awesome. And so for writing down the range, well, ln k in this function here, it's inside a logarithm. And so something that I didn't tell you earlier, but I tell you now, is that the logarithm, the value that's inside, has to be positive. And so whatever's inside has to be positive. And so now, for example, if I pull up a quick graph on Desmos, just so you can see it, here I'm graphing ln of x. Notice how the inside, my x values, I don't have a single negative x value. I have negative y values, yes, but there's not a single negative x value, okay? Because what's inside my parentheses has to be positive. And so that immediately tells me that k, okay, k has to be greater than 0. And I just found out from down here that this is the maximum value that k can take. So k has to be greater than 0, and also it has to be less than or equal to e to the power of 9 over 4. And that, ladies and gentlemen, is how you do number 5. So again, I don't think it's incredibly hard, but the hardest part, for me at least, is realizing you have to use discriminants. Now, I've also realized, because I've done a couple of these tests already, is that the thing when it says has at least one real solution, it's a massive buzzword. Okay, it's a massive hint that you need to use discriminant. So whenever you read at least one real solution, or at least two real solutions, or even no real solutions, whenever it talks about solutions, bada bim, bada boom, you're talking about discriminants, you're talking about the quadratic function. Try to find the quadratic function. I know it can be hard to visualize, so substituting can be a very good idea. Ladies and gentlemen, that is number 5, and I hope it helped. All right, you guys, for number 6, it's not incredibly hard, but it is incredibly specific. So if you keep in mind one or two things that have to do with the sinusoidal functions or the sinusoidal exercises, I think you'll be good to go, okay? And so a lot of these is just context. If you understand it well, you're good to go. If you've never seen or never reviewed the sine function, there's not much I can do to help you because not even the formula booklet has a lot of tips and tricks here. This is stuff you just kind of have to know, okay? So just a heads up, it's not that hard, but it is very specific, okay? So, number 6. The function f is defined by f of x equals sine qx, which is this guy that you're looking at here. They tell you that q, the guy inside of the parentheses for sine, is positive, okay? The following diagram shows part of the graph of f for these values here. Now, what the heck does this even mean? Well, because there's an x in between it, it's basically telling you, dude, your x values go from 0 up until 4m, which is why in your graph you go from 0 up until 4m, okay? And so that is how far your x values can go, and that also affects your y values, right? Because you can't have an x equals 5m, you don't actually have a point here for y, see? So that is what they define as domain. And so let's just recall that for a second. Domain is technically your possible x values, okay? Well, range, you guessed it, is also your possible something, but in this case, your possible y values, okay? So your domain is possible x values, your range is possible y values. Here they define your domain. They also mentioned that x is in radians. Now, what the heck are radians? Radians, whoops, apparently radians is a powerful word. So radians is just a way to express degrees. All right, so let me just give you an example. It'll make a little bit more sense. 2 pi radians, okay, so 2 pi radians equals 360 degrees, while 1 pi radian equals 180 degrees. It might make a little bit it might make a little bit more sense if you look at a unit circle graph. So in Google you're gonna find, sorry I had to cough for a second. So in Google you're gonna find a lot of different unit circles. And so for example here, right, you have that for 90 degrees its equivalent in radians is pi over 2. For 270 degrees its equivalent is 3 pi over 2 radians, all right? And as I said, 180 degrees has a single pi next to it. Okay, so that means if you went all around, that means if you went around again with 180, you need to do pi plus pi, you end up with the 2 pi I mentioned here, see? So everyone chill out, chillax, radians is just a way to express angles, okay? And why can this be useful? Because, well, once you memorize the unit circle, which you should for the test, it is an amazing tool which helps for a lot of the steps you're about to see, okay? Anyways, blah, blah, blah. There are x-intercepts at x equals 0, at 2m, and at 4m, okay? So for part A, we need to find an expression for m in terms of q. So first things first, when they say m in terms of q, what this is really telling you is that they need m to be alone. I'm going to be very clear on that. When they say m in terms of q, it means that m is alone, and you're going to end up with a bunch of q's on the other side doing a bunch of different stuff. Maybe it's 2q, maybe it's q plus 7, whatever, okay? M has to be alone, and on the other side, the
only variable you can have is q. And so the classic would be y in terms of x. And so an example of y in terms of x would be y equals, because y has to be alone, y equals, I don't know, ax squared plus bx plus c, right? Well, actually, in terms of just x, I could not have a, b, or c. Maybe that wasn't the best example. You would end up with, I don't know, 7x squared plus 4x plus 5. And so, yes, you end up with a lot of different terms, but what would be the only variable? Your only variable is x. You do have a bunch of different x's, but only x. There isn't a, there isn't b, there isn't c. It's only x. So that is what it means when it says m in terms of q. M has to be alone, and you will end up with only q's on the other side. Now, to further understand how to solve this, you first need to identify where q is. And so q is inside the parentheses of sine. Now, if you don't know much about sinusoidal functions, or you didn't review in time or whatever, that is useless information to you. So let me give you a quick review for how sine functions work. Okay, technically a sine function, all right, so I'm just going to write it over here. Technically a sine function will have 4 different key values. Okay, you have a, you have b, you have c, you have d. And so technically your sine function, I'm just going to put sine, I don't know, sine x, okay? A, B, C, and D, enter it in various different ways, all right? On the one hand, you can have an A that is multiplying right outside. Now, A is easier to remember. A will be associated to amplitude, okay? What is your amplitude? Your amplitude is in your sine function, right? For example, here. In your sine function, your amplitude will be how high or low it goes in respect to the x-axis. And so an amplitude here, for example, from here to here, and let's say that this is 0, and then this is, I don't know, 2, and down here would have to be -2, right? And so your amplitude here would be equal to 2, just as an example, okay? The other thing that can happen, all right, is this b. So this b is going to enter inside the parentheses. So your b that I'm about to explain now and explain what it does, the b is the q. All right, so like b equals q in the explanation I'm about to do. Okay, so what is b? Well, b has to multiply x inside the parentheses, and there's not a too much of a clear definition I can give you, but b is associated to the period. I'm not saying that it is the period, but it's associated to the period. Why is it associated to the period? Because the formula for period, and this is very important, this is not in the formula booklet, write it down. The formula for period is 2 pi divided by b. This is in radians, by the way. If you want to have it in degrees, you can say 360, as I taught earlier, divided by b. All right, so the period, b is heavily associated to the period. It helps you a lot to find it, okay? And so this is a massive hint for how to, find Q in our exercise, but for now, let's move on. B is just sort of associated to the period, right? Think about it this way. If you have a B that is bigger, that means your function is doing repetitions more quickly, right? So this is a bigger B, all right? And a smaller b, like less than 1, means that your repetitions are a little bit longer than before, okay? And so that's the idea. A b that is less than 1 would look something like this, and a b that is greater than 1 would do its repetitions more quickly, right? That's the main idea I'm trying to tell you guys. Yeah. What else? So c, technically c, would be something like this. C, I don't see it show up too often, I'll be honest. But technically C is something that is adding or subtracting inside, and is what we're going to call a horizontal translation. How can you memorize this more easily? Well, notice that it is adding or subtracting directly to x. And x is associated to your horizontal values, because in your xy axis, your x is horizontal. So whatever is adding or subtracting specifically to x will be a translation to the left or right, okay? And last but not least, for D, you guessed it, it's going to be the vertical translation, okay? And so you might be thinking already, well, if I look at my function here, I have sine parentheses qx, right? And so sine parentheses qx, does it have a horizontal translation? Does it have a vertical translation? And technically I would say yes, but it equals 0. And even for amplitude, it does have an amplitude. Like, what is multiplying sine qx right now on the outside? A 1. There is a 1 hidden right here. And so your amplitude is equal to 1, which is why from here to here, the distance is 1. Ah, look at that. That's why the distance from here to here is of 1. And the vertical translation, the plus d that is like outside, well, here I have a plus 0, right? You have a plus 0, which makes sense because if you look at the like the line that cuts through your sine, it's actually at y equals 0. So I'm just saying, you guys, that is the context of the stuff that can show up. And more often than not, what you end up using the most in my experience is what I told you for the formula of the period. Okay, so let's go back down here. Let's see how that plays out for our exercise. And so you want to find m in terms of q. And you know that q is associated to the period. So immediately you can already say, right, you can already say for part A that the period equals 2 pi divided by b. And you know that b, from the function that they gave you, sine qx, you know that b is whatever multiplies x inside the parentheses, so period has to equal 2 pi divided by q. All right, now we're getting somewhere. Now we just need to find whatever period is, okay? And so period, I vaguely defined it earlier as like, it sort of affects like how fast or slow you do like these repetitions on your sine function. But maybe a better way to put it, or how I like to, remember it, okay, is that your period is like the distance from max to max. So period is the distance from max to max. Now this is the hardcore definition, but this actually has a bunch of different implications I'm about to show you. And so from max to max, well, if I were to keep graphing this, right, following the pattern that I see, I would need to have a maximum over here, right? And then it would cross again over there, right? And so from max to max, you can think about, so it's from here to here, this is a period, right? And so this is going to be one period from max to max. So you're thinking it's 5m minus 4m. So 5m minus, 5m minus m gives you 4m. I gave the answer out loud. So 5m minus m gives you 4m. So the period over here we're going to call 4m. So 4m equals 2 pi divided by q. Now before we move on with the math, let me explain why knowing the period can be very useful. And so the period, as I said, is the distance from max to max. But technically, depending on the exercise, it can also be useful to think about it as the distance from the minimum to the minimum. After all, it's the same, right? If you compare the max to max, it's the same as if you compare from the min to min. And the other cool thing that you can start considering, and I know this is going to be a little bit trippy, but it's very useful to know, okay, is that imagine this red line that I drew, okay? So this red line that I drew, that goes like this for period. Imagine you shift it to the left little by little. So if you shift it to the left little by little, on the one hand, you would end up with something that goes, I don't know, like this. Then you go with something that ends up a little bit like this. And lo and behold, eventually, damn, you end up with something that looks like this. Something that is touching the x-intercepts. Ooh la la, that seems incredibly useful. Maybe not now, maybe for later. And so thinking about the period can be a massive hint. Now, here technically, it gives you the x-intercept of 0 and the 4m, and there's also one in the middle for 2m. So you gotta watch out for that kind of detail. But you know for sure, the period also helps you find the x-intercepts because the sine function, it goes on like this forever. And so any sort of proportion that you find from here to here, or from, I don't know, there to there, or even from, you know, like from here to here, is something that plays along the whole graph all the time. And so the period distance, it's a cycle that repeats, can be useful to know to find all these different sort of values. The last thing I'm going to tell you, just because the IB loves to, do exercises like this, is that technically here, they didn't give you the other maximum, right? I mean, I drew it and it was very easy to spot what the period had to be, but imagine you didn't spot it. What could you have done? Well, the period, as you can see here, as I said, it's from max to max, but you can also think about it as like, if a period is a distance from max to max, you can also think about it as twice the distance of max to min. And so if you take the distance from max to min, which is usually what they give you actually, just like half a cycle or whatever. So if you think about from max to min, this distance is 3m minus m, it's 2m. But this times 2, you know for a fact has to give you the other max. So 2m times 2 gives you 4m. Okay, so that is another way to find the period. You take the distance from the max to a min and multiply by 2. All right. Why does this work? As I said, the sine function repeats forever, so all these different properties really start to shine. All right. All right, that's a lot of blah blah, but sometimes you need blah blah in your life, especially for math. So yeah, deal with it. Anyways, here we are, and here we are almost done. And so you want m in terms of q. That means that m has to be alone. So m has to be alone. How do you get m alone from here? Well, it's being multiplied by 4, so you can divide by 4 to both sides. So that means this goes away with this. M has to equal 2 pi divided by 4q. You divide by 2 on the top and on the bottom. M, whoops, that looks like a very nasty M. So M has to equal pi divided by 2q. So let me put this in light blue just so that we recall what's going on. M has to equal pi divided by 2q, and that is for part A. Then they tell us that the function g is defined by g of x equals 3 times sine, and then parentheses 2 over 3 times q times x. For a new domain, so interesting, so now your function reaches a little bit more. Instead of reaching 4m, it's going to reach 6m. And on the axis above, you need to sketch the graph of g. Now guys, I'm going to mention something right away. Yes, it's a sketch problem, and you might be thinking, haha, easy points, but it's worth 4 points. And so sketching is not only about nailing the visual aspect of how it should look like, it's also nailing what I'm going to consider like key points slash aspects, okay? And I'm just going to leave this clear right away because I feel like a lot of people miss points on sketching just because they don't understand that, dude, it's not just about it looking nice, it's about it being accurate and putting the key points and the key aspects. So let me actually show you the answer key for a second. Over here you can see that the 4 points that show up is on the one hand that the scale factor is seen anywhere. So that this is like the part of like it looking it nice. But then you need to be accurate on the amplitude. Then you need to be accurate on the domain. Then you need to be accurate on the max and min and x-intercepts. And so again, this up here is like looks nice, right? But the majority of points is like that it's actually accurate, okay? So careful, you guys. It's not just about drawing anything. It's about drawing stuff that is actually accurate. These points that they're putting here, right, are not just any points. It's the max and min. It's the x-intercepts. And we're about to find out how to get those specific points with certainty, all right? So the main idea we have to like follow through with is that they're asking you to sketch something which looked similar to f of x. So how did f of x look? They gave us that f of x was sine qx. And now they gave us g of x, which is 3 sine parentheses 2qx divided by 3. And so think about it for a second. What is happening here? Well, on the one hand, my amplitude used to be 1, and now it passed to be 3. So that's the first thing I need to observe for part B. The amplitude, remember that amplitude is whatever is in front of your sign, right? So your amplitude now is going to be 3. So first thing first, amplitude equals 3. The other thing you can observe is that now your period is not just q, it is 2q divided by 3. And so your new b, which is going to affect your period, it has to be 2q divided by 3. Before your b was just q, now it's 2 over 3q. Everything else is the same. And so you have a new amplitude, and you have a new b, and you just see how this affects your max, your min, and all that stuff, right? Now, I did tell you guys earlier that if your b is greater than 1, your frequencies happen like faster, right? And if your b is less than 1, but also positive, I forgot to mention this, less than 1, but also positive, you end up with a period that like takes longer to happen, right? And so from here, your new b is 2 over 3. So that is a little bit less than 1, but it's still positive, and so your period will take longer to occur. Okay, so that means this maximum here is probably going to be, I don't know, somewhere over there. Okay, so it's going to take longer to occur the maximum and longer to occur also the minimum. Okay, and so everything is going to be like a little bit more delayed if you want to think about it that way, because your value for b is less than 1 compared to before. See? I mean, it's less. Okay, it's less. All right, anyways, so I think the most important thing that you can do is always going to be apply the period formula. And so you apply the period formula from here, the new period, so let me just go like this for a second. So the new period has to be, well, you don't figure it out yet, right? And so the new period, well, we're going to put period equals 2 pi divided by b. Now b we said was 2q divided by 3. And from here, you're working with fractions in a very nasty way. What I suggest that you do is that this numerator, you can put it as 2 pi divided by 1, and on the bottom you leave it as 2q divided by 3. All right? I like to think about it this way because technically from here, you can say, so because this is like a big division symbol here, you can think about it as 2 pi over 1 being divided by 2q over 3. And when they divide like this, you end up with 2 pi over 1 times the reciprocal, 3 over 2q. And so 2 pi is going to multiply 3, and 1 is going to multiply 2q. Right? This is just how you handle big fractions. Now notice, here's something interesting. The last, and this is like a math tip, okay? So the last step you reach is 2 pi times 3 and 1 times 2q. And so something very visually appealing when you have big fractions like this is that the 2 pi times 3 up top are the extremes multiplying each other, while the 1 times 2q are the ones in the middle multiplying each other. Interesting. And so you can just do like the edges times the edges and the inners times the inners, and you get the same result. And so that's how I like to do it. I think about the edges times edges and the inners times inners for big fractions, okay? Whatever, to each their own, see? Point is, you're going to end up with 6 pi divided by 2q. And so period, right? Let me just be a little bit more organized in my approach. So period, as I was saying, has to equal 6 pi divided by 2q. Now you can divide by 2 on the top and on the bottom, and so period has to equal 3 pi divided by q. Now q is a little bit hard to read, and it's actually not that useful it would actually be more convenient if you replaced q with something that you can read. For example, m. Your whole x axis is detailed with a bunch of m's. And so if you put this in terms of m, it's actually going to be a little bit more friendly to be able to read. And so lo and behold, what you need in part B comes from something you did in part A. So from this here, from part A, you can get q alone. And so you can do 2mq equals pi, right? If you multiply 2q to both sides. So this goes away with this. And if you get q alone, you can say that q has to equal pi divided by 2m. And so on. Now this, I can plug it in over here. And you end up with 3 pi divided by pi divided by 2m. And here I do the big fraction tip. So 3 pi divided by 1 divided by pi divided by 2m. I do the extremes multiplying each other, so it's 3 pi times 2m divided by 1 times pi, so just pi. Now, because it's all being multiplied, this goes away with this, and the period, period finally becomes into something more readable. Period has to equal 6m. Okay, so your period is 6m, and this already gives you a whole point, okay? Now, remember how I mentioned earlier that the period, you can think about it as max to max, right? Or you can think about it as min to min, right? You can also think about it as from min to min. Well, you can also think about it as, I mean, the actual math definition is max to max or min to min, but you can also think about it as x-intercept to x-intercept, right? Because it's all sort of parallel in a certain way. And so from here, what you can say, technically, right, is that because your period is 6m, right, you need to have an x-intercept here, right? So if you have an x-intercept here, you also have one over there. Now, you know for a fact you have one over here, and this is important, right, for the implication I'm doing. You know you have one over here because there wasn't any horizontal translation. If there would have been a horizontal translation, your first x-intercept of equal to 0 would have shifted, right? If you had a horizontal translation a little bit to the right, then your new graph would have had a different x-intercept. But because there wasn't any horizontal translation, you know for a fact, this is the right way to think about it, you know for a fact you have an x-intercept here because there was no horizontal translation. Because of the new period, you know for a fact there has to be an x-intercept all the way over here because this point repeats in 6m again, and that would be over there. That's the idea of the period. Like if your period is 6m, whichever point you look at, its height will repeat in 6m more units, or in that period amount of units, okay? So if you have an x-intercept at 0 and the period is 6m, you need to have an x-intercept at 0 plus the period, so 0 plus 6m, right? Just going to be 6m. All right, enough blah blah. That is one way you can identify some of the x-intercepts you need. So starting from there, we have something, right? The other thing we need to acknowledge, right? And so the other thing we need to acknowledge is trying to find which, like, is the x value, okay, of my maximums and minimums, okay, which is also going to be a big hint to see if you have another x-intercept in between. And so right now, for example, in the original one, you knew that the amplitude was 1, and so all the maximums and minimums had to be at a height of 1 or -1, right? For a fact. And so from here, well, you know that the amplitude is 3. And there wasn't a vertical translation, so the maximum or minimum only depends on the amplitude, right? If there would have been a vertical translation up here of like +1, and then another amplitude change, then yeah, you would need to consider like a different sort of approach. But right now, the only thing affecting my maximum y value is the amplitude that like appeared. And so because the amplitude over here equals 3, that means that your maximums for this new graph are going to be at 3 for a fact, or they're going to be at, for the minimum, at -3. All right, and now we're getting somewhere, right? And so basically what you can do from here is that you can say, okay, so I want to find the x value of the maximum, right? And so you know the maximum is somewhere at y equals 3, right? And so if you plug in y equals 3, you're going to be asking your function, where is my maximum, right? So if you take g of x, so you know that g of x is, you know, maybe something with more space. So you know that g of x from the exercise is 3 sine 3 times sine 2qx divided by 3. And so the moment you plug in 3 for g of x, you're plugging in the y equals 3 I mentioned earlier. And so you're asking your function, when y is 3, what is x? Okay, and the moment you find your x value is the moment we can really plug in like the maximum point with more accurate description. Okay, so that is what we're trying to do. You're trying to find the exact x and y coordinates of your maximum. So if you plug in 3 for y from here, you can end up with 3 equals 3 sine 2qx divided by 3, right? Now from here, you want to get your x value alone, right? Or leave it into something a little bit more readable. So first things first, you can divide both sides by 3. So you end up with 1 equals sine parentheses 2qx divided, all of this divided by 3, right? Now, the most annoying thing from this step right now is that you have a sign going around. So guys, how do you get rid of sine? What is the opposite of sine? The opposite of sine is sine inverse. So if you do sine inverse to both sides, you're going to end up with this going away with this, and so sine inverse, sine inverse of 1 is going to equal 2qx divided by 3. All right, and here's something I need to mention, like more from a conceptual stand of view. Whenever you do sine of something, as you can see, you get rid of sine and end up with only what's in the parentheses. But there's something I need to like point out that's very, very important. Okay, whenever you use sine, and this actually does show up a little bit from the booklet, so just as an example, whenever you use sine, remember or look, it's always like sine theta, right? And so what is theta? Theta is a way to express angle, okay? And so theta is an angle. The sine always has sine, like whatever's inside the sine, this is what I'm trying to tell you. Whatever's inside the sine is an angle, yeah? And so from here, when you do sine inverse, you end up with just the angle of 1. And so basically, this right here, although it sounds kind of crazy, is trying to, it's asking like, what is the angle at sine of 1? That is what it's asking for. What is the angle at sine of 1? And angle in terms of radians, because this whole exercise has been done in radians, okay? And so that is a weird question to ask, but that is why earlier I said, dude, if you know the unit circle, you're good to go. And so sine, right, we have associated sine and cosine and tangent to the famous so, ka, toa. And so ka, toa, the so is telling you opposite over hypotenuse, the ka is telling you adjacent over hypotenuse, and the toa is telling you opposite over adjacent. And so your unit circle is actually filled with a bunch of different triangles, see? So actually, if you go ahead and draw the unit circle just for a second here, right? So if you draw the unit circle just for a second here, you're going to notice that there's a bunch of different triangles that show up in all these different sort of key angles that they're throwing at you. And there's one key thing you have to acknowledge. The unit circle, what dimensions does it have? What dimensions does it have? This point here is 1, 0. This point here is 0, -1. This one is 0, 1. Sorry, that could not have been more wrong. this point here is negative 1 comma 0. And wow, I'm on a roll today. This one is 0 comma 1. Okay, so this one is 1 comma 0. This one is 0 comma 1. This one is negative 1 comma 0. And this last one is 0 comma negative 1. Okay, that makes more sense. And so from here, you're telling me that the radius is equal to 1. In all of these, the radius equals to 1. In all of these key different triangles that they're throwing at you, the radius equals 1. So all of these hypotenuses are equal to 1. Right, that's interesting. And so when you have a sine of 1, well, the hypotenuse equals 1. And so all this is really telling you is that the opposite equals 1. And what is the opposite in all of these triangles? The opposite of all of these triangles for a sine that's going over here, well, the hypotenuse is 1. And the opposite will always be, because it's the vertical like sort of growth, the opposite will always be the y value. So you gotta go to your, what this is telling you is go to the unit circle and find the y value that equals 1. And so the y value that equals 1 is this guy up here. And what is the radian associated to it? Pi divided by 2. That is what sine inverse is doing. Okay, that is what it's doing. And so from here, well, basically, this whole thing on the left is just going to turn into pi divided by 2 equals 2qx divided by 3. Now from here, get x alone. And I know we have a q going around, but I'll explain how we handle that in a second. Just for now, okay, get x alone, see? And so the first thing I would suggest that you do is that you can multiply by 3 to both sides, okay? So you multiply by 3 to both sides, this goes away with this, you end up with 3 pi divided by 2 equals 2qx. So from here, you can divide by 2q to both sides. That means you end up with 3 pi divided by 4q equals x. Now, this is not a good enough x value for us to read because our thing isn't, our x-axis is only in terms of m. It does not have a q in between, so it's very, very weird and confusing. But lo and behold, once again, part B needs something from part A. And so earlier we said that q can be written as pi divided by 2m. So we're going to do that once again. So q equals pi divided by 2m. That means that over here you end up with 3 pi divided by 4 times pi divided by 2m. All of this equals x. So let me simplify what's on the bottom first. So you end up with 3 pi divided by 1 divided by, this goes away with this, you end up with 2 pi divided by m. So all of this equals x. You can multiply the edges with the edges. So it's 3 pi times n gives you 3 pi m. And then the inner with the inner is 1 times 2 pi, so it's going to be 2 pi. All of these equals x. You can divide or get rid of pi on the top or the bottom. So x equals 3m divided by 2. And this, ladies and gentlemen, let's recall, comes from the fact that at some point, where is it? Here. That at some point, you plugged in 3 for y. So you were asking your function, yo, when y is 3, what is x? And why did we choose 3? Because the new amplitude from here was 3, right? So the new amplitude was 3. So that means the maximum has to be at y of 3 and then x of, as I discovered, and then x of 3m divided by 2. And so at 3m divided by 2, so 3m divided by 2 is the same as 1.5m, right? And so 1.5m, which is right around here, is where you're going to have your maximum, okay? So boom, we finally got one of our key points. But from here, everything is just kind of like smooth sailing. And so from here, that means that my function for g of x is going to look initially like this, okay? And now we need to see where it might touch, like for the x-axis, right? Now, to further understand that, let's take the following idea. From 0, in the original one, right, the black line, from 0 to m, you first reach the maximum, and then you would add another m, right? So from the distance from 0 to your max, you add this distance again in order to reach the x-axis, right? And so if you take this 1.5m and you add that distance again, right? So this adding itself again, you end up at 3m. And so at 3m, you need to have one of your x-intercepts. And so, okay, so that means that for g of x, you have your maximum here, then you cross the x-intercept over there, and then you add another 1.5, right? So you add another 1.5, that means you end up at 4.5. So at 4.5 is when you're touching for your minimum. Because as we said, that max and minimum have to be at 3, and all the process we just did was for finding the corresponding x values. See, so over here, I'm going to go ahead and write 4.5m, okay? That means I have a minimum, over here. And if you continue with this logic, lo and behold, you're going to end up with an x-intercept right there. So ladies and gentlemen, that is the appropriate way for graphing and sketching for number 6. I don't think it's incredibly hard, but you do need to be very conscious of the different tools, and especially the tools that are not in the formula booklet. I think understanding the context of what A, B, C, and D does is massively important, and just as a hint, I've seen that it's extremely important for you to know well the formula for period, okay? Know the formula for period, you pretty much always have to use it, okay? Ladies and gentlemen, that is how you do number 6, and I hope it helped.
All right, you guys. So for number 6, the math is not that hard, but the concepts are really hard to grasp. So let's go piece by piece. On the one hand, they tell us, for some reason, that the side lengths x centimeters of an buzzword equilateral triangle are increasing at a rate of 4 centimeters per second. They also tell us, or the question really, is to find the rate, so find the rate at which the area of the triangle is increasing when the side lengths are 5 square root 3. And so this exercise, as I said, is pretty hard in terms of concepts, but in terms of math, it's very straightforward. Like I could show you the math lines in less than a minute and just show you the answer, but I really need you to understand why we're doing what we're doing. And so let's go piece by piece. On the one hand, we've got the famous equilateral triangle. Now, you guys, you usually run into 3 types of triangles, okay? On the one hand, you have the isosceles. On the other hand, you have the equilateral. And last but not least, you might be facing this thing called the scalene triangle. And so the isosceles is a little bit more of a classic, It has 2 sides which are the same, and therefore 2 angles which are the same. And it has one last sort of angle or side which is different. See? For the equilateral, following its name, equilateral equal, all the sides are the same. And all the angles, therefore, are also the same. Now, here's a quick comment that I'm going to make, which is key information. And so, with an equilateral, okay, or with a triangle, better said, the degrees, how much do they add up to? A triangle will always add up to 180 degrees. And so in an equilateral triangle, because you have 3 different angles, right, 1, 2, 3, you can take that 180, divide by 3, and find out that in an equilateral triangle, all the angles are 60 degrees. So all angles are 60 degrees. And last but not least, the scalene is just this weird kind of thing which has 3 different sides and therefore has 3 different angles. Okay, so the scalene is just all over the place. Okay, for today, for this exercise, we're focusing on the equilateral triangle, and the key information here is that all angles equal 60 degrees because all angles are the same. So you do 180 divided by 3, you get that 60. Okay. On the other hand, we need to find, that being said, right, we now need to focus on finding the rate at which the area of the triangle is increasing. See? Now there's a lot of moving parts here, quite literally. On the one hand, this imaginary triangle that we have has side lengths x centimeters. So let's go ahead and draw that now. So this equilateral triangle of the exercise has a bunch of sides with x. See? And you also know that all of these are 60. All right, so there is my equilateral triangle. Now this equilateral triangle is increasing its sides at a rate of 4 centimeters per second, right? And so having this in mind, you need to find the rate at which the area of the triangle is increasing. Which makes sense, because if 1 second your triangle is this big and the next second it's this big, then the area increased. And so the question of this exercise is, okay, at which rate is the area increasing, especially when the side lengths are 5 square root 3. Okay, that's the question it's trying to ask. First of all, the area is going to get bigger, of course, and at which rate is it getting bigger? Exactly at 5 square root 3 for the side lengths. See? So that is a little bit the context of the problem. Let's go ahead and try to make an area formula. And so if you go ahead and try to make an area formula with the OG one, right? Well, there's two different area formulas that we can use. So you can use the classic, which is base times height divided by 2. And being an equilateral triangle, you can probably figure that out in terms of x. Or you can also go ahead and use the sine sort of or trigonometry version of the area of a triangle, which is in your formula booklet and goes like this. 1/2 times a times b times sine c. Now, all this is really saying, or asking for, better said, is that for an area of a triangle, all you need, okay, is some angle c and the sides a and b that are next to it, okay? So you can get the area of a triangle if you have these dimensions, this guy here, and this angle there, see? You can also get the area of a triangle if you have this side here, and that angle there. And you can also get the area of a triangle if you have this side here, and that angle there. So all I'm really saying is like, okay, for the sine area trigonometry thingamajiggy function formula, okay, for this guy here, all you need is one angle and the sides next to it. And do I have an angle and the sides next to it? Heck yeah, I do. I know that all the angles are 60 degrees. And so following the formula on the right, you can do it with the one on the left, but I'm going to do it with the one on the right. Following this formula, you can end up with 1/2 times, for example, we'll be using these, see? So A times B, times B, right? Times sine C, the one in the middle, so sine 60, right? And so this is my current area formula for this equilateral triangle. You have 1/2 x squared times sine 60. Now, no one likes how sine 60 looks like because we don't have a calculator. For paper 1, we don't. And so you want to find a way, right? You want to find a way to put that sine 60 in other terms, right? So you can be thinking radians, this or that, etc. Eventually, you should be remembering from your unit circle, see? Eventually, you will remember from your unit circle, and this is the kind of thing you have to learn. From your unit circle, you have the 60 degrees right there, okay? And here you have a point which goes, I think it was 1/2 comma square root 3 divided by 2. And so sine, let's remember that sine is so, right? And so that means that sine is opposite over hypotenuse. Now in the unit circle, all your hypotenuse are equal to 1 because the radius equals 1 in all of these, see? And so all you're left with for sine 60 is just focusing on the opposite. The opposite, take a moment and notice that the opposite is, right? The opposite is your y value, okay? So the y value when sine is 60 is square root 3 divided by 2. So all that really was a quick explanation that the area is actually 1/2 x squared, x squared times square root 3 divided by 2, all right? And now is when the exercise gets really juicy. Okay, so now is when we do the big sort of leap and to try to find the rate at which the area of the triangle is increasing, see? And so first, let me do a quick explanation of what derivatives are, how they work. like a general sort of intuition, see? So if you have a normal, just like a normal function, see, imagine you have a function that goes like a parabola, that goes like this, see? If you haven't done anything to this parabola, okay, if you haven't done anything to this parabola, then that means that plugging in x will get you a value for y, see? So for example, I don't know, if you plug in x of 1, you get a y of 2, you plug in x of 3, you get a y of 9. All this is giving you is a bunch of different points. This gives you the point 1, 2. This gives you the point 3, 9, right? So here's 1, 2, here's 3, 9. I'm just making up the information, but the point is, if you have not done any derivative yet, plugging in an x gets you a value for y, see? But the moment that you have the derivative, see? So this is the original, see? Original, unchanged, blah, blah. The moment you have the derivative, it's a little bit different. Because now, if you plug in an x, you don't get a y, you get a slope. Or better said, your y value turns into a slope. So for example, if you plug in an x of 1, maybe my slope would be like, I don't know, 1 as well, see? So that means that an x of 1, okay, my slope is approximately 1, see? For example, an x of, I don't know, 2, see, might give me a slope of 0.5, because at an x of 2, it's a little bit more flat, right? And so you end up with a slope that is closer to 0, see? So point is, all I'm really trying to tell you is that every time you do the derivative, you are now looking at slope, see? And slope, we also associate it to rate of change. And so anytime you do the derivative of something, you're really finding the rate of change of whatever that is. Okay, so the derivative helps identify the rate of change of whatever you're looking for, see? And so over here, it's super convenient because, oh, look at that. You need to find the rate. Well, isn't that just nice, right? And so from here, your formula for area, you can, clean it up a little. So for example, combine this 1/2 with this term over here. Your formula for area ends up being as x squared times square root 3 divided by 4, because of 1/2 times the 2 on the bottom, see? And so from here, if you want to find the rate at which the area of the triangle is increasing, all you really have to do is just find the derivative, see? And that helps you find the rate of change as I mentioned earlier, and you're pretty much good to go. However, there is one small tiny detail that we have to go over, and it's not exactly exciting, but it is worth knowing, see? Basically IB math. Just kidding. Point is, here, you're handling a special type of unit. Here you have an increasing rate, 4 centimeters per second. And so technically your area of the triangle is depending on 2 things. So the rate, this is the thing, so area of triangle is depending on 2 things. On the one hand, it depends on the fact that side increases by 4 centimeters per second. So that is the one thing that the area of the triangle depends on, that the side increases by 4 centimeters per second. But it also depends, obviously, by the current side length. And so from here, if you go ahead and do the derivative and plug in for x, all you're really doing is applying the current side length, see? And so let me first show the common mistake, which is actually how I was facing it earlier until I realized how to actually do it. If you do the derivative, you end up with 2x square root 3 divided by 4, and then you go ahead and plug in x with the side length, right? Because x is side length, and so you plug in x as 5 square root 3, and you find that the area has to be 2 times 5 square root 3 times square root 3 divided by 4, right? And this seems like the right play. It's probably what a lot of people do, including myself initially, until I took a closer look at it and realized, careful, the area of the triangle depends on 2 things. It depends on the side length increasing 4 centimeters per second and the current side length. And so the approach I just did in orange is only applying point number 2. It's only taking into consideration the current side length. And so the weird unit I was talking about is time. You have to consider time. This first one up here is time, right? It's increasing by 4 centimeters each second. You have to consider that, difference in time, see? And so technically from over here, you get a little bit fancy you're not just doing the derivative with respect to x, you are doing the derivative of your area in respect to time. And compound. This is the big step and big concept you need to grasp. So the rate at which the area of the triangle changes not only depends by the current side length, but it also depends of the side increasing by 4 centimeters each second. And so technically from here, what you need to do, like this is just very sort of like fancy math writing, but I think intuitively you're gonna get it. And so on the one hand, you need to do the derivative, right, of this whole thing in respects to time, right? And so if you go ahead and do the derivative of this in respects to time, all you really end up with, I know that when it says in respects to time, it's kind of whack, but all you really end up with is the same derivative that I showed earlier. See? And so really what you end up with is the 2x square root 3 divided by 4. See? That's what you end up with. But because you're doing the derivative in respects to time, you have to acknowledge, x, my side length, is increasing by 4 each second. And so you also have to multiply this. And yes, you can big brain and just do like times 4 and bada bing bada boom, but really, like the fancy math language is saying that, x also depends, right? X also depends on time, see? And so here it's a little bit of a chain rule sort of thing going on, which on the one hand is, okay, so you need to find how the area changes in respect to time. So you do the derivative of x, or your area, right? Derivative of your area sort of like normally, quote unquote. But then you have to acknowledge, x itself depends on time because x is the side length, and the side length is increasing by 4 each second. So you also need to put this term right there, see? So that is the big brain play you sort of have to do. Now, how much is x increasing per second per time, right? How much is it increasing? It's increasing 4. So technically you can plug in 4 right there. And also, what is x? Well, x is the side length, right? And they tell us to find the rate at which the area of the triangle is changing when the side length is 5 square root 3. So this is what you plug in for 5 square root 3 right here. See? So you go ahead and do all of that. You end up with 2 times 5 square root 3 times square root 3 divided by 4 times 4. See? So this looks long, this looks nasty, but go piece by piece. The hard part is over. All you really need to acknowledge was this thing right here. The area of the triangle depends on two things: the side length increasing by 4 each second and your current side length. So once you do that and you do the chain rule appropriately, you just gotta solve this basically. See, so this goes away with this, and you can end up with 2 times 5 times 3, because the square root 3 combines with the other square root 3, so basically you end up with this. This times this is going to be the same as this, is going to be the same as this, okay? So 2 times 5 times 3 is going to give you, well, this is 10, so 10 times 3, 30. So really, the rate at which the area of the triangle is increasing when the side lengths are blah, 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 or that amount, are 30 centimeters per second, okay? So that is, for number 6, the math is not too hard, but the intuition is wild. Okay, the intuition, I'll be honest, is wild. It's hard to grasp. And the main thing I would focus you to realize, okay, or to study more deeply, is that this is a derivative in respects to time, all right? And so notice, whenever you have the derivative in respects to time, you gotta put this extra sort of term at the end, see? On the one hand, the area of the triangle, this is the thing. Let me do it like very colored, see? So on the one hand, for finding how the current side length affects, I'm putting it in pink, which is this whole thing here, see? And for the side length increasing by 5, which I'm putting in, I don't know, blue, see? It's this guy here, right? And so once you realize that and write it down accordingly, it all just sort of flows a lot more than what you think, see? So be careful, keep that in mind. Derivatives respects to time will always be done this way, see? The other way you can try to understand it is that right here, there was a chain rule, see? Because yes, you did the derivative in respects to time, but not yet like in respects to x. So this is in respects to time, then you're gonna do it in respects to x, because x depends on time as well, because of this first line over here. See? So guys, I know it's kind of confusing. I explained it in as many ways as I could. That is for number 6, and I hope it helped. Alright, you guys, for number 7, it's pretty tough, I'm not gonna lie, but there is a very friendly sort of procedure associated to it. See? I feel like this is the kind of exercise that you have to know a lot of different things about it, but once you internalize it, it's actually pretty straightforward. So let's go piece by piece. On the one hand, they tell us to consider that this function equaling blah blah blah, this nasty thing over here, we have that z, okay, that symbol and the big C. So what this is telling you is that C pertains or is part of this subset of numbers that are complex. Okay, so all your z variables are part of complex numbers, and complex numbers, you guys, is the same as if we were be talking about imaginary numbers. Okay, and so all your values of z are your imaginary parts of your polynomial. On the other hand, you know that m pertains to all real values, which are da, 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 which are positive. So there's a small detail that might be very useful down the road. Okay, so basically your values for z are the imaginary part of your polynomial, and your values for m are the real part of your polynomial. And with that information, they tell us, given, okay, that's kind of huge. So given that z minus 3i is a factor, that is another big word, of pz, find the roots, that's another huge word, of pz equaling 0. So guys, this is basically an exercise of finding the roots, okay? In that sense, the procedure is fairly straightforward, and it just gets kind of wild because we do have imaginary numbers going around. Now let's go piece by piece and really understand why I highlighted the words that I highlighted. So given that this is a factor, it's going to help me a lot to find the roots, okay? Now let's really get why. So on the one hand, what is a factor? Well, when you were factoring before entering the IB, before entering HL, when you were a little bit more innocent, you would factor stuff like, I don't know, x squared plus 4x plus 3, okay? And eventually you would have found out that the factors of 3, or really like 1 times 3, right, are 1 and 3. And so that means that 1 plus 3 gives 4, blah, 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 etc. Yeah, you would end up rewriting this, right, rewriting this quadratic as x plus 1 times x plus 3. And you would solve this by equaling it to 0 and saying, okay, so from here, I can say that because these two things are multiplying and this equals 0, either this on the left is 0 or this on the right is 0, or both. Because if you have a times b equals 0, you know for a fact that either a equals 0 or b equals 0. There's no other way for two numbers multiplying to equal 0. One of them gotta be 0, okay? And so with that in mind, technically the roots from here, you would say that, okay, so basically either x plus 1 equals 0 or x plus 3 equals 0, right? And so from there you have that x equals -1 or x equals -3. So this is fairly straightforward. I'm sure you've seen this. And why did I highlight the word factor? Because the factor ring that I just did is this guy along with, whoops, sorry, along with this guy. Those are your two factors, okay? And so basically they're handing you, like to your face, some of the roots. And so if they tell you, okay, if they tell you that one of the factors in this exercise is z minus 3i, then you can immediately assume, so this is part of the parentheses, and sure, there's a couple other parentheses going around, okay? But you know that one of them is these, okay, z minus 3i, which is kind of like saying, like, you know that one of them is x plus 1, okay? And so from here, you can immediately go ahead and say, okay, so this has to equal 0, which is the same process I did here in orange, right? And basically, well, technically, this guy here, see? It's the same process that you're doing right there. So z minus 3i equals 0. So you can immediately just say that z has to equal 3i. So guys, this is literally one of your roots, okay? And your other roots, and here's a big sort of trust me sort of energy. I'll try to explain it in a second, but really it's a trust me sort of energy. So if you have complex numbers and one of your factors, okay, one of your parentheses is z minus 3i, then the complex, the, sorry, I got tricked up. Then conjugate, the complex conjugate is also a root, is also a root, okay? Massive information, you should be writing that down, okay? And so if one of the factors is z minus 3i, then the complex conjugate, because there is a z in there, there is a complex number going around, right? The complex conjugate is also a root. So if one of the roots was this guy here, then your other root is going to be z plus 3i equals 0. And so z has to equal negative 3i. This is your other root. Okay, so you can literally think about it this way. Your root 1 was this guy here. Your root 2 was that guy down there. Okay? Now, what the heck is a complex conjugate? How does that work? What is going on? See? So on the one hand, you have your formula booklet. Okay? And the formula booklet is very important that you get used to it because the day of the test, you will have 2 years of experience of this thing called IB. You will have probably 2 hours of sleep, a lot of study time done in your past, and a whole lot of energy for you to do well. Okay? And you will also have a pen and pencil, an eraser, maybe the graphing calculator depending on the test. And more importantly, and this is my point, the formula booklet. The formula booklet is a tool you can take in the day of the test, get familiar with it, know what's in it. A lot of it is useful and a lot of it is not, okay? And so for today's exercise, or for this exercise, better said, there is something very, very important that we have to use, okay? So down the line, we will be using this guy here, okay? Not yet, but this guy here. And for now, I wanted to talk a little bit about what is this, see? So here they tell us that complex numbers, okay, are z equals a plus bi. And all this is really telling you is that a complex number has a real part plus the imaginary part. Okay, this is a t. Plus the imaginary part, right? So the real part is the A, and the imaginary part is the BI. Okay? And so if you were to sort of graph this, usually imaginary numbers get graphed as like vectors and stuff like that. See? So if you were to graph this, on the one hand you would have your real part, and on the other hand you would have the complex or the imaginary number part. See? And so basically you would have, say, here you have A, and over there you have your BI. And technically, okay, so this is like the OG, right? You can take this as the OG. And the complex conjugate, just so that we see it more visually, the complex conjugate, okay, is like, it's sort of like the mirror. It's like in the same sort of direction, but mirrored, right? And over here, you would have minus BI, okay? And so that is why if the OG is Z equals A plus BI, then the complex conjugate is pretty much the same thing, just that you have Z equals A minus BI. Okay, so the complex conjugate, you can think about it or memorize it or whatever you want, okay, as like the imaginary, okay, with times -1, okay? So if the OG was A plus BI, then the complex conjugate is A minus BI. See? And if you ever face an exercise where the original that they gave you was A minus BI, well, the complex conjugate is A plus BI, of course, right? Because you're going to be doing minus BI times -1, which gives you that positive BI that I mentioned earlier. All right, whatever. I don't want to go too deep into that. This is more of a visual aspect of what the complex conjugate is. Just recall that the complex conjugate is a -1 to the imaginary part of it, and it's also a root. Okay, that is the biggest sort of thing I really, really need you to understand it's also a root. And so over here, I already found two roots. Okay. Now you might be thinking, but dude, how many other roots are there? Like, this is crazy. Like, what's going on? And there's actually a fairly easy way to identify in polynomials what a root is. Okay. And so polynomials by itself is anything that is like, for example, this x squared. Actually, let me do it like this. So you have ax squared plus bx plus c. This is a quadratic. See, but it's a polynomial. It's a second degree polynomial. See, so it's second degree because you have x squared. If you happen to have something that goes ax cubed plus bx squared plus cx plus d, surprise, this is a third degree polynomial because you have a 3 up here. And the way to tell how many solutions, how many solutions you have is by identifying the polynomial grade that you have. All right. Now this is very fancy math definition. What I actually want you to remember or recall or write down is that biggest exponent equals amount of solutions. And so in this case, for example, we have an x to the power of 3. That means you have 3 roots, 3 solutions. Here you have an x squared. That means you have 2 solutions, right? Now we know because of the discriminant, some of them are imaginary, some of them are not, etc. Blah, blah, blah. Still, 2 solutions, 3 solutions, etc. Right? And so over here, what's your biggest exponent? Your biggest exponent is a 3. So, you need to find, okay, you need to find 3 roots. Right now I found 2, all right? So again, this is a very sort of context problem. I need to explain everything piece by piece. And now the next thing I have to explain is, okay, so you found 2 roots. Which one is my third? How can I do it? Blah, blah, blah. And this is when it's very useful to have tools in mind, okay? Technically, there's 2 approaches, all right? One of the approaches, which I'm not going to do, but I will show you the first step, is identifying that, okay, so if one of my factors is z minus 3i, and my other factor is z plus 3i, because this guy on the internet told me that it's a complex conjugate, then that means I have a third root going around, okay? That means I have a third root going around, and once I identify that one, right, and I can compare it to my original function, right, maybe I can find the last sort of root, okay? So one of the methods is literally just trying to like distribute backwards or figure out by intuition like what the last root should be, or factor out piece by piece from the original one until you end up with what the last parentheses should be. Okay, so that is one of the methods. I don't really want to get into it because I think the other method is a little more straightforward, but I do want to give you the tool in case you've seen it in class or whatever, etc. See? Anyways, the method that I'm going to show you has to do with the following. In your formula booklet, which I did mention that it's very important to get familiar with it, to learn it, etc., I gave you the foreshadowing, ooh, fancy word, foreshadowing, that this was going to be very useful. And so this over here is like a sort of math law, okay? And this is telling you that the sum and product of the roots of polynomial equations, okay, polynomial equations being like these guys here, see? Polynomial equations of the form blah, right? So basically that your polynomial, all this is really saying is that your polynomial equals 0. When your this is the thing, when your polynomial equals 0, the sum is this of the roots. The sum of roots is that, and the product of roots is that. So, now we're getting somewhere. And so, well, what is this actually saying? Because here there is an A, there's an N. What is N? What is A? What the heck? Like, what is going on? See? First, let's go with intuition. So as I said, when your polynomial equals 0, there is a formula they can use for the sum of roots. and also for the product of roots, which can be very, very useful in order to solve it. See? Now, piece by piece, what is n, what is r, what is happening? So, this n, which is the same as that n over there, and this n here, and all these other n's, okay? This n is your biggest exponent. And the a, which is appearing here, which is also appearing there, notice that a right here, it's next to what thing? It's next to an x. Ah, so the a is the constant. All right, now this is getting interesting, right? Because basically, what this is telling me, and notice, here you have n, so this is gonna be, you can basically think about it as like the constant next to the biggest exponent. While this one over there is a very similar idea, but it's the constant before the biggest exponent. All right? So basically, and if I actually apply that over here in this exercise there, see? So notice, when your polynomial equals 0, right, you have an equation that is basically telling you that the sum of your roots is going to equal the constant before the biggest exponent, which is what is on my numerator, divided by the constant next to the biggest exponent. Okay, so the sum of roots, we really need to understand this formula before we apply it to the big exercise. See, so using this simpler example here, the sum of roots equals negative a n minus 1. So this is the constant with like right before the one with the biggest exponent, divided by the constant next to the biggest exponent. See? So the sum of roots equals those two constants. See? So if I apply that here, well, the sum of my roots, we did say that the roots were negative 1 plus negative 3, right? This is negative 1, this is negative 3, equaling this one is, actually, let's do it the other way around. So first, the biggest exponent, right? So the constant next to the biggest exponent, so it's going to be negative because of this negative here, see? So the constant of the biggest exponent, well, what's my biggest exponent? It is the x squared. So next to the x squared, which is my biggest exponent, you have a 1. So on the bottom, you put a 1. And then right after the x squared, you have an x to the power of 1. So over here, you can put 4. So, so the sum of roots is going to be negative 1 minus 3, right? Equaling negative 4 divided by 1. So negative 4 equals negative 4. Boom. So that formula actually works. Wow. The formula booklet can be really useful. Surprise! It's going to save you. It really will. And so this right here is massive, you guys. It is an incredible tool that you can apply and basically really focus on the example I gave you. Because it's very easy to get mixed up on the an minus 1, an, and all that stuff, and etc. Dude, all this is telling you is that sum of roots equals negative um, um, constant before biggest exponent divided, right, by the constant of the biggest exponent, right? And so let's just review that one more time. This an minus 1 was the constant before the biggest exponent, so there would be, well, before the biggest exponent here is the 4, right? And the constant of the biggest exponent was 1. So that is why you had 4 divided by 1. You have a negative because that's what the, you know, the formula brings to you, right? And the sum of the roots is just going to be the negative 1 plus the negative 3. All right, so this formula is huge. I had to explain it piece by piece because I don't just want to throw it at you, okay? This is how it works. This is how you apply it. So now let's apply it to this super hard exercise, see? So if I try to apply it now, on the one hand, you know that you have 3 roots because you have z to the power of 3. And if you try to apply it now, well, you have the root, like the root of the first root plus the second root plus the third root, right, has to equal the second to last constant, right, and the biggest constant. And so the biggest constant here is just going to be -1. So you have negative divided by -1, and then the constant next to it is actually this, 36 divided by m. And if you go ahead and plug in the roots that you have, well, you can plug in the first one, which we said was 3i. You can plug in the second one, which we said was -3i, right? And then this third root, well, you still don't have it, right? But if you go ahead and try to solve this now, well, this goes away with this. You have your third root that you're going to discover soon. And here on the right side, you end up with negative 36 divided by m divided by -1. Which, first of all, looks kind of nasty, but second of all, you can't solve it yet because you don't have m. And so this is the next big step that we have to go through. Well, what is m? How can I find m? What can I do? How can I get m alone? And so the big step you have to do now is that in order to find m, what you can do, right, is that because you know, for example, that z equals 3i, that 3i is indeed a root, then that means that you can plug in 3i into your equation, and this must equal 0. You can also do it with the one on the bottom, right? You can also say that -3i has to equal 0. They're both going to work. So both of these are an approach in order to find m. I'm going to choose the one up top because I want to, but they both work, okay? Now, why would this help you find m? Because if you plug that in to your equation or formula or whatever, actually first let me write it down here. So it's your OG is 4m minus mz plus 36 divided by mz times z squared minus z cubed. So if you go ahead and plug in 3i here, first of all, it's going to look really nasty. And so what you're going to end up with is with 4m minus 3im plus 36 divided by m times 3i squared minus 3i cubed. And so yes, this looks pretty terrifying, but there is something interesting that just happened. So in the original one, which I am now putting in pink, so in the original one, how many variables did you have? Technically, you had the variable m and you had the variable z. So you had 2 variables, which is annoying. But now that you plugged in 3i, how many variables do you have? You actually only have m. And I know some of you might already be thinking, dude, what? What are you saying? I don't believe you. I don't believe you because there's an I going around. And I will say, yes, there is an I going around, but careful. I has a value associated to it. And so I is an imaginary number. That is why we're talking about complex numbers in the first place. And so I, ladies and gentlemen, is basically, or is better said, square root of -1. And so the reason imaginary numbers exist in the first place is because if you ever, for example, say you have square root of 4, right? You're going to tell me, the solution of square root of 4 has to be plus or minus 2. Because you can do 2 times 2, and that gives you 4. Or you can do -2 times -2, and this also gives you 4. But if I go ahead and ask you, okay, now try to solve -4, square root -4, suddenly you can't answer 2 because, well, 2 times 2 gives +4, and -2 times -2 gives +4 again, right? And so there is no way to end up with a negative because you either multiply two positives or multiply two negatives. You never end up with a negative. And so the way to solve this would actually be 2i, right? And so that is why the I exists in the first place. It helps you solve. This is the thing. Imaginary numbers. This is just like a useful fact. So imaginary numbers help you solve square roots that are negative. All right, that is like the big deal. That is why they were invented in the first place. Imaginary numbers help you solve square roots that are negative. See? So that is why they exist, and I equals square root of -1. Now, from there, because you don't have a calculator, you do have to try to manage these i's in the best way possible. See? And so from here, some of these i's, you can actually solve them like straight away, right? So on the one hand, because I equals square root of -1, then I squared has to be square root of -1 times square root of -1. So I squared has to equal, look at that, -1. I cubed is really just going to be negative I. And I to the power of 4 is going to be +1. See? So these are things that are definitely worth keeping in mind. Everything that I'm putting in a box right now is very useful information. If you don't trust me, I get it. I'm a person on the internet. You shouldn't trust people on the internet. But this is a math video, so put your guard down. So if you put I into your calculator, I know this exercise doesn't allow calculators. I'm just showing you how I works. So I by itself just gives you I because whatever. See? I squared gives you that -1 I was talking about. I cubed gives you that negative I was talking about. And I to the power of 4 gives you that 1. And you will actually notice, and this is just good to know, that this pattern repeats if you keep on going, right? And so to the power of 6 is the same as if it was to the power of 2. To the power of 7 is the same as if it was to the power of 3 because it's a pattern. Well, that looks kind of whack, but point is, it's going to start repeating. See? Here, the calculator just kind of loses it, but really I to the power of 8 is the same as I to the power of 4. That's what I was really trying to show you. I did not think the calculator would go kind of crazy there. Whatever, okay? I don't want to stray too much from the point that I'm already trying to make. So, enough blah blah. Point is, from here, you can actually solve I squared immediately, see? And so from here, you can go ahead and simplify what you can. On the one hand, you end up with 4m minus 3im plus 36 divided by m times, here this squared affects the 3 and affects the I. So you end up with 9i squared. Interesting. And over here, this 3 affects both. So you end up with minus. Okay, you end up with minus. 3 times 3 is 9 times 3 is 27. So minus 27 I cubed. All right. So, okay. Now it looks like we're getting somewhere, aren't we? So, from here, the context I mentioned a million years ago, we did say that the imaginary numbers that we deal with have a real part and an imaginary part. And so because we we did say that this whole thing equals 0, you have an equal 0 here, right? Then that means for this to be true, the real part has to equal 0 and the imaginary part also has to equal 0. And so if you divide it between imaginary part and real part, we'll first solve the I squared, right? And so the I squared is a real number, right? We did say that I squared was -1. So from here, you can end up with 4m minus 3im plus 36 times 9, which if you take your time and do it, I know it's without a calculator, so you're going to have to do it yourself, but 36 times 9, I think was 324. There it is. So 324, so you end up with plus 324 times I squared divided by m. Now I squared we did say was -1, so really over here it just turns into minus 324, right? And this last number ends up as 27I cubed. Now, as I said, the real part has to equal 0, the imaginary part has to equal 0, so the real part is going to be, 4m minus 324 divided by m. This has to equal 0. And on the other hand, the imaginary part has to be 3im minus 27I cubed has to equal 0. So, now that I have the real part and the imaginary part next to each other, to solve the real part, which is a lot more straightforward because I only have m's going around. On the other hand, I still have i's going around, which are annoying, right? So I and m. For solving the real part, you gotta get m alone. Now, because you have m on a denominator, I strongly suggest that you just multiply everything by m. So if you multiply everything by m, you end up with 4m, right? So 4m squared minus 324 equals 0. So getting m alone, you do plus 324 plus 324, you end up with 4m squared equals 324. Divide by 4, divide by 4. M squared equals 81. You can trust me on that. You can double check later. So from here, you can now do square roots in order to get m alone. So m has to equal plus or minus 9. Now, is it positive 9? Is it negative 9? Technically, you can check by plugging it into the imaginary part, and whatever makes it make sense, you're good to go. But what I'd like to remember you, or remind you, better not remember you, what I'd like to remind you is that up here, way earlier, you did say that m pertains to the set of real numbers which are positive. And so, bada bim, bada boom, you can immediately say that m has to equal 9. So, guys, that was a very long sort of approach. I think this video is a little bit long, but it does go over pretty much everything you need to know for imaginary numbers. So, I think it has a good side. See? Anyways, all of that thing was just to find m, which we just did. So m equals 9. We concluded that m equals positive 9 because they did tell us that m pertains to the real numbers which are positive. Okay? If we weren't sure whether it was positive or negative, you would plug it into the imaginary numbers set here, and whatever makes it equal 0 is, the value of m that we will use. Anyways, so now that you have your value of m, we can come back to this part right there. So, this is what we were going for in the first place. We were trying to do the sum of roots, and it almost worked, just that we had an m going around. See? And so now that you can plug in now that you can plug in 9 for m, we can solve for the last root and be done with this very exciting exercise. And so your last root is going to be negative 36 divided by 9 divided by negative 1. Now, on the one hand, because you have a divided by negative 1, really what that ends up happening is that you end up with a negative times a negative, so this guy times this guy, and it ends up being that the whole thing is positive. See? So you end up with positive 36 divided by 9. So your last root has to be 36 divided by 9, which is 4. And so, boom, look at that. So your first root, just to be very organized, is 3i. Your second root is negative 3i because of the complex conjugate, and your last root has to equal 4. So ladies and gentlemen, that is how you solve number 7. It's pretty wild. And let me just make a quick recap of the approach we did just so that we really understand the process, because that is the main idea, right? Once you internalize all these different methods and processes that you can do, then that is an additional tool that you can use the day of the test. So basically what happened is that they gave us a factor. See? So because they gave us a factor, that immediately gives you two solutions, right? You get one solution just by plugging your factor equal to 0, which is the same stuff that you've always done, right? So you take that factor and you equal it to 0. That gives you one root. The other root arises because of the complex conjugate. The complex conjugate is also a root always. Okay, so you go ahead and do the complex conjugate. Basically, you go from negative 3i to a positive 3i. That is the only change you need to do. You only affect the imaginary part of your number. So once you do that, you got the other root, right? Now for the last root, and first of all, you know there's a last root because you have z to the power of 3. And so if it's to the power of 3, you have 3 roots. If it was to the power of 4, you have 4 roots. If it's to the power of 8, you have 8 roots. Because the biggest exponent tells you the amount of solutions. Now, you're thinking solutions, you're thinking roots, you're thinking factors, all these different things. And it should come to mind once you study enough with it, with the formula booklet, that there is a formula for a polynomial for the sum of roots. And so basically, all this stuff that is written here is just the fanciest way possible to tell you, yo, you have a formula that when your polynomial equals 0, you can basically take all the roots, sum them up. So the sum of roots is going to equal two constants, right? The constant of the biggest exponent on the bottom and the constant of the next biggest exponent on top. See? And I did a quick example showing it over here. So the biggest exponent was x squared, so you put 1 on the bottom, and the next biggest exponent is x to the power of 1, so you put the 4 on top. See? And so you take the sum of roots, which you said was -1 and -3, and we showed that the formula worked, right? And so because the formula worked and we gave this very intuitive example, well, now you got to apply it for the polynomial with imaginary numbers at the HL level, which is absolutely crazy, but you follow the procedure, you trust the procedure, you trust this guy on the internet, not all of them, just this math guy talking about stuff. And boom, you found out this equation, and the only thing you were missing was m. And so how do you find m? Well, you plug in 3i into your formula, right? You plug in 3i into your formula, and we passed from having the variables of m and z to having only the variables of m, right? I is not a variable because we also talked about how I is a number. See? You found m, you completed the sort of like plug-in formula thingy majingy, and everything worked out nice and dandy. So, you guys, number 7 is pretty crazy. This video is probably pretty long as well, but I'm sure it helped out at least one of you out there. So this one's for you. I hope it helped, and I'll see you around. Alright, you guys, so for number 8, it's a pretty creative problem, and not that hard once you grasp the concepts, all right, but it's definitely more on the creative end. So for number 8, it is worth 7 marks, and they tell us that part of the function f is shown in the following diagram. So this whole thing that I have drawn is function f, the graph of y equals f of x, right? So this whole thing is basically f of x. They tell us that it has a y-intercept at 0, 3, which is right there, of course, and then x-intercept, okay, an x-intercept at a, 0, so at some x, 0, and the horizontal asymptote, I'll put this in a different color, at y equals -2. Now, you guys, an asymptote, just a quick review, an asymptote is basically a value that your function never touches. Note, it does get very close to it, but it will also never touch. So it gets very close, but it never touches. And so a horizontal asymptote, okay, that means you are drawing a horizontal line. So horizontal asymptote is basically just horizontal line, and that is why we also mark it with a y equals. And I know that might be a little bit weird. You might be thinking, yo, wouldn't the horizontal thing be associated to x values because x is my horizontal line? And I say, yes, you're right. But in this case, if you want to draw, this is the thing. If you want to draw our horizontal line, we'll take a moment and look at it. So this horizontal line of -2 right here, this y equals -2, which is the one they're telling us here. So this horizontal line, take a moment to think about it. For example, this point, this point, this point. And so this point here is around, well, we actually don't know the dimensions of our x, but I'm just going to make up that that point is -10, comma, -2. This point here is, I don't know, like -8, comma, -2. Oh, that's interesting. And this one is -6, comma, -2. So these numbers are made up because we don't know the dimensions of the x grid, but notice these 3 points have a -2 for y. And so that is why for expressing a horizontal line, you would say something like y equals -2. Okay? That is why on decimals, if you put y equals -2, it looks like that. And if you put, for example, x equals 4, it looks like the one that's purple. This is because all your x values are 4, while for the horizontal one, okay, all your y values are -2. And so it's just a quick recap, you guys. Horizontal asymptote, y equals something because one y is always going to be the same. While for the vertical asymptote, x equals something and that x will always be the same. Okay, in this example, x equals 4 looks like that. Your value of x equals 4 does not change, your y does. So, enough blah blah. let's now get into more of like the core of the exercise. And so for part A, what they tell us is something a little bit weird. They tell us to consider the function g of x equals all those symbols, which I will go over in a second, but it's a bunch of symbols, it's a little bit weird, and that on the following grid, we need to sketch the graph, okay? And now I know some of you, or at least it used to happen to me, like, sketch the graph, easy peasy, easy points. But careful, sketching this graph is worth 4 points. And so for sketching, it is very important, you guys, that you consider key points. Key points. That you consider, for example, asymptotes, okay? That you consider intercepts, okay? And that you consider just like how it looks like. Okay, usually if you consider these 4 things, you will get those 4 points, okay? And I'm just going to show you right away in the mark scheme because I think it's important to know how they like evaluate these sorts of exercises. For example, this one up here is literally the one I said about like it looks like correct. See? This one here is that asymptotic behavior is making reference to, you know, you get the right asymptote. This one over here is basically, well, you put a maximum at 0,3, so that would be definitely an intercept, right? Well, actually, more than an intercept, it's just coincidence, but it's more of a key point, right? You're putting the maximum. And over here, you have, again, asymptotes, and, oh, here, actually, sorry. Here you have x-intercepts, see? So, although it's worth 4 points, don't do the common mistake of just drawing what it looks like. Make sure you label your graph. Okay, this is going to be your favorite word for this exercise. You want to label your graph. And actually, it tells you to label any axis, any intercepts, blah, 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 blah. See? So, just a kind of reminder that whenever you see sketch, yes, it's relatively easy points, but do it correctly. Label everything. Put the intercepts, put the key points, put the asymptotes. Make sure it looks like how it's supposed to look like. Okay, nailing how it looks like is only one of the many points you can get. So, how the heck does this look like? Well, our function is, and let me write it up here. Our function is g of x. This is what we need to sketch. So g of x, and they tell us that we need to do the absolute value of the absolute values of x, which is kind of crazy. See, so first things first, what is an absolute value? So an absolute value, okay, so absolute value, and I'll be putting that thing, see, so like it's basically like a wall, okay, or a straight parentheses. Think about it however you want. See, but an absolute value is those straight lines that I have in pink down here. See, so those straight lines, what they tell you is that you're dealing with absolute values. Now, the absolute value, what's the cool thing about it? Absolute values, okay, which look like that, make whatever is inside positive. Okay, so if you ever have, for example, the absolute value of -4, your answer is just going to be 4. If you have the absolute value of -3, your answer is going to be 3. If you ever have the absolute value of 2, it's going to stay as 2. Okay, so stick to the intuition that absolute values makes whatever is inside positive. Makes whatever is inside positive. And so, having that in mind, you might be thinking like, oh, okay, so if I need to make everything positive, all that's really gonna change in my graph, and you would be partially correct, all that's gonna really change on my graph is noticing, okay, so here I have negative values, so all I really need to do is sort of like make it jump back up, see? And you would say, okay, here's my sketch. And you would be almost correct, okay? What you graphed just now, okay, what you graphed just now, which is in green, all right, so forgetting this thing on the bottom, what you graphed just now is really this. And so careful, there's a small difference that I need to go over. Technically, there's 3 variations, so let me explain all of them one by one, just so that we go over everything that can happen to us. So this one that's in orange is both x and y being positive. Well, this one in green, which is what I graphed actually, is only y is positive. Well, this one down here in purple is actually only x is positive. Because notice the example that I have in green, which is one guy that goes like this, so boom and then boom, you still have a bunch of x values that are negative down here, right? And so having that in mind, you guys, okay, having that in mind, what you need to do is think about the corresponding y value, okay, for orange, right? For the correct answer, you need to think about, okay, so this x of -1, for example, is really going to be an x of +1, and what is the y value of that? See? Now I know that sounds pretty much insane, so let me show it to you more visually, okay? So, because your original is, yeah, okay, I'll do it that way. So, because your original looks something like this, okay? That goes boom, 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 touches, and then keeps going down, see? Because your original looks like this, okay? And actually, let me put it in red just so we understand that this is my function. So this is your OG, right? Because you have absolute values on the outside and on the inside, that means that both your x values and y values are being affected by the absolute value. And so on the one hand, first you can consider the transition of having no negative y values. See, so if you make no negative y values, well, it has to look something like this. So if you have no negative y values, when you reach that famous a, right, when you reach that famous a, it's just gonna like sort of bounce back up. See? Now it bounces back up, having in mind the asymptote from before. See? So if here you have -2 for asymptote, over here you would have +2, right? So on the one hand, this is making your y values positive, but which would be actually considering just this, okay? Just this. But now we need to consider, you also need to affect the x values. And so if you go ahead and affect the x values, and this is the hardest part to explain, see? Technically, let's start maybe like from the middle, see? So if we start from the middle, we know that the middle has a 0, 3, right? So you know that you have 0, 3 here, right? And you know that somewhere over here you have a, 0. And you know that it goes like this. Boom, and then boom, right? Something like that. You will have an asymptote over here at 2. Okay, that is all you know for the right side, okay? For the left side, because now you're doing the absolute value of your x values, because you have an absolute value inside, technically, like this x value right here, okay, this x value right here is going to have the same y value as this x value right there. And so if the distance from here to here is, for example, 1 for your x, and from here to here is also 1 for your x, then these y values have to be the same because of the absolute value. Okay, so basically this x equals -1 is going to have the same value as the x equals +1 over here. This x equals, I don't know, negative, I'll make it up, x equals -3, right? So I don't know, maybe somewhere around there, I'll just make it up, has to have the same value for y as the x equals 3 over here, right? And so once you realize that basically the x equals -1 has the same value as the x equals +1, and the x equals -3 has the same y value as the x equals +3 because of the absolute value thing, then it's basically sort of mirrored. And so you go boom, and then boom. And so here is your sketch. And so because, as I said, the x equals negative 3 has the same y value as the x equals 3, then if this is a, then that means that this is negative a. And so now we are ready to sketch properly. See? I just really needed to go over the thing of how the absolute value is affecting, on the one hand, the y values when it's on the outside like this, and also affecting the x values when it's on the inside like that. Okay? So having that in mind, if you go ahead and sketch it now, I'll try to make it a little bit more fancy, but on the one hand, you still have a 0, 3 for y-intercept, okay? On the other hand, as we identified, you will still be following this path over here, see? So you're still going to be reaching that a. But because you can't have negative y values, this part here is really just going to go up top, right? It's just sort of going to reflect and go up top. And because you have an asymptote at negative 2, well, now that asymptote has to be up here at positive 2, okay? So it reaches a, and instead of it still going downwards, now it's simply going to go sort of upwards and have an asymptote at equals 2. See? So whatever, that's probably good enough. See? And so here, just to get full credit, I would be putting definitely a dotted line and a y equals 2. See? And now, because I identified that, because we have an absolute value on the inside, right? That means that, I don't know, this value here, if you take the distances equally, is also going to be this value here, this distance here, equaling that distance again, you have a point there. Basically, it's also mirrored on the y-axis. Okay, so the other way you can kind of think about it is that the absolute value is going to mirror, so absolute value mirrors / reflects your graph. Okay, this is another way you can sort of try to remember it, which is actually part of the mark scheme. Here it says attempt to reflect f in the x or y axis. Okay, like technically, if you cover this side and you say, okay, try to reflect it, boom, it's going to show up on the left side, right? So you can kind of imagine it that way. There's a lot of different approaches. What I really needed to explain here, though, was the concept of absolute value. And so from here, because all these points are the same, then you know that this a value is also going to be somewhere on the left right here, right? So here you know you have a negative a, okay? And so now I can sort of try to eyeball my sketch, which would be something like this. So boom, and then boom like that, again with the asymptote, see? So just to really get full credit, I will be marking this point as negative a comma 0. This a, well, it's already marked, but I'll just put it as a comma 0. Here I can put 0 comma 3. I marked my asymptote. I'm good to go. See, so this would give me the whole 4 points. And yeah, that's about it for part A. See? Part B gets a little bit more exciting. And so part B, what they ask you to do is to find the possible values of k such that g of x squared equals k has exactly 2 solutions. So notice, it's not at least 2 solutions, it's exactly 2 solutions. So, what the heck does this mean? Notice, on the one hand, you need to square your um, function. See, so we will talk a little bit about what happens if you square your function, okay? But before we square our function, before we see how the numbers change and stuff, let's really try to understand what it means by exactly 2 solutions. And so if here, we will do the exercise not with it being squared, but just thinking that g of x equals k, where 2 solutions. Okay? And so how the heck would you even answer this? So, first things first. A long time ago, at some point with math, you stopped writing, for example, y equals ax squared plus bx plus c, but instead you started writing f of x equals ax squared plus bx plus c. And so why do I tell you this? Well, I tell you this to identify that f of x is basically just your y, see? And so from here, you need to see where do you have two solutions thinking in y. Thinking in y, see? And so I know this is like maybe not the most professional way to explain it, but I think intuitively it's going to make a lot of sense. So g of x equals k, where do you have two solutions? So you're thinking in terms of y because you have literally g of x equaling k. And so if you're thinking in terms of y, okay, this k value, imagine that k equals -3, okay? If k equals -3, that means that at -3, you have a line going like that. How many solutions do you have? 0, because you're not touching your function at all. Let's imagine now that k, okay, and we're going to keep doing this until you really understand it, see? Let's imagine that now k equals -1. So if k equals -1, while you're cutting through here, are you touching your function at all? You're not. No solutions. But the moment you say, for example, I don't know, that k is whatever, like 1, see? So when k is 1, boom, boom, boom. How many times are you touching your function? Once, twice, thrice, and 4 times. So damn, here at k equals 1, you actually have 4 solutions. And so you gotta keep doing this and keep thinking, and this is the creative part that I mentioned earlier, where do you have exactly 2 solutions? And eventually, you guys, you will identify or see that you only have 2 solutions right above the horizontal asymptote. Because right above the horizontal asymptote, you can draw a bunch of lines that go like this, and all of these have only 2 solutions, unless you're crossing right at the maximum. If you cross right at the max, so right at max, it is only 1 solution. But anywhere below that, you are actually cutting through twice. For example, here you cut there and you cut there. Here you cut there and you cut there. And so clearly, above the horizontal asymptote, or in that small sort of area section, is where you have 2 solutions. See? And so for the answer of my sort of made up question, sorry for erasing all of that. Let me redraw it real quick, something like that. All right, cool. And so where does k have 2 solutions? In your unchanged, in your OG version, k has 2 solutions wherever you have that k, okay, is greater than or equal to 2, but less than 3. Okay? Now, that is for the original. See? Here they are asking for g of x and it's being squared. All right? So the same sort of exercise. On the one hand, I can immediately give you like the intuition that you just square your answers and you're good. See? So if in your original it was from 2 greater than or equal to k and less than 3, okay, you can just square your answers and you end up with 2 squared, k, 3 squared. So you're going to end up with 4 less than or equal to k, less than 9. Okay? So that is a sort of like quick trick you can use. Okay, you look at the original solution, you analyze it from there. If it's squared, you just square your answer as well. Bada bing, bada boom, it works. See? Now, that also works because of the nature of the function. Okay, it's not always going to be the case. I suggest you sort of graph and stuff like that, and etc. I think there might be special scenarios. I'm not sure if you guys see them on AAHL. So don't quote me on that. I'm not entirely sure. But at the very least, like analyzing the OG version of it can help you approach the problem properly. So on the one hand, you can look at the OG, then square everything, except for K of course, and boom, there's your answer. See? Now more intuitively, I do want you guys to see that when you square your function, what really changes, and the more I think about it, I think it is true that you can just square your answer and it's going to work every time. See, if it's squared here, it's just gonna, this is the thing, it's gonna change in proportion. See? It's like the same shape, just that it's bigger or smaller. So for example, you can draw like a cube, right? And then you draw like a bigger cube. And it's not that it's the same cube, but they are similar cubes. Okay, one of them is maybe 3 times as big. See? And so there's a bunch of relationships that come out of that, like how does the volume change? How does the area change? It's all in a nice proportion if the distances are all increasing at the same ratio. And so if it's times 3, the area changes in a very specific way. The volume changes in a very specific way. The distances change in a very specific way. See? And so all that kind of stuff, it's worth getting familiar with, especially for these types of exercises. And in this case, we're talking about a function. Okay, we're not talking about a cube, but my point is they're very similar. There are relationships that arise when you multiply all the distances by 3. See? So in this case, if you square all your values by 2, well, look at this example here. So here you have the red quadratic. See? It's a pretty standard quadratic. Look at it, enjoy it, right? If you go ahead and square it, which is the second example that I have here, see? So if you go ahead and square it, let's see what happens. Boom. So on the one hand, it's growing like a lot faster and this or that and etc. But let's really focus on when x is -1. Huh, interesting. So in the OG, when in the red one, see? When x was -1, y was 4. And in the new one that's squared, when x is -1, y is 16. And so, will you look at that? Basically, when you square a function, it's gonna grow in terms of y. Okay, it's not gonna grow in terms of x because your x values like practically stay the same. Like what really happens is that your y values get amplified. Okay, that's the big word I'm going for here. They get amplified. And so really, if you were to redraw this, all that's really going to happen, right? All that's really going to happen is that instead of having those dimensions here, you're going to have something that goes like this. Your horizontal asymptote will first of all be on 4, and your new y-intercept is not going to be 3, it's going to be 9, all right? And so if you analyze it, thinking it like this, well, it's pretty clear that after 4, after your y equals 4, right? After your y equals 4, from 4 to 9 is where you have all those double solutions. See? So here you have a double solution, here you have a double solution, here you have a double solution, but not at 9. And so that is why we write that the values of k that make it exactly 2 solutions is from 4, including 4, up until 9, but not including 9. Because 9 is right at the maximum, it touches only once. See? So you guys, I had a little bit of a monologue and blah blah at the end, just really trying to explain how the squared affects your functions, and just stick to the rule that basically it amplifies everything. See? It amplifies everything, specifically your y values. And so remember this example I just gave you here, and remember also how this one would change. So you pass from an asymptote of 2 to one of 4, and you passed from a vertical, sorry, a y-intercept of 0, 3 to 0, 9. Okay, so clearly you're just squaring the 3, you're squaring the 2. Okay, so that being said, you're here, if you square the 0, see, just in case someone's wondering, here all you would have to do, whoops, is square the 0. And so if you square the 0, nothing's actually going to change. And so if you were to like draw the other graph here, they would probably, well, technically I would have a y equals 4 like up here. Really, it would look something like this. Boom, it still touches at 0, and wham, somewhere at 9. See? Boom, and then somewhere at 4. See? And so here is like both functions plastered on top of each other. It would look something like that. All right. Again, stick to intuition. I hope you guys learned a thing or two in respects to the absolute value and in respects to amplifying and basically just squaring your function. Ladies and gentlemen, that is number 8. Not that hard, a little bit creative, but very doable. I'll see you around, and I hope it helped. All right, you guys. So number 9 has a lot of moving parts to it. It's pretty hard, and I think this video will really focus on like the thought process that you might go through. So instead of showing you the answer right away, I'm going to try to sort of show the thought process that goes behind it, just so that we can have like a better understanding of like, okay, what do you do when you face a problem like this? I don't want to show you the answer right away because it's not so obvious. right away, okay? So I hope you learn one or two tools down the road. Let's see what happens. So for number 9, we have that the function f is defined by this right here, okay? For these values, okay, so this is technically like my domain or range or something like that. See, so your values can only go from negative r up to r. And so if you notice, here's your r. So your function basically is defined from there to there. Okay, that is all it's really telling you. And that the region enclosed by the graph of x equals f of y, and the y-axis is, here's the first big hint, is rotated by 360 degrees about the y-axis in order to form a solid sphere. And so really, and this is more of a big brain thing, like you don't have to notice this, but this is really like the equation of a circle. Equation of a circle, okay? The equation of a circle goes like this. If it starts at the origin, so at the origin, if it's not at the origin, you're gonna like figure out the center and stuff like that. But at the origin, it is x squared plus y squared equals r squared. And so from here, whoever created this problem, all they really did was get x alone. So they did minus y squared, x squared equals r squared minus y squared, square root to both sides in order to get x alone. And that is what they ended up with, okay? This is where that comes from, okay? That comes from this. And so basically what they started with, okay? What they started with was simply this circle that you see here, and then they spun it around a bunch of times. They rotated it 360 degrees. And so basically they replicated the circle and started giving it more of a 3D shape. Now, I'm not exactly good at drawing 3D figures, but I hope you get the idea. So basically, you ended up with more and more circles each time, and then bada bim, bada boom, you ended up with a whole sphere. Okay, now this sphere has a hole in it because they also tell us up ahead that there is a sphere that is drilled through along the y-axis, creating a cylindrical hole. And so here you have two main shapes. Okay, clearly on the one hand you have the solid sphere, and on the other hand you have the cylinder. Okay, cylindrical hole, cylinder, right? And if you do the sphere minus the cylindrical hole, you end up with what they call the spherical ring. Okay, this is the spherical ring, which is basically just a sphere with a cylinder that got like pummeled through it, right? Drilled through it. It subtracted it from its volume. Ah, interesting. And so then they tell us, because apparently this is going to be useful, right? Then they tell us that the spherical ring, okay, has a volume, okay, has a volume of pi cubic units, and through all of this to find the value of h, and h is right here. So of course this is a lot of different information thrown at us, and we have to go piece by piece in order to really understand the ideal process and stuff like that, okay? So the first thing we can really try to like think about or go over is that, okay, I have a couple of shapes here, right? On the one hand, I have the sphere. On the other hand, I have the cylinder. And subtracting both, okay, you end up with a spherical ring. I'm just going to call it ring, okay? So you have the sphere, you have the cylinder, you have the ring, right? And we're talking about volumes here, see? And so technically, as I said earlier, the volume, okay, the volume of the ring has to equal the volume of the sphere minus the volume of the cylinder. Which makes sense because if in this diagram here, right, you go ahead and take the area of the whole like circle or sphere and you subtract this, which I'm putting in red. Okay, so if you subtract all of this, yeah, if you subtract all of this from your shape, you end up with the ring, right? All that I drew in red that I'm colored in red that I was deleting is this whole thing over here, right? This cylinder that shows up like that. That is what you're getting rid of, okay? That is what you're eliminating. So if you eliminate that, you end up with the ring. So that is what I'm telling you. The volume of the ring is equal to the volume of the sphere minus the volume of the cylinder. Now from here, there are a lot of different approaches, you guys. In fact, just looking at the mark scheme quickly, you have one method up here, you have another method over here, you have another method over here. So it's pretty crazy. There's a lot of different ways to solve this problem. It can get overwhelming, see? And so what I would sort of suggest is that, okay, you first established that for the volume of the ring, you got to do the volume of the sphere minus the volume of the cylinder. That is the first big, like massive sort of step. Now, the other sort of thing you have to realize, or the other tool you have to add to your toolbox, okay, is that this is the thing. Integrals are for finding volumes slash areas. Literally. Integrals are for finding volumes slash areas. In fact, when you're dealing with something like a normal distribution, okay, and you want to find the area from here to here, like normal CDF, okay, all your calculator is really doing is doing an integral of this whole thing from here to here. And it spits out this area, and that area is probability. See? So you've been using integrals for finding volumes and areas like the whole time. Maybe you just haven't really realized it. See? Um, so yeah, the integral is marvelous. It's excellent for finding volumes or areas. So in this case, we will be using it mainly for finding the volume, right? Now, what is another sort of way that you can realize or notice that this is the approach? Well, getting familiar with the formula booklet. Guys, the formula booklet has a lot of formulas, of course. It's a formula booklet. There's a lot of stuff in here that you can use that can really save you the day of the test or any test that you ever take. See? And so, in this formula booklet, there's one key tool that I would like to show you. In the topic of calculus, you will find topic 5, see? You will find stuff about integration, derivatives, and all that stuff. And here, this random guy online started talking about derivatives. So, and about integrals, sorry. So it's probably important, see? So let's go to page 11 or 12, right? Well, 12 because HL only, and we're cool boys by now, see? So now that we're part of the cool team, we can look at all these integrals and notice and tell ourselves, wow, why did I ever take Math HL? But you can also say, okay, there's one sort of relevant thing here which is hidden right there. Bada bim, bada boom. This is the volume of revolution about the x or y axes. And so earlier I drew with my amazing art skills a replication of how this circle is sort of like repeating all along it, right? So it's it's rotating. See, it's rotating, so you end up with one circle there, another circle going like that, another circle cutting through like the middle. You end up with a bunch of different circles. That is how you end up with a 3D shape, right? And so when it says, and here's the big idea, see? When it says that it is rotated by 360, it's actually also telling you, or the equivalent, right, is that it is a volume of revolution, see? So it's also, I mean, really, if it's rotated by 360 degrees, it's like the circle is doing a lot of revolutions. That's the most intuitive way I can put it. The circle is doing a lot of revolutions. Okay, so if it can do a lot of revolutions, if it can spin a lot, right, it rotates by 360 degrees, right? And so suddenly this tool becomes very, very relevant. And I've actually noticed that the IB loves to put in questions about, like, you have this shape, it spins 360 degrees, what's the area? Like, that's their classic. They love to do that, see? And so from here, well, here's my main tool, right? And so for the volume of revolution, let me just write this down. On the one hand, you have one version which is just with like y, and on the other hand, you have a version that's just with x, see? At the end of the day, it's pretty much the same thing, see? Point is, your integral looks like this. So our volume, right? The big tool that we're going to use, which I'm going to put in green, okay, the volume, right, is going to be the integral of from A to B, yeah, I'll talk about that in a second as well, pi, okay, and then, I don't think it really matters what we use, but we'll just go pi x squared dy. See? Yeah. So point is. In order to fill this in, we need to clarify what each thing is. See, so on the one hand, this A, okay, is your smallest value. This B is your biggest value. Now you might be thinking, is it X or is it Y biggest value? And in this case, because I chose dy, it's going to be the biggest or smallest Y value, okay? But that is only because this is the integral in respects to dy. Okay, if it was in respect to dx, it would be a little bit different. See? Now, why did I specifically choose the one of dy? Because we need to find the value of h. Let's not forget, and h is right here, and h works vertically, and so h has to do with y, so we're going to do the integral in respect to dy, okay? And this x squared, I know it looks kind of weird because it's an x, but really this is just your function, okay? It's just your function. And so if you follow all of these sort of approaches and rules, right, for plugging this in, right, well, you have that the volume of a ring, they told us, is just pi, right, from here. So volume of ring equals pi. It's going to equal the volume of sphere, which following this, will go from the smallest value of y, which, what would be the smallest value of y, you guys? And so, because we're talking about h, right, well, this sphere, or all these shapes, start perfectly at the origin, right? They start perfectly at the origin, right? Because, well, they don't really tell you otherwise. And you can also get the hint from here. See? It starts at the origin. And so, really, this right there is half of h. And this right there is also half of h, right? And so what that actually tells you is that down here, this y value is negative h over 2. And this y value is h divided by 2, right? We're talking about y values here, you guys, right? And so the smallest y value that you will be evaluating this integral on is negative h divided by 2. And up here you have h divided by 2 times pi times x squared, and x we said was our function. So our function is up here, right? It's just square root of that whole thing. So it's square root of r squared minus y squared. All of this squared because it's part of my formula, right? And integral respects to dy. So this whole thing was for volume of sphere, right? This is where I'm at, volume of sphere. We do minus the volume of a cylinder, right? Now, for the volume of a cylinder, it's a little bit harder. I mean, more than harder, it's tougher to spot, see? So I'm going to try to go over that in a second. Just give you a moment, see? And so for volume of cylinder, I'm just going to write minus volume of cylinder for now, see? Yeah. So, what the heck do we plug in for the volume of cylinder? Well, on the one hand, I will immediately tell you that we will be using this approach again, but just spotting that approach is a little bit tough. So let me show you how it works, right? So on the one hand, we just found, okay, we just found how to express, all right, we just found how to express the smallest and tallest value for h, right? So we said that this was negative h divided by 2. This was h divided by 2 for these sort of y values, correct? Now, let's now think about the radius. And so the radius, you guys, on the one hand, we have this radius from here to here, right? And that r there. And this r here is for, this r here is for the sphere. So this is the r of the sphere, see? So let me just put here small letters, sphere. So that is for the r of the sphere. Now you have another r technically. You have another r that goes from there. Actually, just to be a little more accurate, I guess the middle would be like IE to here. And so this r, which I will put r with an asterisk, okay, just to show that it's different. So this r is the r of the cylinder, okay? So, okay, how the heck can I express like the function, right, of the circle or whatever for the cylinder. So think about it this way, and this is like this is probably the biggest brain move part or thing that you have to do. See? So the integral that I use for the sphere looks like this. See? Now that comes from here, right? And this comes from the equation of a circle, where at the origin, you can express it like that. See? Now, this is for a y value that goes all the way up. So all the way up, this is for the sphere, right? So for the sphere, you have this y value associated to it. For the cylinder and the ring, actually, which is why we use those values, for the ring, it's a little bit smaller. And so the OG function has in mind, basically, the OG function has in mind this small, like, extra y values, right? Or these small extra y values. And how do they express it? They express it simply as y squared, see? And so all those extra sort of y values, they express it as y squared. But what is the y value that we are interested in for the cylinder? Only h divided by 2 or negative h divided by 2, see? And so really, if you follow the same sort of approach, because the cylinder in the end is also like very similar to a circle, it's just like top side down, right? You can actually express the function of the cylinder, right? If you rotate it by 360 a bunch of times and etc., the function of the cylinder is actually going to be square root r squared, so it's an extremely similar approach, right? Minus h divided by 2 squared. Ah, look at that. And so basically, this problem is super big brain because, I mean, my impression is that you have to know a lot of different stuff in order to go over this exercise. See? And so the biggest sort of jump or like specific thing you really have to know is associating that, okay, so if this comes from the equation of a circle, and because I have a smaller y value now, I can express that new y value as h divided by 2. Like basically this guy here. See? And well, you follow the process, it's y squared, so it's your y value, correct? You're just going to have it as um, h divided by 2 squared. See? So once you establish that, now you can plug that in for the volume of a cylinder, which is going to look something like this. It's going to be minus h divided by 2 minus h divided by 2 pi parentheses square root of r squared minus h divided by 2 squared. And this whole thing squared because we have our function squared, right? In respects to dy, right? Now, because, okay, these integrals are extremely similar, and in a certain way, it's not that they're the same, but they have both this, they have equal, I'm not expressing myself well. So the smallest value that they're going for and the biggest value, so the smallest with smallest and the biggest with biggest, are the same. And so when that happens, you can actually sort of combine these two integrals, and that way you can solve it all in one go. See? So this is just more of a work smarter, not harder sort of thing. You can combine these integrals, and yeah, you actually could have from the beginning just put an integral here and just done that whole thing. See? So maybe I should have done it that way. Whatever, who cares? You can combine these integrals. See? So because you can combine these integrals and they both have a pi that's in common, technically, right, what you end up with is a pi outside, the integral inside, right? And here, on the one hand, this squared with the square roots makes you end up with, quite simply, r squared minus y squared, right? Minus, well, this squared affecting this square root, minus r squared minus h divided by 2 squared. So all of this in respects to dy. See? Now, because you want to solve smarter and not harder, you can keep on simplifying before you apply the actual integral. And so if you keep on simplifying, what you can end up with, well, on the one hand, you can actually do a big brain play and divide both sides by pi immediately. See? So you actually end up with 1 equals this whole integral. So this whole integral now is going to be da, da, da. If you go ahead and combine these terms, you're going to notice that this r is going to go away with this r, right? And everything else in between will stay the same. And because you have a negative with negative, this term on the right turns positive. See? So basically, you're going to end up with h squared divided by 4 minus y squared. And you're doing the integral of this in respects to dy. Okay? So how the heck does that even work? How does the integral work? Especially when you're putting the limits, right? From negative h divided by 2 up until h divided by 2. How does this look like what actually happens? So, well, I'm kind of running out of space here, so let me just rewrite it down here for a second. So 1 equals the integral from negative h divided by 2 up until h divided by 2 of h squared divided by 4 minus y squared dy. Now, for evaluating an integral, see, first you have to actually do the integral and then you plug in like the lowest and highest values. See? So let me just write this on the side because the procedure is very important. So for an integral, first do the integral, which I know sounds kind of troll, like do the integration process, then plug in the highest value minus the smallest value, right? Again, this is just a very intuitive sort of approach or description. It's not the hardcore mathy way. First do the integral, like see what happens with the exponents and etc. Then do the highest value minus the smallest value. See, this is the part that like I really need you to understand because it's usually the confusing part. See, so first do the integral. Now you can go ahead and go to your formula booklet and it should be here, right? So da da da, standard derivatives, standard integrals. Ba-ba-bum. All right, there it is. See? So the classic integral, which is the one that we're going to go through here, right? You don't have a logarithm in here. You don't have an e going around. You don't have anything wacky happening. So all you're really facing is the integral of an exponent. Okay? And so you can do the hardcore mathy way, which is looking at the formula booklet and looking at this, right? So this is the integral of an exponent. And all you really need to notice is that on the one hand, well, if you have x to the power of n, that means once you do the integral, you end up with x to the power of n plus 1, and you divide it by that n plus 1. See? So for example, if you have, I don't know, x squared, and you're trying to do the integral of this, you're going to end up with x 2 plus 1 divided by 2 plus 1. So you end up with x cubed divided by 3, which makes sense because notice, and this is more of a nerdy comment, but integral and derivatives are opposites. All right? Which is no different than like multiplying and dividing are opposites. Okay? So that means if you have, I don't know, 4x and you times it by 2, you get 8x. And you have 8x and divided by 2, you get 4x, right? And so this can be like an eternal sort of loop. The multiplying and dividing are opposites, and integral and derivatives are the same. So if you do the integral of x squared, you end up with x to the power of 3 divided by 3. But if now you do the derivative, all right, so derivative of this guy here, you end up with the 3 going back out in front, right? So you end up with 3x cubed minus 1 divided by 3. The 3 goes away with the 3, you end up with x squared. And so, interesting. Integrals and derivatives are opposites. This is worth mentioning because if you look at this and you have no idea how that works and it looks crazy and it looks nasty, you can also sort of big brain it and think about, okay, so think about it as a derivative but backwards. And you can solve it that way. You really can. Okay, I've met people that never fully understood integrals, but they did understand derivatives. Like to the brim, like very deeply, and they would just always think backwards. See? So I'm just saying, whatever floats your boat, do it. Okay? Now, here you have the derivative. I mean, sorry. ah, here you have the integral of an exponent. See? And just like the example I just showed, you end up with x cubed divided by 3. Here you have y squared, right? So for the integral of an exponent, you end up with this first term, actually. I'll explain in a second, but this first term actually ends up as like this, with a y next to it. And the next term ends up as y cubed divided by 3, right? You already explained that. Here I'm like full on, this is the first step, right, for doing the integral, right? So you do the integral and this is how you write it. You did the integral, you integrated it, and you gotta put down the lowest value and the highest value that you're going for, see? So that was like the first step, see, doing the integral. Now something that I forgot to explain is why a y appears here, see? So think about it this way. Imagine you have x squared plus 5x plus 3, right? And this is your function. And they tell you, okay, do the derivative of this. Well, pretty straightforward, right? So this 2 is going to go in front, so you end up with 2x plus 5, because here you have an x to the power of 1, see? Multiplies in front. And then you do minus 1, so you end up with no x. And this last term, right, is going to disappear. Because technically, here you have an x to the power of 0. 0 is going to multiply in front. 0 times anything makes it disappear. And so here's the derivative, right? Now, if you were to go backwards, right, so here we did the derivative. With my wonderful cursive writing that says derivative. If now you were to go ahead and do the integral, okay, to try to get back, there's two main things that we can learn here. So on the one hand, if you try to get back, yes, as we've learned, you end up with x squared for the first term, right? And notice, this term here had no x next to it in the derivative form. In the derivative form, it has no x next to it. That means in the integral form, it must have had an x next to it. Because anything, right, that in the derivative form does not have an x next to it, it means it must have had at least one. Or else, it would have disappeared like this one, okay? And last but not least, over here, you don't put plus 3 because you're not a psychic. Here you put plus c. And so, that is why we also put the constant when we do the integral. You put the constant because you don't know which numbers might have disappeared in the process. Interesting, interesting. And so the main thing I needed you guys to catch on to it is that if you have the derivative version with like a singular number by its own, that means that in the original one there must have been an x, or else that singular number would have disappeared like the 3. Okay, that is what I'm trying to tell you. And so from over here, once you do the integral, well, this does not have a y next to it, so in the integral version, it must. That's all it really is. See? And here you don't consider the plus c because you are evaluating it in like a minimum and maximum, right? If it were on an undefined integral, I think it's what it's called, when it doesn't have the boundaries, then yeah, you need to put the plus c. But in this case, because we're evaluating with actual numbers like this minimum and this maximum, you don't put the plus c. See? Now, how the heck does that work? This is the next step. Then plug in the highest value minus the smallest value. See? So I'm going to try to be as clear as possible. I'm going to put in dark green the highest value. So highest value is h divided by 2. So on the one hand, if you do the highest value, you end up with h squared divided by 4. And the highest value, you guys, enters right here into the y. It enters into the y's. And so the highest value is going to be right here, times h divided by 2. Minus, you guessed it, you have h divided by 2 cubed. Damn. Divided by 3. And so you do this, okay, you do this minus the smallest value, which we will be doing in pink, okay? And so the smallest value is going to be minus h squared divided by 4 times my smallest value is negative h divided by 2. Da, 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 interesting. Minus negative h divided by 2 squared, cubed, divided by 3. So that is what I mean by highest minus smallest value. You first evaluate the integral with the highest value, subtract it to the integral evaluated on the smallest value. See? And so this looks absolutely crazy. It looks absolutely nasty. But there's one very important thing that just happened, you guys. Up here, and I really need you to notice this, okay? Because this is the cool thing about it, you know. This is why you do it. This is why we love it. Up here, how many variables did you have? You had h and you had y going around. But the moment that you evaluated, right, the integral with these h's down here, yes, it looks nasty. Yes, it looks crazy. Yes, no one wants to solve it. But the one good thing about it is that you have only h's. And so that is what helps you find the value of h. Finally, you found an equation, a formula, or a something that has only h on it. And so from here, you can solve for h doing a whole lot of math. So let's get excited about it. We're almost done. See? So this first parentheses, it's going to end up with h squared times h, so it's h cubed divided by 4 times 2, 8. Minus, here you have a cubed going around affecting both the numerator and the denominator, so you end up with h cubed divided by 8 divided by 3. I will show you how to solve that in a second, right? Minus, on the other side, you end up with negative h cubed divided by 8, so very similar to what we just had, minus, and this one is kind of crazy because you have negative h divided by 2 cubed, right? So I'm talking about how to solve this guy here, see? So because it's cubed, that means you have negative h divided by 2 times negative h divided by 2 times negative h divided by 2. And so on the one hand, it's pretty evident you also end up with an h to the power of 3, much like earlier, divided by 8. But because you have 3 negatives, it's an odd amount of negatives. So these, for example, turn positive, but then this positive is hit by that negative. Boom, you end up with a negative. So careful with that. So you end up with minus minus h3 divided by 8 divided by 3, right? And I'm just going to immediately show you guys, because you have a minus minus, really this is just going to turn into a plus, see? So careful with that, small detail, very, very important. Now, you have a bunch of fractions, you have some big fractions, it's getting nasty, it's getting weird. What I suggest you do, okay, is write it as like a very big fraction, see? So you want to reach this. You want to reach this, one fraction on top of another, see? You don't like it when it's like that. You want it to be one big fraction on top of another, see? So from here, you can actually put it as h cubed divided by 8 divided by 3 divided by 1, right? So this 3 divided by 1 is the same as 3. It's legal to write it this way. Trust me, guys, it's legal. No harm is being done, see? Minus the other parentheses, which ends up like this. So the same idea, divided by 3 divided by 1, see? Now, this is just a personal approach. You can deal with fractions however you want. But my personal approach is that I like to reach the one fraction on top of the other because there's actually a very visual approach to solving this. To solve this, you can do a times d divided by b times c. Literally, see? The other approach that you can do it is you can technically say that it's a divided by b divided by c divided by d. And because it's a fraction dividing, what you have to do is the reciprocal. You've probably heard of that. It's a divided by b times d divided by c. But that's really the same thing that's happening up there. So a times d divided by b times c. Right? So it's the same thing happening. Use your approach. Deal with fractions however you want to. Yada yada. See? So now, we end up with 1 equals h cubed divided by 8 minus, well, this guy times this guy, so it's just going to be h cubed divided by 8 times 3, 24. Minus my other parentheses, which is negative h cubed divided by 8 plus, well, it's really the same thing, right? So plus h cubed divided by 24. And so from here, right, so from here, You can start like combining the fractions right away. Is it better? Let me take a moment to think about it. I think it would be like a little bit better, I guess. So let's try to combine these fractions right away. So what they both have in common, when you are adding or subtracting fractions, you need the denominators to be the same. So when add/subtract fractions, you need the denominators to be the same. So because you need the denominators to be the same, you have an 8 on the bottom on the left, you have a 24 on the bottom on the right, and you can realize that 8 times 3 is 24. See, if you didn't notice that right away, just write on the side like multiples of 8. So 8 times 1 is 8, 8 times 2 is 16, 8 times 3 is 24. Boom, you found something in common, right? So that means that if I amplify by 3, the fraction on the right, so you do times 3 over 3, that means they will end up with the same denominator. And once you have the same denominator, you can combine the terms more fluently, right? So over here, you're actually going to do the same, times 3 plus this guy, right? All right, so you end up with, oh, and this is legal. This is called amplifying, okay? Okay, I think I wrote that horribly. I think it's amplifying, see? It's legal because you're technically just multiplying by 1, you guys, see? So some of you might be thinking, don't you have to multiply by 3 to everything? I say, no, this is multiplying by 1. Guys, 2 over 2 is how much? 1. 3 over 3 is how much? 1. If you multiply a number by 1, for example, 101 times 1, it's still 101. So you're not changing it in any way. Yes, it's a fraction, you're changing how it looks like, but it's still the same number. It's still the same amount because you're just multiplying by 1. And so the word amplifying is kind of tricky because you might be thinking, it's getting bigger. Think about it like a magnifying glass. See? You're looking at an object, you're looking at it closer, you're looking at it farther, it's still the same object, okay? So, now that that's been established, this fraction turns into 3h cubed divided by 24 minus h cubed divided by 24. So this is my first fraction minus the other one, which is negative 3h cubed divided by 24 plus h3 divided by 24. See? So now we can finally sort of reach almost the last part of the exercise. It's been a long one, you guys. So anyone that stuck around, you're a warrior, okay? You are a warrior. Good job. So the parentheses on the left, okay, it's going to be 2h cubed divided by 24 minus the parentheses on the right, which is going to be negative 2h cubed divided by 24. See? Now, because these two parentheses are separated by a small minus, this minus affects this minus, so really what you end up with is 1 equals 2h cubed divided by 24 plus 2h cubed divided by 24. So you end up with 1 equals 4h cubed divided by 24. So that means you can do times 24 to both sides in order to get h alone. This goes away with this. 24 equals 4h cubed. You want to get h alone, so divide by 4, divide by 4. H cubed has to equal 6. And how the heck do you solve h cubed equals 6? Well, you have to do the square roots with like a small little 3 here. This goes away with this. H equals that. Ladies and gentlemen, this is a very hard problem. Guys, that was crazy. That was actually like very impressive. This exercise is not the sort of exercise that is easy to notice what to do. I really try to focus on the thought process behind it. And the main tools that I think you should take home or write down or really just sort of like, that was very important, that was a huge step, is this guy here most of all. See? This guy here is huge, okay? The other big thing that was surprisingly important was the equation of a circle. See, for understanding how your y is going to change, it was also a very big brain play that you had to notice, right? So, what was the thought process to even discovering that tool? because it says rotated by 360 degrees, you should already be thinking about revolutions. And if you're thinking about revolutions, you're also thinking about the mark scheme. I mean, sorry, the the formula booklet and this guy here. See, I've noticed it's a classic of the AB, trying to find the volume of a 2D shape turned into a 3D and finding the volume. This is your main tool, you guys. Okay, this is probably the biggest sort of thing you can really write down and take home. It's this formula here. Don't fall into the trap of thinking, I have the formula booklet, so like I'm good to go. Guys, I assure you that none of you can tell me by memory what is inside the formula booklet because it's too much. And I'm not saying that you should be able to know what's in the formula booklet by memory, but you should know sort of what's in it. See? So that why is that important? Because the next time you're facing a crazy exercise like this one, and you read y-axis rotated by 360, you immediately think, rotated, revolutions. I know that's in my formula booklet somewhere. You don't have to know by memory which page. You don't have to know by memory like how it looks, how the formula looks like. You maybe don't even remember by memory how the formula works, but you know that it's in there, okay? And just that step is huge because then you open your formula booklet and slowly you start remembering how it works, where it is, etc., etc., and that gives you the big hint of how to move forward with an exercise like this. See, so the thought process oftentimes, you guys, depends on the buzzwords that they throw at you, the key formulas that arise from the formula booklet, and stuff like that. See? So, enough blah blah by me. Number 9 was pretty crazy. So, good job. Even for just trying this. Good job, you guys. All right, that is number 9. I'll see you around, and I hope it helped.
All right, you guys, and now for number 8, we walk into what we call a arithmetic sequences problem. Well, later on we have geometric sequences, but immediately the massive buzzword that we should be thinking about is the word sequences. Okay, so let me first talk about what sequences are, and then we'll jump into this specific problem. And so a sequence has two different sort of worlds, right? So you have the arithmetic ones, as you saw earlier, and you also have the geometric ones, okay? And so arithmetic ones are for adding and subtracting, and the geometric ones are for multiplying and dividing. And so an arithmetic sequence, an example could be 2, 4, 6, 8, 10. Okay? And so here, each time, what are you doing? You're adding by 2 each time. And so for an arithmetic sequence, the main idea here for the plus 2 is that you have what we call a common difference of how much? A common difference of 2. So that means d equals 2. It's specifically d, and in the formulas that you're going to see for arithmetic, you have the d letter associated to it because of difference. Okay? For geometric, an example I can give you is, for example, 2, 4, 8, 16, 32. And so what's happening here? Well, before it was for adding or subtracting, now it's for multiplying or dividing. So here you have to be multiplying by 2. So 2 times 2 gives 4. 4 times 2 gives 8. 8 times 2 gives 16. And 16 times 2 gives 32. And so here it's not common difference anymore, but rather common ratio. And here is also a common ratio of 2 because it's multiplying by 2. So r has to equal 2. Okay? Why do I talk about R? R because of ratio, and it's relevant to know this small sort of technicality because in your formula booklet, if you go to the part of sequences, okay, it's important to be familiar with the formula booklet, you're going to find that you have 4 formulas, you guys, okay? So you have this first one, this second one, this third one, this fourth one. Now, first things first, you can immediately notice that the two that are up top, which I'm going to put in green, okay, the two that are up top are for arithmetic. And the two that are on the bottom, which are going to be in blue, are for geometric. And so it's important to first know that these tools and formulas exist. So the moment you read the word sequences, you think, ah, okay, these tools are at my disposal. And you also need to know how these tools work, what is related to them, etc. And so as I mentioned earlier, you have common difference for D, which is why for arithmetic, you have D going around, right? While on the other hand, for geometric, which is common ratio, you have an R going around, okay? And so understanding R and D in that sense is already like useful, right? What is the other observation we can do? Well, they both, like the two up top, right, for arithmetic, you have one for nth term and you have one for sum of n terms. And on the bottom, for geometric, you also have for nth term and you also have for sum of n terms. Now, sum of n terms makes a little bit more sense. For example, S of 3 means you're adding the first term, the second term, and the third term. While on the other hand, for nth term, that means that, for example, you're trying to find U6, right? And so for finding U6, you plug in n equals 6 into this formula here. See? And so nth term is like you're finding one specific term, and sum of n terms is a little bit more straightforward. S of 3 means you're adding up the first 3. S of 7 means you're adding up the first 7. And now the last thing I'm going to mention is that you have I've been saying this whole time they have 4 different formulas, but I'm sure some of you already noticed, wait a second, don't I have more than one? And I would say, yeah, you're kind of right. Okay? What do I mean by this? Down here for geometric, okay, for the sum, right, you have 2 equal signs. Okay? And so that means that this equation on the left is the same as the equation on the right. Now, do they ask for the same things or not? For example, the one on the left asks for u1, asks for r, and asks for n. While the one on the right asks for u1, asks for r, and asks for n. And so, okay, so both of these equations are technically the same. They might be laid out differently. For example, the bottom has r minus 1, while on the other one you have 1 minus r. But technically, they're asking for the same stuff. There aren't different variables here that they're asking for, and so intrinsically they're the same, okay? While up here, for the sum of arithmetic, if you take a closer look, you have 2 different formulas here, right? But what do they each ask for? And so the one on the left is asking for u1, is asking for n, and is asking for d. While the one on the right is asking for also u1, also n, but not d, instead un. And so these small differences are the kind of thing that the day of the test can really add on to help you know what to do. So guys, these are your tools, and having clear what they ask for, what you need for each, is absolutely essential, okay? And I'm not saying you have to know this by heart, but you first need to have the intuition, okay, the moment you read sequences, you're thinking of, I have 4 tools, right? And of these tools, I remember there was this guy online saying something about like, some of these formulas have some things in common, other things not. You're not going to know it by heart because, spoilers, almost nobody does. But what you will know by heart is, there's a difference. What was the difference? And so you're going to do the same exercise as I did now and say, okay, so there's 2 equations here. For the one on the left, you need n, u1, and d. So you're going to write that down. And for the one on the right, you need n, u1, and only un. And so that's the main difference here. That is a big hint for which one can be more useful than the other one. And so this is more of a generic approach I'm trying to give you. You guys, in general, the procedure you should be doing is that you read buzzwords. You read, for example, arithmetic sequence, or you read, for example, sum of first, and boom, you're already thinking, okay, so the tools I be using are these over here. Now, this exercise is a little bit different because they actually give you And so as I was saying, for the procedure of this exercise, right, you're going to be identifying the buzzwords. And so this exercise is a little bit more of a special scenario because, you need to find this. They tell you that the sum of the first n terms of the sequence is given by this here. And so the formula for sum that you can use isn't just these ones, okay? But it's also this additional one over here, right? And so the one over here is a special one just for this specific arithmetic sequence, okay? So just for this specific arithmetic sequence, you can also use this sum of this formula, sorry, right? And so if you do the exercise over here that for the formula booklet, you need U1, you need N, you need D, or you need U1, you need N, and you need UN. Over here, what do you need? Look at that. You only need N. And so for part A, part I, for finding the sum of the first 5 terms, well, first 5 terms is a big hint for N equals 5. And so for the sum of the first 5 terms, you only have N equals 5. You do not have U1. You do not have D, right? And you do not have UN, right? And so you only have N, and thankfully the formula they give you only asks for N. And so for part AI, it's pretty straightforward. You just need to plug in N equals 5 into the formula they gave you. Now you plug in N equals 5 everywhere just to be organized. So that means that even this little n is going to turn into 5. So S of 5 equals 5 squared plus 4 times 5 is going to equal S of 5. It's going to be, well, 5 squared is 5 times 5, so 25 plus 20. S of 5 equals 45. So for part AI, we have that the sum of the first 5 terms is going to equal 45. Now let me put this in red, okay? Just so that, actually that looks very ugly. So let's put that in blue to remember that this was my final answer for part AI. For part A double I, we have that given that S of 6 equals 60, find U6. Now, before I tackle this exercise, there's a massive sort of thing I want to teach you, okay? First things first, an exercise which has 2 parts in terms of like part I and part double I, um, they're always going to be related. And so part double I needs something from part I, okay? And more often than not in the IB, although not always, but more often than not, what you do in part B needs something from part A, okay? And so on and so forth. It's not always the case, but sometimes it is, and it can be a massive hint on how to move forward. There's a very direct way to know if it's the case, right? And it has to do with the special word given. And so usually when they say given, it can either be like given what you did earlier, right? But other times the given is just like given and something they give you, quite literally. And so here it's given that S of 6 equals 60, find U6. And so this is a big hint. It's like, from part A, part I, plus the fact that S of 6 equals 60, find U6. And so these are a bunch of hints that you identify because first, it's part I and part double I, and secondly, they gave you this with the big buzzword given. Okay, and so this is just test taking skills, and you gotta have that in mind, right? And actually, this shows up all over the place. For example, here you have hence or otherwise, so it's telling you that for part B you need to use that. And over here you have given this, and so given this, you're gonna find V5 for part E. Now, that's just be on the lookout for the word hence. Okay, the IB loves to use the word hence, and just keep it in mind. Okay. Anyways, enough blah blah. I'm pretty good at that. For part A double I, they tell you that S of 6 equals 60. You know that S of 5 is 45 from before. So what is U6? And this is actually very straightforward. And let me explain it with the following idea. And so you know that S of 6, actually, let's start with, you know that S of 5 equals 45. And you know that S of 6 equals 60, right? Now, what is S of 5? S of 5 is the sum of the first how many terms? Of the first 5 terms. So S of 5 is just the first term plus the second plus the third plus the fourth plus the fifth. while the sixth, while s of 6, sorry, is the first plus the second plus the third plus the fourth plus the fifth plus the sixth. And so from here, if you do, for example, s of 6 minus s of 5, well, visually what you end up doing is this goes away with this, and 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 this, bada bim, bada boom, boom. So s of 6 minus s of 5 gives you u6. All right, and so technically 60 minus 45 is going to equal 15. All right, and so, well, I mean, if I plug everything in, it would be that 60 minus 45 equals u6, right? And so 15 equals u6, okay? That is what I meant to say. But anyways, I think visually it's very appealing. And there it is, okay? So u6, right? So u6 has to equal 15. Let me put it in light blue just so that I remember that this is what we did for part A double I. Now for part B, we need to find u1. And so for u1, there's a couple different approaches that we can use. There's actually like a lot of different methods. And there's one really quick way and one more hardcore mathy way. And so I'm going to start with a hardcore mathy way because it has a lot to do with procedure and formulas and stuff like that. And so when you need to find u1, immediately ask yourself which formulas have u1. And so you go to your formula booklet, and which formulas have u1? Well, both of the sum ones, right? Both of the sum have u1. And u1 is also up here, right? But what's the problem? Even though one up here, what does it ask for? It asks for d. Do we have d yet? No, we don't. And so you cannot use this one, and you also cannot use this one over here, right? Because you don't have d. And so you only have one remaining option, this formula on the right side. So do you have u1? I mean, you don't have u1, but you have everything else. So let me show you how that plays out, right? So you have everything else as you're about to see. So that formula from the formula booklet is s of n equals n divided by 2 plus, no, sorry, parentheses, my bad. Happens to all of us. Parentheses, u1 plus un. And so from here, you gotta start considering, like, what variables are here. And so technically, I did say earlier that you have three. You have u1, you have n, and you have un, right? But technically, and this is about getting familiar with your formulas, getting creative as well, which has to do with you using them a lot. So always start with the formula booklet. Technically, the other variable is also Sn. And so if you find a way to plug in, for example, this, and this, then you only need to solve for u1. Okay, so that's the game plan that we're going for now. Is there a way where I can plug in the other three and get u1 alone? And so technically from earlier, you found that, for example, s of 6 is 60. And so s of 6 is using n equals 6. So, that means down here, I have s of 6 equals 60. That also means that n has to equal 6. And do you have u6? You have u6 because you know that u6 is equal to 15. And so suddenly, you can now plug in all the ones that I put in green. Okay, you can suddenly plug in here, here, and here, and end up with only u1, which is what they're asking for part B. And so from here, if you plug everything in, you end up with 60 equals 6 divided by 2 because of n, parentheses u1, plus u6. u6 we said it was 15. Okay, I might have gone a little bit too fast there, so let me go piece by piece. If you first plug in n equals 6, you end up with s of 6 equals 6 divided by 2, parentheses u1 plus u sub 6, right? And so what is s of 6? We said that s of 6 was 60 equals 6 divided by 2 is 3, parentheses u1 plus u6, which is 15. And so from here, because it's all being multiplied, the 3 in the parentheses, you can divide by 3 to both sides. You end up with 20 equals u1 plus 15 minus 15 minus 15. Bada bim, bada boom. U1 equals 5. Okay? So this is the hardcore math way to solve it. You just use the formulas. Always consider the option of plugging in for s of n. I know it's kind of weird because you don't usually you're trying to find s of n, right? And so you as long as you practice with these formulas and look at different examples, you keep getting into the creative options, and that way the IB won't catch you. See? And so that is one creative way to use this formula. I know earlier I said you need u1 and an un to use this formula, right? These three things. But technically, right, if you have s of n as well, you can start like you can have 3 out of 4 and find the last one. So that's what I'm trying to tell you, okay? Which is what we did over here. Anyways, so that is one way to do part B with the hardcore mathy way. So U1, as we said, has to equal 5. Let me box it in and put it in blue so that we remember that this is my final answer. Now, that being said, there is another way to find U1, which is fairly quick, and I would like to show it to you guys, okay? And so technically, if I look at this example for the arithmetic sequence over here, right? So technically, think about it this way. And this is a very logical approach. And so S of 3, for example, is going to be the sum of the first 3, right? S of 2, for example, is going to be the sum of the first 2. And S of 1, I know it sounds kind of troll, but technically S of 1 is just the sum of the first 1. And so what I'm trying to tell you is that S of 1, it's just the sum of the first one. So S of 1 equals U1, and from here, well, you have this sum formula over there that asks only for n, so you can plug in n equals 1 here. You end up with S of 1 equals 1 squared plus 4 times 1, right? And so S of 1 equals 1 plus 4, S of 1 equals 5. And you know that S of 1 equals U1 by logic, right? And so here you can say that, because S of 1 equals 5, then U1 also equals 5. This is another way to do part B, okay? I'm just giving you all the tools you need. Might as well, show you all the options. Why not, right? Anyways, that is for part B, all right? Technically, you can also plug it in over here. So I'm just going to show you that quickly. Even here, if you plug in n equals 1, you end up with S of 1 equals n divided by 2, parentheses U1 plus U1. Oh, that's interesting. Oh, and n is 1, right? And so S of 1 is going to equal 1 half, parentheses 2 U1. This goes away with this. This is literally proof that S of 1 equals U1, okay? So trust me, you usually shouldn't trust guys on the internet, but just for today, trust me, S of 1 equals U1, okay? Yeah, and then for part C, they use the buzzword, hence or otherwise, write an expression for, and this is interesting, UN in terms of N. And so this right here is very important for us to understand, first of all, what it's actually asking for. And so what it's actually asking for here, when it says UN in terms of N, is basically that UN is alone. Okay, so careful with that. UN is alone, and you have a bunch of different n's on the other side. You might have a plus or 3, you might have a plus 3 somewhere, a plus 2, but you only have a bunch of n's on the right side, okay? And so keep that in mind. UN in terms of n means you have UN alone equaling a bunch of different n's doing a bunch of different stuff. And so it's our job to figure out how that plays out. Now, I think from here there's two different approaches, and part C is kind of hard. Okay, so I'm gonna immediately say that part C is kind of hard. So there's definitely a challenge coming up, right? So on the one hand, specifically to this exercise, you have that S of n, right? That one of the formulas for sum has only n's inside of it. And so this might be useful for leaving it in just in terms of n. But you might be thinking, yo, what about un? Don't you need un? Un isn't in here. And so that is when you start thinking, okay, where do you have un? Un, you have it. Actually, once again, un, you have it only in two places, right? Un is only in what I'm putting now in pink. So un is over here, and un is also over here, right? So there's un, and here's un. And so these are two different approaches, right? So the one up top, well, for using this one for getting un, just in terms of n, you need to find d. So if you find d, you're good to go. And for this one on the bottom right, well, basically, the problem is they have s of n here, right? And so, here's something interesting. That equation from the formula booklet is that s of n equals n divided by 2, parentheses, u1 plus un, right? And so you pretty much have all of this because you already have u1, right? And un is the expression you're trying to leave it in. But the problem is s of n. That is what's annoying you. But what is s of n? S of n is also this whole thing. So wow, this is kind of whack, but technically you can say s of n equals s of n, and I know that looks troll, but basically you're plugging in this guy in orange here and this guy in pink over here. And so if you go ahead and do that, you end up with n squared plus 4n equals n divided by 2, parentheses u1, we know that u1 is 5, plus un. And so yes, this looks super nasty, but wait a second. Technically, you only have two variables. Technically, you only have n and un. And so, that makes it a little bit more friendly. So if you get un alone, you end up with un in terms of n. So that being said, to solve from here, you want to get un alone. I think it's easiest if you first multiply everything by 2 to get rid of this fraction. So you end up with 2n squared plus 8n equals n, parentheses 5 plus un. You want to keep getting un alone so you can divide by n, like everything, right? And so, well, technically here, just to be more accurate, would be all of this divided by n. And so this goes away with this. You end up with 2n plus 8 equals 5 plus un. So you can do minus 5. Minus 5, you end up with un equals 2n plus 3. That is a way in which you can do part C. Now, part C is pretty hard to spot, and so let me go over the procedure just one more time. So because you need the expression for un in terms of n, you first thought, where the heck do I even have the symbol un? And you have it in two places. You have it in the equation up here and the equation down there. And so which one is more useful? Well, the one up top, you first need to find d, and with what we've done, we still don't have d. And for the one on the bottom right, well, you have s of n. S of n is annoying. But can you replace s of n with something? You can replace it with this, which is only in terms of n. Alright? So that was the logical approach that we employed. And technically, if you find d, then using the equation up top is like doable, right? And so I'm going to show you real quick how you can find d. Now, d is the common difference, right? And you can always find d, and this is important, you guys. You can always find d as long as you have two different terms. And so because you have u1 and u6, you can find d. As long as you have two terms, you can find d. All right, so that being said, you know that, I'm just kind of running out of space here, but you know that u1 is 5, and you know that u6 is 15. And so to reach from u1 to u6, how many times do you apply d? Well, I think it's good to make this like super visual, right? And so if I add a lot of visuals to this, you can put the term u2, u3, u4, and u5. And so technically, yes, you don't know what U2, U3, U4, and U5 are, but you do know that to go from U1 to U6, how many times did you apply D? And so the same idea I did up here of doing plus 2, plus 2, plus 2, plus 2, you can think about it down here as from here to here you did plus D once to reach this guy, right? And then plus D again, 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 right? So how many plus D's was it? It was 1, 2, 3, 4, 5. So that's telling me that U1 plus 5D has to equal U6. Pretty logical, right? And so if you plug in the values, you have that 5 for U1 plus 5D has to equal U6, which is 15. So get D alone, right? Minus 5 to both sides. So 5D equals 10. Divide by 5, divide by 5. D equals 2. And so now that you know that D equals 2, oh, you can plug it in over here, right? And so UN has to equal U1, which we know is 5, plus N minus 1 times 2. We know that D is 2, right? Now, I know that this 2 looks a little bit troll in the parentheses being at the end, but guys, it's no different than if it was in the front. Okay, so I'm going to leave it in the front just because it's a little bit more friendly. Blah, 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 blah. But from here, if you distribute, right, you end up with UN equals 5 plus 2n minus 2. You end up with UN equals, oh, look at that, 2n plus 3. Sounds familiar? It better be. It's the same thing that we got over here. UN equals 2n plus 3. UN equals 2n plus 3. So again, two different ways to approach it. You either identify that, oops, I need to find D, or oops, I need to solve the fact that S of n is annoying me, right? So you either plug in something for S of n, or you discover what D is using the different terms. So yes, keep it in mind, you guys. Whenever you have two different terms, you can always find D, and it's the same for the common ratio, okay? Which is actually what's coming now. And so later on, they tell us that considering a geometric sequence Vn, where V2 equals U1 and V4 equals U6. All right, interesting. We need to find the possible values of the common ratio R. And so what they're telling you here is a little bit weird, okay? And so first things first, here they're associating, right? I mean, we gotta leave something clear. So for geometric and arithmetic, they always think in terms of U, okay? So like UN is on both, U1, U1, like they both arithmetic and geometric, like they use the letter U for the terms. But over here, they plug in or they give you Vn, okay? And so this is just to sort of like tell you that, okay, when we're talking about the geometric sequence, it will be with V. When we're talking about the arithmetic, it will be with U. And so they tell you that V2, so the second term of the geometric, is equal to the first of the arithmetic. And that the fourth of the geometric is equal to the sixth of the arithmetic. And so if I, before even answering part D, I just highlight that information more visually. So you have that, well, you have some first term, right? Then you have your second, your third, and your fourth for the geometric, right? And you know V2 and V4. And so V2 is equal to the first of the arithmetic. And the first of the arithmetic was, it was 5. V3 you have no idea, but V4 they tell you is the sixth term of the arithmetic, and the sixth term of the arithmetic is 15. And so guys, to reach from 5 to 15 in the geometric, how many times did you apply R? So you applied it once here, and you applied it once over here, right? Now, clearly you ended up with a bigger number, so you know it's multiplying, see? Now, technically, it's always multiplying because if it's less than 1, it gets smaller, but just for us to think about it, we're going to think about it, it's multiplying, not dividing, okay? Whatever, it's growing, it's got to be multiplied by something greater than 1, okay? So, the common ratio you apply r twice to reach 15. So 5 times 2r has to equal 15. And so careful, here's a slight difference. It's not going to be 5 plus 2r. We're now in the world of geometric. It's 5 times 2r. And so technically you end up with 10r equals 15. And so from here, because you want to get r alone, what you can do is divide by 10 to both sides. So r has to equal 15 divided by 10. Now, I made a massive mistake here, and I'm going to leave it on the video because we all make mistakes, and that's just fine. See? My massive mistake is that yes, r is being applied twice, but it's being applied twice by multiplying. It's not being applied twice by adding, which is by putting 2r. It's being applied twice by multiplying. So technically here, instead of 5 times 2r, it should have been 5 times r squared. So I'm sorry, you guys. I trolled you a little bit, but hey, we all make mistakes. I'd rather leave it on the video. And it's a common mistake, so I think it's also a good idea that you leave it on the video. See? Anyways, point is when you're applying the common ratio, think about it as squared, cubed, etc. because it is multiplying, right? So whenever you have, I don't know, x times x times x, you're gonna add the exponents, right? So you end up with x cubed. Whenever you have x plus x, you end up with 3x. You're adding the constants that are in front, okay? So it's a slight difference, and I messed it up. Happens to anyone. Let's proceed, okay? So now I'm putting it as I should have. 5 times r squared equals 15. And so from here, you want to get r alone, so you can divide by 5. Divide by 5, r squared equals 3. Whoops, sorry about that. And so from here, you can, you want to get r alone, so you do square roots to both sides. In order to get rid of the squared, you end up with r equals 3. Now, careful. Because you're square rooting, your answer is going to be r equals plus or minus 3, which actually makes a lot of sense because for part D, they're asking for the possible values of the common ratio r. Also, the possible values is either r being positive or r being negative. If you've never understood well why square root of something gives you plus or negative, let me explain. And so technically, if you're looking for the answer of, I don't know, square root of 4, right? Immediately you're going to tell me, it's 2. Now let's understand for a second why it's 2. It's 2 because 2 times 2 gives you what's inside the parentheses, gives you 4. And so technically, when you write this, you're asking, like in math terms, what number times itself gives me 4. And so 2 times itself gives you 4. So 2 times 2 gives 4. But you guys, negative 2 times negative 2, how much is it? Ah, it's also 4. And so that's why for this square root, if it's base 2, right? I mean, I think it's called base, but whatever. Whenever it's like a normal square root, right? You can do this association, right? So you can do this association where it's either positive 2 or negative 2 because of these two different scenarios, okay? So anyways, for part D, that is why r has to equal plus or minus 3. And so now for E, they tell you that given that v of 99 is negative, find v5. All right, and so this is a little bit of a curveball, you guys. Okay, and so here is something we need to understand. So for all these different sort of values, okay, for your geometric, r can be positive or negative. Now, you haven't discovered yet if r is negative or positive, right? And so this information here is a big hint to see if r is going to be positive or negative, right? And so think about it this way. If you were always multiplying by like a by positive 3, would you ever end up with a negative value in your geometric sequence? Technically, no, right? And so if you're multiplying by a positive value and your terms are already positive, they're never going to go negative, okay? But if you're multiplying by a negative value, some of them will be positive and some of them will be negative. Why do I mean some of them? Because, for example, over here, I don't know, let me make something up. See? So let's say you have a geometric sequence of r equals -2, right? And so if you're multiplying by -2, you can have, I don't know, you can start with +2, then it goes to -4, then you have +8, then you have -16. And so, yes, it's increasing, but some of these values are positive, some of these are negative. Now, if you start with a positive, like, first term and r is positive, then your values will always stay positive, right? The only scenario that can be like a little bit tricky, right, is if your first term starts negative. So if your first term starts negative, but your r is positive, then everything will stay negative, okay? And so think about it this way. The only scenario that should really, really catch your attention is if you have alternating symbols. So if you have alternating symbols, that means your r has to be negative. Okay, that is the only hint I can sort of like give you. Okay, so if they're alternating, your r has to be negative. And so here, they're telling you that your 99th term, which is way out, right? So your 99th term is negative. Your 99th term is less than 0. And so if somewhere along my line of math, I have some that are positive and some that are negative, r by logic has to be negative. The other way you can think about it is that, for example, in this example, right, the ones that were odd, so v1, this is v2, this is v3, this is v4. So in this example, the ones that were odd are positive, while the ones that are even are negative. And over here, what you can actually end up with is that the even ones are positive, and here the odd one for 99th term, 99 is odd, so the odd ones are going to be negative, right? V5 is negative, that means R has to be negative. So I said the same thing in a lot of different ways. I'm sure one of them worked out for you. See? So anyways, for finding V5, all you really have to do is take this 15 from before, the V4. So you take this 15, you multiply by R, and that gives you V5. So just to be a little bit more organized, actually, V4, right? So V4 times R will give you V5. Okay? So V4 times R gives you V5. V4 is 15. R we just identified has to be -3. And so that will be my V5, right? And so 15, right? 15 times -3 has to equal V5. And so from here, actually I missed something small over here. So this is plus or minus square root of 3, you guys. Okay? And so technically from here, my bad on that, right? So you do square root of both sides, you end up plus minus square root of 3. Apologies. This is from way earlier, right? You end up with 15 times -3 equals V5. And so V5 has to equal basically -15 square root of 3. All right? And so apologies for that. On this step over here, everything was going just fine, but I needed to leave it as plus or minus square root of 3. So small detail there. I'm sorry, you guys. But now I recognized it, so there it is. For part E, V5 has to equal -15 square roots of 3. That is how you solve number 8, and I hope it helped.
Alright, you guys. So for number 11, you really have to be organized in your approach. Okay, this is yet again another sort of exercise that has a lot of different tools that you can use. So you have to be very organized and methodical in how you approach this. Okay, so consider the following diagram which shows the plan of part of a house. So here we have, as it says, a narrow passageway with width 3 over 4 meters, which is this passageway right there, right? Is perpendicular, okay, that can be useful information, is perpendicular to a room with width of 6. And so just so that we all understand, this is the 3 over 4, right, all along this, and this is the 6 meters of width, okay? Boom, 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 boom. So, that being said, they tell us that at the corner point C, points A and B, okay, are variable points on the base of the walls such that ACB is a straight line. Let L denote the length of AB in meters. And so L actually goes like this. All of this will be the famous L, okay? And alpha, which they actually already put for us, will be the angle that AB makes with the room wall, where alpha is between these values. Okay, so that is definitely going to be more useful down the line. But for now, what interests us is that the angle alpha is this guy right here. Okay, so that being said, for part A, we need to show that L equals that whole thing. Now, before we even move on, whenever you face an exercise that starts with show that, notice this is a fact, okay? So a lot of times in my videos, I make the point that, what you need in part C is something from part B, or what you need in part B is something from part A. So like, if you don't have the exercise like completed thoroughly from the beginning, you might get stuck at some point, right? And then it has something positive and something negative. It can have something positive because looking at the other parts that you just did, it can be a very big hint for what's coming. All right, but another thing that can play against you is that, dude, if you didn't do part A, you can't do anything, right? And so watch out for that. It's not always the case, but you do need to like keep an eye out for that. See? Now something that I've come to realize or that I've noticed is that whenever you have a show that exercise, because it's a fact, technically you can skip this one and only do this if you're low on time, right? Like don't skip exercises just to skip them. Skip them if you're low on time, if you're prioritizing, etc. You don't have to show you don't have to, you can skip part A and do part B, right? Because part B, you need to do the derivative of this equation, and they're giving you the equation, right? So you can do part B without part A. That's what I'm trying to tell you. Whenever you have a show that show up in your exercise, whenever you have a show that show up, that means it's a fact. That means you can use it, okay? And that's also important because down here, this show that, okay, is also a fact. All right. Is that going to be useful or not down the line? I do not know. But watch out. Whenever they say show that and you're stuck on that exercise, like imagine we never solve part A, right? Don't give up. This is a fact. You can do part B. Okay. So even if you have a lot of trouble showing whatever you're supposed to show, know that you can work with it as a fact for the parts that follow. Okay. That's the big hint I want to start off with. Keep it in mind. All right. Now, now we will actually get into the exercise. See? So we need to show that L equals that whole thing. See? Now there's a lot to go over here, and the main idea is, first of all, L, as we mentioned earlier in red, is that line. So we need to basically find the sum of two things in order to find that line, right? And on the other hand, it has this thing called sec and cosec. And so this is something we also have to go over. What the heck is sec of alpha? Whoop, sec. What the heck is sec alpha and what the heck is cosec alpha? Now, this is the kind of thing that is awfully specific, but it is so specific that it is also in your in your formula booklet. Okay, guys, the day of the test, you're going in with 2 hours of sleep, 2 years of this thing called a graphing calculator, hopefully that you can use, not always, right? Depends on the test. And a pen and pencil, your brain, a whole lot of motivation. and the formula booklet. So the formula booklet is something you can use the day of the test. So get familiar with it. Why is this important? This is important because the moment, and this is what like the level I need you to reach, okay? The moment you read sec or the moment you read cosec, first you're going to freak out because it's trigonometry and no one understands trigonometry. But secondly, you will recognize it as something that you've seen before. And where have you seen it before? Bada bim, bada boom in the formula booklet. So, guys, that is how you're supposed to use the formula booklet. Okay, you don't have to know it by memory, but also don't just say, I have the formula booklet, so I don't have to know the formulas. No, no, no. That's not the ideal approach. The ideal approach is knowing what is in it vaguely. Okay, is recognizing that if you read sec or you read cosec, you say, I'm pretty sure that's in my formula booklet. Let's check it out. Okay, that's the sort of thing we need to do. So you obviously go to topic 3, geometry and trigonometry, because if you don't know what's going on, you're probably in a trigonometry problem. So we go ahead and go to page 7 HL only because we are cool kids. We are in HL. So we go to page number 7, and here we can really start playing around with what's happening. So, oh, will you look at that? So here is sec, and here is cosec. Now, maybe the names are a little bit not so intuitive, right? Because sec, you might think about sine because it has an S, or cosec, you might think about cosine because it literally starts with co, but stick to the formula. So really, sec is just like inverse co. You can kind of think about it that way, right? Inverse in a more literal sense because it's 1 over cosine, right? So sec is 1 over cosine, well, cosec is 1 over sine. And so that is already a big hint. So if sec is 1 over cosine and cosec is 1 over sine, then looks like I need to use sine and cosine in order to solve this, right? Now, going back to length L, well, length L, they did tell us for some reason, and the IB always tells you things that you need to use. Okay, so for some reason, they just told us, oh, points A and B and C lie on a straight line. Okay, ACB lie on a straight line. And so because they lie on a straight line, that means that length L can be this distance plus this distance. So length L is that plus that. So let's explore piece by piece how we would do it, taking taking into consideration that we probably have to use cosine and sine. So from here, well, how can you find that length in green? See? So eventually, right, if you stare at it for long enough, you will start to realize, I can draw a triangle here. Because it's a triangle, because it's a trigonometry problem, once you identify you have sine and cosine going around, you should be thinking in right triangles. Okay, a lot of the tools that you can use in trigonometry have to do with right triangles. Okay, that is why trigonometry has tree with it, tree for triangle. Think in right triangles. That's what I'm trying to tell you. Think in right triangles, and eventually you will realize that you do have a right triangle hidden right over here, right? And so this right triangle, well, what do you know about it? This right triangle, okay? What you know about it is that this is 90 degrees, right? And some of you might be telling me, like, how do you know it's 90 degrees? Well, because this passageway is perpendicular to the room. Haha, got you there, didn't I? So, you know that this is 90 degrees, right? You know that because this distance is 3 over 4, that means this one up here as well. So this is 3 over 4. You know that because this angle is alpha, the one on the other side is also has to be alpha. So this is alpha. And is that all I know? I think that is all I know. Yes, that is probably all I know. See? And so this thing in green is from A to C, right? So we can just call it AC. All right, cool. On the other hand, we do have another triangle over here, right? Once we start thinking in right triangles, it's very easy to spot because this is 6 meters. Then that means that if you keep moving this line over and over and over, eventually you reach this guy here. And so bada bim bada boom, it's a right triangle. It's a room, right? So it's nice dimensions. This is a 90-degree. And so what do you know about this triangle? You know that this is 6 meters. You know that this angle is alpha, and that from here, right, from here to here, you have the distance CB. And so if you actually redraw that triangle, what you end up with is, just so that we're all on the same page, you know that this is 6, and you know that this line in blue, right, this line in blue is just the distance CB, right? Oh, and sorry, this right here is alpha, right? And so once we start thinking in terms of cosine and sine and all that stuff, because we identified it from sec and cosec, you think about those specific tools. And so you must have learned by now or must have heard, and if not, here's a quick review, that sine and cosine and tangent has associated to, or at least it's how it was taught to me, sine is so, cosine is so ka, and tangent is so ka toa. So what the heck is happening? Why, like what, right? What is happening? So is telling you that you can have sine of some angle, right, equal opposite over hypotenuse. That's why so, OH, opposite over hypotenuse. Meanwhile, cosine is going to be ka, so that means I have cosine theta equaling the adjacent over hypotenuse. And last but not least, you have the toa tangent, so tangent theta has to equal toa, so it's opposite over adjacent. Okay, so that means that in all of these triangles, you have to be really careful with which one is adjacent, which one is opposite, which one is hypotenuse. And the main thing that most people get confused with is sometimes they put the adjacent as the hypotenuse. Okay, that is the main thing that people sort of mess up, and I need to tell you immediately that the hypotenuse is always the hypotenuse. Okay, the adjacent and the opposite might change relative to which angle you're thinking of, but the hypotenuse is always going to be the hypotenuse. There is no argument there. The hypotenuse will always be the long side. Okay, and you can also understand it as the one that is opposite from the 90 degrees. Okay, the hypotenuse is always the long side. It's always the opposite from the 90 degrees. The adjacent and opposite depends on your angle. What do we mean by this? If this is your angle, right, that means that this is your adjacent. But if this is your angle, then that means that this is your adjacent. See what I mean? So adjacent depends on where you're standing, but the hypotenuse is always going to be the hypotenuse. See, this one will never be adjacent. This one will always be hypotenuse. Okay, so be careful with that. I might as well mention it because I know it can be confusing and etc. And well, there it is. Okay, so back to reality, back to the exercise. Over here, what can we apply? You stare at it for long enough and you realize that you have an opposite and the hypotenuse. So which one has opposite and hypotenuse? Sine. So up here on top, you can apply sine of alpha has to equal my opposite, which is 6, divided by the hypotenuse, which we said was side CB. Okay? Well, down here, you stare at it for long enough and say, okay, so I have the adjacent next to alpha and the hypotenuse. So which one has adjacent and hypotenuse? Cosine. So down here, you can apply that cosine alpha. So ca, so it's going to be adjacent over hypotenuse. The adjacent is 3 over 4 divided by side AC, right? Now, from here we still need to finish proving, showing, etc., right? And so why would I do this in the first place? You would do this in the first place because technically L, this distance L, right? The long line has to be, and I should have mentioned this earlier to be honest, that distance L, right, has to be AC plus CB. And here you just created equations that have CB that have AC. Ah, so that's why we're doing this in the first place. If you find AC and you find CB, that will be, and you add them together, that will be the length that you're trying to find, and that will pretty much show that L has to be this. See? So, we need to get AC and CB alone, like, respectively in each of their scenarios. And so up here, what you can do, right, is that you can multiply by CB on both sides. So that means that you have CB times sine alpha equaling 6. Now, you want to have CB alone, so you can go ahead and divide by sine alpha to both sides. This goes away with this, and CB has to equal 6 divided by sine alpha. Okay? Now, our show that has sec and has cosec inside of it. So we looked into the formula booklet, we found out what it was, and it's basically just 1 divided by cosine or 1 divided by sine. And so in this case, I have a sine on the bottom, right? So if I, just to make this very, very clear, when you have 6 over sine alpha, it's the same as if you wrote out 6 over 1 times 1 over sine alpha. Okay, it's the same thing. It's like the short version, the long version, it works the same, okay? And so, here you have a 1 over sine alpha. So that right there, ladies and gentlemen, is cosec alpha. And so, boom, will you look at that? CB equals 6 cosec alpha. And so on the one hand, we just found our value for CB, right? And our value for AC, well, we do a very similar approach. We're going to multiply by AC to both sides in order to get it out of the fraction. So you end up with AC cosine alpha equals 3 over 4, right? You divide by cosine alpha in order to get AC alone. A very sort of similar approach, right? And eventually you reach that AC has to equal 3 over 4 times 1 over cosine alpha, okay? Because you're dividing by cosine alpha, it goes in like this, and bada bim, bada boom, this, as we saw earlier, is that. So, this makes it a lot more friendly. AC has to equal 3 over 4 sec alpha, right? Sec alpha. And so if now I apply my formula from earlier, that is basically this long distance has to be what's in green plus what's in blue. Clearly you end up with AC, which is 3 over 4 sec. So you end up with your big L being 3 over 4 sec alpha plus CB, which we said was 6 cosec alpha. Bada bim, bada boom, it is the same thing that they told us to show down here. So ladies and gentlemen, part A is not that tough, but you do need to be aware of what sec and cosec is. And really, you don't have to know it by memory. That is the biggest sort of energy I'd like to transmit to you. You don't have to know it by memory. You don't have to be a math grandmaster or anything crazy like that, but you do need to be someone that knows what's in their formal booklet roughly. Okay, so you should reach the state where you reach sec, where you read cosec, and you say, I know I've seen that before. Let's look it up. I know it's somewhere in there. What's going on? See? So you figure out what's going on. You realize it has a cosine and a sine, and boom, those are already huge hints that, okay, you need to use cosine and sine. So you draw your triangles, and it becomes very evident, right? You do a quick review of what cosine and sine, how it's written. It's SOHCAHTOA, and everything just kind of flows. See? So again, being familiar with the formula booklet is the number one like tip I can try to give anyone that watches my videos. Okay? Anyways, enough blah blah. Let us now move on to part BI. Okay, so part BI is asking you to find basically just the derivative of L in respects to A. And so the derivative of L in respects to A, on the one hand, a quick reminder, if you couldn't do part A, you can move on to part B because this is a fact. Okay, so you can just do the derivative of this immediately if you never did part A. Keep it in mind to claw some points if you're running low on time or you got stuck or you get stuck or whatever. See? Yeah. That being said, what the heck is the derivative of this? And so again, you need to go to your formula booklet because the derivative of sec or cosec or sine or cosine, you can end up like memorizing them, but most of us right now probably don't, and that's perfectly fine. I might as well double check you guys. And so because we're entering the realm of derivatives, right? Because we're entering the realm of derivatives, we are talking about the land of calculus, everyone's favorite. And so page 12, HL, we're part of the cool team now, so we can go to page 12. So page 12, here starts the calculus, and there's a bunch of standard derivatives. See? You actually have cosec in here, which is interesting, right? So we might end up using cosec right there. Let's see what else we have. A bunch of crazy stuff. A bunch of crazy stuff. See? Yeah. Standard derivatives. Derivatives, yeah. So yeah, we're probably just gonna end up using this page right here. And so on the one hand, I can use the derivative from the formula booklet for cosec, right? So I can use that for this part. And oh, I have one for sec as well. See, so I can use that here as well. Let's just do it and see what happens, right? And so, for finding the derivative of dl in respect to dA, right? For sec A, we can see that sec, right, is just gonna keep the sec, right? So it keeps it, and you multiply with a tan. Okay, that's it. So you keep the original and you multiply with a tan. So for this first term, okay, which I will be doing in whatever, in pink, right? So for this first term, the 3 over 4 stays because it's, well, multiplying my term, right? We leave sec A, or sec alpha, sorry, because we're following from the formula booklet, and we multiply by tan alpha. That's literally it. See, so this is sec alpha times tangent alpha. And then for the next part, right, for the next part, which I will do in this yellow, actually, no, that yellow looks terrible, in this, whatever, this color, yeah, 6 cosec alpha. So what does cosec do? Cosec, on the one hand, okay, means that you put a negative in front and you multiply by cotangent x. Okay, I know this looks crazy, and I know some of it maybe you don't recognize it, you're not sure what it is, but trust the procedure, trust the formula booklet. This is their derivative for cosec, so we will follow it word by word. So on the one hand, you will end up with a negative 6. The 6 sticks around, that is not going anywhere, so negative 6 times cosec alpha, so that stays, following from the formula booklet, right? The cosec stays, and then you multiply it by cotangent of alpha, right? Cotangent alpha. All right, perfect. So there's my derivative. Not that complicated. Go ahead and leave it a little nicer, which would really only be that this plus and negative makes you leave it as negative this. See? So there is my derivative. Not that hard. You just gotta be familiar with the formula booklet. See? Don't be the guy that looks at this derivative and says, damn, I never learned the trigonometry derivatives. Like, I'm screwed. Take a moment, think about it. You know it's in your form booklet, find it, do it, okay? You can do this mainly just by knowing that it's in here, okay? So keep that in mind. That is for part BI, see? For part B double I, they tell us that when your derivative equals 0, okay, that's all it's saying. That is all it's saying. When your derivative equals 0, show that, so this is also something you can take as a fact, show that alpha equals arc tan 2. So, the first thing I'm going to go over is what the heck is arctan 2, right? Or what the heck is arctan? So, my quick review for that is the following. A lot of times in these exercises of sine, cosine, tangent, etc., for example, imagine you have, I'll make it up, but imagine you have sine theta, okay, equaling 1/2, right? And so this theta is an angle, okay? And if you were to get that angle alone, like if you want to find the angle, well, you need to get theta alone. So what is the opposite of sine? Well, think about it this way. What is the opposite of multiply? It's divide. What's the opposite of adding? It's subtracting. What is the opposite of sine? It's sine inverse. And so multiplying is the inverse of division, adding is the inverse of subtraction. The inverse of sine is literally just sine inverse. And so if you apply sine inverse to both sides, this goes away with this, and you end up with theta equaling sine inverse of 1/2. Okay? That is the main idea of why you use inverse. Now, for some reason, a bunch of people wanted to get fancy, and if you face the same exercise, just that you're using tan, so tan theta equals, I don't know, 1/2. Again, I'm just making up the numbers. And you apply the same thing, like, okay, you gotta do tan inverse, and then tan inverse. This goes away with this. Theta equals tan inverse, okay, of 1/2. And for some reason, you can also write this as theta equals arctan 1/2. Really, you can write it like arctan instead of tan inverse. See? So all the arctan is really doing is like, dude, it's a synonym for tan inverse, okay? That is the intuition I'm going to share with you. So arctan is not so spooky, and it's actually a little bit of a hint. You gotta get tans in there. So get tan in there. So that is a big hint. Get tan in there. Eventually you will be using a tan inverse, and it's written as arctan. Okay, that's all that's really happening. That is also why they get alpha alone, because alpha is inside all of these parentheses. So eventually you put everything. That's the thing. Because you reach that alpha is arctan 2, which we said was just tan inverse, right? You need to have everything in terms of tan. So everything in terms of tan, and then you do tan inverse and you get alpha alone. And so this right here is actually giving you so much information than what you think. It's telling you all the things I just mentioned. On the one hand, you need to get tans in there because it's arctan. Like, just starting off with that, see? On the other hand, because it's arctan, you will be doing tan inverse. And also, because you're leaving alpha just in terms of arctan, everything needs to be in terms of tan. Or else you would also have a plus sign going around, which you don't. So you need to do those things, right? Just leave it in terms of tan, figure out what happens, how to do it, etc. Right? So we will need a little bit of space. So let me put that maybe up here, right? So let me erase this for a second. So as I said, keep in mind, you need to put everything in terms of tan. And you might be thinking, dude, I have no idea how to put everything in terms of tan. But what you should have an idea of, and if not, you will learn that now, is that for putting stuff in terms of tan, okay, or cosine or sine or etc., you have a bunch of trigonometry properties, okay? And so all of those trigonometry properties can really help you jump from one, like cosine or whatever, to the next, right? And so first things first, our derivative was equal to 3 over 4 sec, I think it was, sec alpha tangent alpha, sec alpha tangent alpha, just give me 1 second to do this, minus 6, I don't know why I put plus up here, but whatever, see, minus 6 cosec alpha, minus 6 cosec alpha, right, minus 6 cosec alpha, times cotangent alpha, times cotangent alpha, right? So this is my derivative, okay? And they tell us that when this equals 0, right, we need to show, that's the thing, when this equals 0, show that alpha equals arctan 2, right? So first we will equal it to 0. That means you end up with 3 over 4, well really, let's make it a little quicker, right? So this equals 0. This whole thing equals 0, right? So when this whole thing equals 0, that means you can do plus this whole thing, just so that everything remains in terms of positive terms, right? So plus this to both sides. This is legal because there's only a negative affecting everything, right? And so this goes away with this. You end up with 3 over 4 sec alpha times tangent alpha equaling 6 cosec alpha, right? Cotangent alpha. See? Now let's first go with what is most friendly. I will actually first go through the 3 over 4 and the 6. See? So technically, if you want to sort of leave this more nicely written, you can first do times 4 to both, right? So that means this goes away with this. You end up with 3 on the left, and on the other side, you end up with 24. And if you divide by 3 now, so this goes away with this, and divide by 3, that means on the right side, you end up with 8, all right? So there I was just playing around with the numbers. You can make this disappear, and eventually you will reach an 8 on this side, okay? Now the next thing we have to really embark upon is that, okay, we end up reaching an arctan, so you need to put everything in terms of tan. How the heck can I do that? And so clearly you need to like sort of get rid of the sec, get rid of the cosec, get rid of the cot, right? Of the cotangent. So on the one hand, we did see earlier, right, that sec was 1 over cosine alpha. See? And this is already a step like forward because we're getting rid of the sec and leaving things in terms of sine, cosine, and tangent. Now, some of you might be wondering, why would I want it in terms of sine, cosine, and tangent and not in terms of sec? Well, because in your formula booklet, you have a bunch of, let me find it. Okay, this is not in calculus, it would be in trigonometry. You have a bunch of identities. So you have a ton of identities going around, right? Trigonometry identities, identity for tan, this or that, etc. And a lot of it has to do with sine and cosine. See? So on the one hand, you can get rid of the sex, rid of the sex. You can get rid of the sec. You can get rid of the cosec, put it in terms of cosine and sine. And if everything is in terms of cosine and sine, you can start thinking about applying this. So tan can get written as sine and cosine. So if everything is in terms of sine and cosine, you will be able to reach tangent more easily. Okay, that is the main idea I'm trying to tell you. And the way to sort of realize that is being familiar with the formula booklet. So once you're familiar with the formula booklet, you can have that sort of realization that, because I need everything in terms of tan, I first need everything in terms of sine and cosine. So the sec alpha, we can write it as 1 over cosine. See? So here on the left, you can immediately put tan alpha divided by cosine alpha. Okay, so that is already a little more friendly. On the right side, you end up with 8 times cosec alpha. Now, cosec, we did say was 1 over sine. So that means I end up with 8 times cotangent alpha divided by sine alpha. Okay? Now, for the cotangent, it's a little bit more tricky to try to get rid of that. So the cotangent, let's go and take a second and look over here. Where does cotangent appear? What is going on? You do have a cotangent that appears right there. See? Now you would turn into a cosec, and it's a little bit of a longer process. So let's see if there's a little bit of a different approach that we can do. So give me a second. Let me try to remember, right? Okay, so what I would do, thinking about it a little bit more, is that from here you can leave it as tangent alpha divided by cosine alpha equals 8 cotangent, okay, divided by sine alpha. And so from here, you can now cross multiply. So that means that you end up with 8 cotangent alpha times cosine alpha, right? Equaling tangent alpha times sine alpha, right? Now, the the identity for tan is sine following this. See, it's sine divided by cosine. So you want sine on top, cosine on the bottom. So that means you can do divide by cosine, right? And eventually you end up with, this goes away with this, 8 cotangent of alpha has to equal, this whole thing is going to turn into tangent, right? So that means that on the right side you end up with tangent twice of alpha. Ah, interesting. And so from here, the cotangent, okay, which is something that I didn't mention like thoroughly before, but the cotangent, okay, cotangent is 1 over tangent, literally. Okay, so much how you have um, sec or cosec for 1 over cosine, 1 over sine, you also have cotangent being 1 over tangent, literally. Okay, so that is not in your formal booklet, or not that I've seen. This is the kind of thing you have to know. So much how you have sec for 1 over cosine or cosec for 1 over sine, you do have cotangent for 1 over tangent. So that being said, I come back over here, and the cot, I can just write it as 8 divided by tangent, right? And now we're almost done. Everything is in terms of alpha. It looks much more friendly. So from here, you can multiply by tan to both sides. Multiply and multiply. This goes away with this. 8 equals tangent cubed, parentheses alpha. And so from here, in order to get rid of the cubed, you can go ahead and do square root with base 3, right? So that means that on the right side, or actually, you would end up with just one tan, right? So tan alpha is going to equal 2. It equals 2 because basically right here, you're asking this thing, which number multiplied by itself 3 times gives you 8, which would be 2. 2 times 2 times 2 gives you 8. And so from here, because you want to get alpha alone, because eventually you want it to reach the alpha equaling something, right? You can go ahead and do tan inverse. So you do tan inverse to both sides, tan inverse, tan inverse. You end up with alpha being equal to tan inverse, right, of 2. But I mentioned a long, long time ago that tan inverse is basically the same as arctan. And so this alpha equals tan inverse 2 is the same as saying alpha equals arctan 2. So, ladies and gentlemen, that is how you would show that alpha equals arctan 2. So that was a lot of points. That was 5 points in total between both parts. There's a lot of stuff you have to know, and more than anything, to my judgment, it's being familiar with the formal booklet. So, that is how you do part B, part double I. Alright, you guys, and now for part C, part I, we need to find this. Now this, okay, just so that we're all on the same page, this is really just asking for the derivative, okay? The derivative twice, all right? And so if from part BI, we did the derivative, this is basically just derivative in respects to alpha once. So if this is the derivative once, here we need to do the derivative twice, or you can also think about it as like you're doing it again, okay? And so this is just a very fancy way to say that in respects to this function, you're doing the derivative twice, this time in respects to alpha, and basically again, see? Because in theory, you could do the derivative again, but in respects to a different variable. But what we're always going to face, at least us in this class, all right, or at this math level, as far as I'm concerned, is the same variable again. So you are doing the derivative in respects to L, sorry, in the function L in respects to alpha twice, okay? So from part BI, I have written up here the first derivative, and now we need to do the derivative of this again. And of course, a couple of things arise from here, and the main thing that the IB is trying to test us on from here is what we call the product rule. Now, there's a couple different derivative rules that we need to be aware of, and there's 3 of them. Okay, the one we're going to be using is product rule, but you also have the chain rule. Okay, and the other one that you can also face is what we call the quotient rule. Okay, so I really need to go over these for just a quick second. Now, before we look at the formula booklet and get incredibly anxious because the derivatives look absolutely crazy, let's first understand intuitively which one is which, when to use which. So let's go with the easier ones to understand first. Product rule, following its name, has to do with multiplying. Okay, so whenever you have your variable being multiplied with itself in any way, you should be considering the product rule. Now, I'm not talking about doing the derivative of x times x and ending up with x squared. No, ladies and gentlemen, I'm talking about the product rule when you have something like sine x, so x is on one side, times cosine x. Okay, here you would consider the product rule because you have two x's multiplying each other and they're sort of like separated by something. See, this x squared is not separated by anything. In fact, over here you would actually apply the exponent, just derivative of an exponent. See, derivative of an exponent. It's a little bit different, see? So product rule is something you consider when you have something like sine x times cosine x. Or you have, I don't know, like log x times x. Actually, that would also work as a product rule, see? So be wary of that. You should be thinking of product rule when you have your x's or the variable you're trying to do the derivative of multiplying each other. Okay, so keep it in mind. That is the intuition that I need you to go forth with. For the quotient rule, it's awfully similar, just that you now have dividing. Okay, so instead of having log x times x, it would be something like log x divided by x. Okay, here you would apply the quotient rule. Okay, and last but not least, the chain rule is perhaps the weirdest one, but intuitively it's easy to follow. It's basically just when you have one inside another, okay? So, for example, here I put the example of the sine and cosine. Well, an example for chain rule could be like you have sine of cosine x. And so this x, basically, right, this x is within two different functions. See, it's the same as if you put log and then sine x. Okay, so you have two sort of like functions that are chained together. Okay, you have first the log, then the sine. Okay, here you have first the sine, then the cosine, and notice how x is like deep in there. Okay, so you first gotta go through sine, then through cosine. That's the intuition of the chain rule. It is one inside of another sort of function or whatever. See? Now, the product rule has to do with multiplying, see? And the product rule, once we look at the formula booklet, you will realize that it is pretty crazy, okay? Unless you like study this a lot, you're probably looking at this saying, I'm screwed, okay? You're probably looking at this thinking like, this is insane. I should not have signed up for this, but it's too late. Gotta do what you gotta do, you know? So, anyways, you're probably looking at this. Maybe you have your test in 30 minutes or 30 days. Nobody knows, but you gotta learn this. Okay, there's no other way out. See? And one of the things that I love but also dislike about the formula booklet is that although it does have all the formulas, a lot of times it's not that intuitive. See? And so imagine just for a second that the product rule is rewritten. See? And so the product rule, what they tell you is that it's the first one. I mean, the product rule, you have your two terms, right? Which is the same as if I wrote here sine x times cosine x. See? So u would be sine x and v would be cosine x. Okay? So, how the product rule really works is that first you take first first you take the first one. So, initially you take the first one and you multiply it by the second one in its derivative version, plus the first one in its derivative version times the second one in its normal version. So this, like for me at least, is much easier to follow just like visually. So the first one like sort of normal times the second one with the derivative plus the first one with the derivative times the second one like normal, see, or unchanged, however you want to think about it. And so really this formula that I erased, that's what it's telling you, okay? This symbol that I'm putting here for like its derivative version is that thing right there. Oops. It's, ah, it's that thing right there. Okay, I'm like highlighting everything, damn it. So it's, here we go. It's that thing right there. While over here, the derivative of that guy, ¿cierto? It's that guy right there, okay? So it's all the same at the end of the day, but for me, it's much more intuitive if I think about it like, so the first one normal times the second one with a derivative plus the first one with a derivative times the second one normal or unchanged, okay? And if you really sort of look at it that way, even the quotient rule gets a little bit more friendly, see? And so the quotient rule, I mean, we're not going to use it today, but I do want to like help you understand the formula a little bit better. So just real quick, what you end up with is really, okay, so v, notice v is the denominator, see? So v is denominator, while u is numerator. So really, the quotient rule is telling you that you do the denominator times the numerator being derivatized minus the numerator times the denominator derivatized divided by the denominator squared. So really your derivatives are with the numerator here and the denominator there. So for me, that is a lot easier to follow. I don't know. I thought I would share that sort of tip that yes, the formula booklet is amazing because it has everything, but you do have to understand it in your own way. This is how I understand it. Maybe it helps. Okay? Anyways, enough blah blah. Let's get back to reality. So over here, clearly we have the product rule. Now, as I established earlier, I like to think about it as the first one unchanged times the second one with the derivative plus blah 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 blah. Okay? Yeah, cool. So let's follow the formula like piece by piece. See? So first, and careful with this, first you will do um the product rule on this term, and then you will do the product rule on that term. Okay, so it's two different operations. Let's do the product rule of this first one. So the product rule of this first one means that I have 3 over 4, right? And sec alpha, okay, will be like my u, yeah? So just to be very, very careful, because I know this can get really wild, this is going to be like your u, okay? So this is going to be like your u, and this is going to be like your v. Okay, so just that none of us get lost, this is what I'm following in my head, okay? So the product rule here means that the first one remains unchanged, see? So I end up with sec alpha times the second one in its derivative version. And so the second one in its derivative version, well, I had to do the derivative of tan. Now, nobody knows, at least, yeah, I would say that nobody knows, let's be honest. So nobody knows the derivative of tan. So you open up your formula booklet, blah, 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 find the derivative of tan. Here it is, ladies and gentlemen. So the derivative of tan is just sec squared. So that means I end up with sec squared alpha. All right, so there I did, technically I just did this part here, see? I still need to do this part over there. And so for this part over there, it's the first one with the derivative, see? Oh, and also, sorry, you put a plus in between, see? So you do plus, again the 3 over 4, don't forget it, plus the 3 over 4. The first one being derivatized, so the sec alpha, right, with the derivative. So the sec alpha, what is the derivative of sec? Nobody knows. Check your formula booklet. So the derivative of sec is right there. Look at that, how friendly. So it's really just you multiply by 10. I mean, that's it. You multiply by 10, see? And I know you might be thinking, ugh, this is getting crazy. This is getting nasty. I am ending up with a lot of stuff on my piece of paper. And I'm going to say, yes, you're right. You signed up to AAHL. You got to deal with it, okay? But trust the process, especially for these double derivative problems. And whenever you have a product rule in between, you will end up with a massive answer. Okay, so that's normal. Get used to it, don't worry. So this is the derivative of the first one. See? Now we have to multiply by the second one unchanged, following this here, see? So now the second one unchanged times v. So v we said was just tan, so times tan alpha. Okay, that's what's happening right now. That right there is the product rule of the first one. See, and just so that we're all on the same page here, here's my u, here's my v with a derivative, here is my u with a derivative, and here's my v. Okay, that is what just happened. Now, I gotta do that thing again, but now with this guy. Okay, so of course I'm gonna run out of space, so I'm just gonna put it down here. See, now we're gonna call this the u and this the v. Okay, so once again we have to start with -6 and following this formula over here. So first it's the u times the v with derivative. So the u is going to be unchanged, so I just write down cosec alpha, it stays normal, times the v with derivative. So derivative of cotangent. Do you know it? I don't. So let's go over here. Here is cotangent. Let me double check. Yes, so derivative of cotangent is just going to be, wow, look at that. That's kind of wild. So you end up with negative cosec squared. All right, sure. I mean, I didn't make that up. So negative cosec squared alpha. Trust the process. It's gotta be what it is, right? So, yeah. So here I would have the u, and here I would have the v. See? Now you gotta do the plus, correct? Now you gotta do the plus. And following over here, now it's the first one with derivative times the second one unchanged. So the first one with derivative is derivative of cosec. Do you know it? No, you don't. Go to the formula booklet. Cosec is right there. So cosec ends up as this crazy thing. So it's the same cosec but with a negative, and you multiply by cotangent. All right. I mean, what the heck? See? So I put the plus, but I still start with the -6. So it's -6 times -6 cosec alpha times cotangent alpha. Yeah, so this right here that I just put is derivative of the first one, see? Times the second one unchanged. And so the second one unchanged is just going to be cotangent. So there is the second one unchanged, okay? So I know that was kind of confusing because it is confusing. See, so if you got lost at some point, like make sure you double check, you review, etc. Product rule is confusing you guys. See, so practice it a couple times. For me, it helped a lot to understand that first I changed this, the second one not, then the second one gets changed, but the first one not. See, stuff like that. Just practicing it a lot, seeing a lot of examples, and doing this a lot of times, so you really understand the logic behind it, is key. Okay, understanding why it works the way it works, or the pattern that is like behind it is huge. Okay, that's the best thing you can do for yourself. See. Now, obviously it's the AB, so you gotta leave your final answer at least in a nicer way. Or at the very least, it's convenient to like group it together for down the road, see? So, for this guy here, what you end up with is 3 over 4. You can find the sec, you combine the sec, so it's 3 over 4 sec to the power of 3 alpha. For this next term over here, right, you can combine the tangents. So you end up with plus 3 over 4 sec alpha times tangent twice, or tangent squared, see? Next, we can move on to this one here. So boom, you can do that one. Clearly, you have 3 cosecs going around. You do have 2 negatives though, so careful with that. You do end up with plus 6 cosec cubed. And this last term, I'm probably going to run out of space, but this last term is right there. Notice how you have a plus and a minus, so it's plus minus. So it ends up being negative. See, so here now you do minus 6. Okay, I'm definitely going to run out of space there. See, it's fine. No harm done. Minus 6 cosec alpha and cotangent twice. See? So there is my final answer. Here is the second derivative of my function. And let me just show you the mark scheme just so you believe me, believe this guy on the internet. You end up with a pretty crazy long answer, and it's right over here. See, so as you can see, you end up with the 3/4 sec tangent twice. So here's the sec tangent twice. The sec 3 times, the sec 3 times. Then over here it's 6 cosec cotangent twice, 6 cosec cotangent twice, and last but not least, the cosec 3 times. See? Now, small mistake that I've committed, which we will find together because it can happen to anyone. I'm leaving it in the video because learning moments are all around, especially when I make a mistake. Here's a negative, and here is a positive. So where did I mess up? What happened? This can happen to anyone. So clearly, I must have messed up somewhere on the derivative when I was doing the derivative of cosec. See, so when I was derivatizing cosec, what the heck happened? So when I derivatized cosec over here, well, let's take a moment to understand what happened. So the derivative of cosec, as you can see, and now I immediately see my mistake. So the derivative of cosec is that this cosec ends up with a negative in front. See? Now, I kind of got confused because there's already a negative here. So what I should have done is that I do plus minus 6, and then here I needed a negative cosec. See, so following the formula, it would have been like that, technically. And so that means I have the plus, the negative, 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 plus. This should have been a plus. See? So small detail, I am leaving it on the video because it can happen to anyone. And I mean, what better learning moment than you messing up? See? That's life. We only get better with time. Mistakes happen to anyone. Take it easy. See? So, anyways, small mistake. There's my plus. Bada bing, bada boom. See? So, wow, that was crazy. But it is worth 7 points. So, fair is fair, right? Then they tell us that when alpha equals arctan 2, show that this equals that. Now, this next part, you guys, is very big brain. Like, I'm just going to tell you right away, it's very big brain. There's a lot of stuff you need to understand. There's a lot of context you really need to swallow for this to really make sense. Okay, so let's try to go piece by piece as safely as possible. So right now you have sec, you have tan, you have cosec, and cotangent. So we have sec, right? We have tangent, right? We have sec, we have tangent, we have cosec, and we have cotangent. We have cosec, and we have cotangent. And so apparently from this, okay, because they tell us that alpha equals arctan 2, I should reach an actual value. So why am I setting it up this way? Notice, my current derivative has a sec, has a tan, has a cosec, has a cotangent, and all of these, you guys, disappear. Like they get consumed, they get turned into an actual number, and if you add up all those actual numbers, you end up with this right here. How do I know you end up with this right here? Because it says show that. So you have to reach that. It's a fact. So how the heck from here do you somehow get rid of all of this, turn it into numbers, and end up with an actual value? Okay, that is a massive sort of concept jump we have to go for, and let's try. See? So first things first. Why is it so useful that alpha equals arctan 2? See? I did go over that a little bit before earlier in part B, part double I, but basically, how do you reach an arctan? Well, arctan, you guys. So arctan is the same as if you were saying tan inverse. Okay? So that means that that technically right here, see, at least for me it's easier to understand. So right here you have tan inverse, right? So that means the step before this meant that you had tan on the left side. So before this, right, that means you had tan here equals 2. So really, um, knowing that you have that alpha equals arctan 2, right, which is the same as just tan inverse, you can apply like tan on both sides or something like that. I'm sure it works like that because it's an inverse, see? And you end up like figuring out or whatever that tan alpha equals 2. Okay, that's the big sort of thing that's happening. See, so tan alpha equals 2. And so this actually helps you because now, so all the tan alphas have to equal 2. Now, how in the heavens is that ever going to help me out for sec, cosec, and cotangent? Okay, that is the big challenge that is happening now. And so, what is the formula of sec, cosec, cotangent? The formula of sec, for example, if you go to the formula booklet, because once again, the formula booklet got like everything. So go to topic 3, not topic 5. It's not a derivative anymore. Now we're talking about trigonometry and stuff like that. See? So for HL, because we're big boys now, big team, yeah, we are full grown adults doing big important things called IB Math HL. See? Um, Notice, so sec is just 1 over cosine. See, so let's go ahead and write that. So sec alpha is just 1 over cosine alpha. See, we're not sure how it might help yet, but let's just write it down. See, cosec on the other hand, so cosec is just 1 over sine. Yeah, cool. So this is 1 over sine alpha. Well, cotangent, I'm not sure if cotangent is here. I think it's not. But cotangent is very similar to the inverse. It's just telling you 1 over tangent alpha. See? So cotangent alpha is just 1 over tan alpha. See? All right. So why would this be useful? It's useful because in trigonometry, and this is huge, you guys. So I'm actually going to write it down over here. See? So in trigonometry, you do not care. This is very important. You do not care about the lengths of your triangles. You only care about the angles and this is a hugely important word and concept, proportions. And so, because you don't care about the lengths of your triangles and you only care about the angles and the proportions, this is actually a massive amount of information for understanding the proportions of this exercise. Bear with me for a moment. So, tangent, you guys, we know comes from SOHCAHTOA. So, SOHCAHTOA, as I mentioned earlier, for sine, right? So for sine, the SO is going to be opposite over hypotenuse. So this is for sine, see? I'll just, whatever. So this is sine, right? For cosine and for tangent. So for sine, you have opposite over hypotenuse. For cosine, you have adjacent over hypotenuse. And for tangent, you have opposite over adjacent. So what's the big deal here? Basically, because alpha, whoops, because alpha, see, tangent equals 2, you can basically say, right, you can basically say that opposite over adjacent equals 2. Now, because you do not care about lengths of triangles and you only care about the angles and proportions, from here you can think about, okay, so opposite divided by adjacent has to equal 2, so the most obvious explanation is that opposite equals 2 and adjacent equals 1. And there might be a part of you sort of like protesting me saying, can't you say that opposite equals 4 and adjacent equals 2, and you would get the same answer. And on the one hand, I would say yes, and you can actually solve it like this, and you will get the right answer, I promise you, only because you do not care about the lengths of the triangles, only that the proportions and angles are appropriate. And so, yes, you can solve it thinking about it like this, but might as well pick the friendlier version, right? So opposite is 2, adjacent is 1. As long as it makes sense and you follow through with these proportions, okay, you will be okay. So, you're now establishing that the opposite equals 2 and the adjacent equals 1. Now, if I were to try to plug it in for SOHCAHTOA, right, I'm not quite there yet because I still need to figure out what hypotenuse is before actually using any of these formulas. And why would you use these formulas? Because it would help you define sine and cosine. And if you define sine and cosine, suddenly, boom, you unlock this. Boom, you unlock this. And boom, you already have that, actually. So, that is why we're doing what we're doing. See? Figuring out sine and cosine helps you figure out sec and cosec. And how can you do this? Well, because tan equals 2, that means you have a proportion of opposite and adjacent equal to 2. And since you do not care about lengths of triangles in trigonometry, only about angles and proportions, you just say that the opposite equals 2, adjacent equals 1. How do you get the hypotenuse from here? Well, technically, right now you have a triangle that you know has alpha here. See? And you know that in respect to alpha, you have an opposite of 2 and an adjacent of 1. So what's the hypotenuse? Will you look at that? Will you look at that? So Pythagoras theorem, a squared plus b squared equals c squared. 1 squared plus 2 squared equals hypotenuse squared. 1 plus 4, cierto? 1 plus 4, I'll just write it out, who cares? So 1 plus 4. So hypotenuse squared equals 5. Hypotenuse, ladies and gentlemen, equals square root of 5. And so, boom, hypotenuse equals square root of 5. It's gotta work. It's gotta work. We are definitely onto something. Da, 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 da. It's kind of exciting, I'm not gonna lie. So, this means that for sine, okay, this means that for sine, let me make a little bit of space, okay? So, right now, the proportions that make this make sense is that opposite is 2, adjacent is 1, and hypotenuse equals square root of 5. And so if you go ahead and plug in, that means that sine alpha equals opposite over hypotenuse. See? So it means that sine alpha is 2 over square root 5. That also tells you that cosine is adjacent over hypotenuse. So adjacent over hypotenuse would be adjacent over hypotenuse. It would be 1 over square root 5. See? And so now you can plug in up here knowing that information. So following this line, you have 1 over cosine alpha. So you have 1 over, well, cosine alpha is 1 over 1 over square root 5. See? I'll explain how to solve that in a second. Tangent alpha equals 2. Cosec is 1 over sine alpha, cierto? Sine alpha is 2 over square root 5. So here you have 1 over 2 over square root 5. See? And this last one is just 1 over tan alpha. Well, tan alpha is more straightforward. Tan alpha just equals 2, so this is the same as 1 over 2. See? So this one is already sort of like completed. Cotangent, right, is going to be 1/2. See? So this is for cotangent. That one is already done. Tangent alpha is also already done. Now we need to finish clearing up these weird sort of fractions. So these fractions, you guys, there's a couple of different ways to think about it, and what I suggest, or my approach really, is that you want to have two fractions on top of each other. See? For me, it's easier to think about it. So if up top you have a 1, that means up top technically it's just 1 over 1 divided by 1 over square root 5. See? Well, here down here you have 1 over 1 divided by 2 over square root 5. Now from here, what I like to do is just that when you reach this sort of scenario of two fractions on top of each other, resulting in one big sort of fraction here, cierto? The way you solve it is, well, technically, if you have a over b divided by c over d, it's the same as saying a over b divided by c over d. See? And because you are dividing fractions like this, you gotta do the reciprocal for multiplying. See? So this, you must have learned at some point, turns into this. So you flip the c and d, right? So that is one way you can sort of think about it and reach that. The other way you can think about it, which is what I love to do, is you do the edges multiplying each other and the middle ones multiplying each other. Okay? So basically here you end up with 1 times square root 5 divided by 1 by 1. By 1 over 1, sorry. See? So just square root 5 is going to be sec alpha. See? So sec alpha is going to be 1 over square root 5. See? Meanwhile, the cosec, we have 1 times the square root of 5, so just square root of 5, divided by 2. That's my final answer. So cosec is now going to be square root of 5 divided by 2. And so now you can plug everything in, and notice there was a lot of information hidden in this arctan. See? The main thing, I mean, really, I feel like this is a kind of exercise that you face one and you're prepared for it forever. This is just the kind of thing you have to know. See? So in trigonometry, you do not care about lengths of triangles, only about the proportions. So if they tell you that you have alpha equals arctan 2, that means you have tangent of alpha equals 2. And that gives you so many different proportions over here. It lets you get the hypotenuse, etc., etc. And you can just sort of plug everything in, right? So be wary of that. Be conscious of that. See? Yeah. Damn. Okay, that was a lot of stuff. So over here, let me just write somewhere, I guess. Let me just write that sec. Let me use a different color. See? So we know that sec alpha is, just so that I'm not scrolling so much. So sec alpha is square root 5. Square root 5 tangent alpha equals 2. Then I think it was cosec. Yeah, so cosec is going to be square root 5 divided by 2. So cosec is going to be square root 5 divided by 2. And last but not least, you have over here that cotangent is just 1/2. Yeah, cotangent is just 1/2. Okay, cool. So if you go ahead and plug in all of that stuff, on the one hand, you end up with 3 over 4 times this sec cubed. See, so sec, we said was square root 5, so you end up with square root 5 3 times. We'll see what happens there. See? Plus 3 over 4 times sec, right? Sec alpha, which we said was square root 5, times this tangent twice. So times just 2 squared. That's a little bit more friendly. Plus 6 times cosec 3 times. So cosec cubed, basically. Plus 6. So there I just did this. See? Now I'm doing 6 times cosec once. So cosec is square root of 5 divided by 2. Times cotangent squared. So cotangent is 1/2, right? 1/2 squared because of this squared. See? So just follow the procedure. Take it easy. I know it's a very long line of math. But hey, this is worth 7 points for a reason. See? So keep going. We finally got rid of all the sec, tangent, cosec, and cotangents, and blah, blah, blah. See, right? So now we can really try to solve it and see what the heck happens. So for this first term, you can end up with 3 over 4 times, think about it this way. So if you have square root 5 3 times, that means you can do it twice. See? So you can do square root 5 times square root. Actually, just you can write it out, ¿cierto? And you know that this has to be, this is square root 25, right? So this is square root 25 times square root 5. So really you end up with 5 square root 5, right? So you end up with times 5 square root 5, correct? Plus 3 over 4 times 4 times square root 5, 4 because of this guy, see? Plus, and I'm actually going to go down here because I'm running out of space. Sorry, guys. 6 times that whole thing cubed. So really, this whole thing cubed is square root 5 divided by 2 times square root 5 divided by 2 times square root 5 divided by 2. So on the one hand, you will end up with an 8 on the bottom, and up top, the same as here, you end up with 5 square root 5. So here it's 5 square root 5 divided by 8. Yeah, so 5 square root 5. And then this last term is going to be plus 6. It's just square root 5 divided by 2 times 1 half times 1 half. So it's going to be 8 on the bottom. So you end up with square root 5 divided by 8. So square root 5 divided by 8. Okay, this looks kind of crazy. I'm not going to lie. But we're not done with multiplying and everything yet. See? So let's keep going and just see what happens. Okay? So on the one hand, this first term, right, you end up with 3 times 5 up top. So it ends up being 15 square root 5 divided by 4, right? Now, especially when it starts to get kind of weird or you're not sure how you should be solving, what's the smartest way, well, what do you need to reach? So you need to reach 45 divided by 4 times square root 5. So you're not going to be getting rid of all the square root 5s, which is actually like a good thing to know. And also notice the denominator has to be 4. So let's focus on leaving the denominator on 4 and everything should start to flow. So here's for this first term. Now we do this second term. We have 3 times 4, correct? So you end up with 12 square root 5 divided by 4 plus, now this term here, ¿cierto? So it's 6 times 5, right? So that gives me 30 square root 5 divided by 8 plus, this one is just 6 square root 5 divided by 8. See? Now, as I said, you do want to leave your denominator as 4. That's probably going to make everything a lot more friendly. So on the one hand, you can immediately combine these two guys. So these two guys will turn into 27 square root 5, because 15 plus 12, ¿cierto? Divided by 4. This next term, if you simplify it a little bit, you actually end up with, you can divide by 2 on the top and bottom, see? So 30 divided by 2 gives you that 15. 8 divided by 2 gives you that 4, which is what we're going for. And here you divide by 2 again in order to get a 4. See, so you do 3 square root 5 divided by 4, right? Now you combine everything. So this 27 plus this 3 gives you 30, plus 15 gives you 45. 45 divided by 4 times square root 5. Ladies and gentlemen, that exercise was crazy. I'll be honest. Part C qualifies as illegal in many countries, I'll be honest. Okay? All right, you guys. That is for part C, part double I. All right, you guys. So now we will go ahead and do parts DI and part D double I. And so for part DI, we have that we need to hence, this is an important word, so hence, so given everything you just found, hence justify that L is a buzzword minimum when we have that alpha equals arctan 2. So this has a lot to do with interpreting how derivatives work, how the double derivative works, and stuff like that. And so let me do a quick 101 in regards to that. For example, with a quadratic, okay? Let's imagine you have a quadratic that goes like this, okay? When you do the derivative, okay, so when you do the first derivative, yeah, and you equal it to 0, what you're actually doing is asking the function when is the slope equal to 0. Now, why would it be relevant to find where the slope is equal to 0? Well, in this diagram that I just drew here, where is the slope 0? And so over here, it's growing by like a lot, right? And so this slope, I would call it like, I don't know, 4. See? Over here, just a little bit more over to the right, correct? A little bit more over to the right, you have a slope that it's a little bit less now, right? So it's growing at a less of an increased speed or whatever. So here it's growing at, let's say 3. If the other one's 4, this one's 3. And if you keep going with this idea, okay, over there it would be, I don't know, I'll make it up. Like now it's like 1, okay? Well, where is it a slope of 0? Da da da. Let me use this color here. Boom. Right there. You have a slope of 0. And so the reason that you want to equal your first derivative to 0 is because it helps you find where in your function, okay, you have a slope equal to 0. So basically, when you do this move right there, okay, you're finding the x value. Okay, you find the x value that gives you when the slope is 0. Okay, that is why on part b double I, when you equal the derivative to 0, okay, this is basically what you're doing, see? So you equal your derivative to 0, and you find out that the x value that makes it have a slope of 0 is alpha equals arctan 2. So in this exercise, when alpha equals arctan 2, that is where you have your optimal, see? Your minimum or maximum. And so there's the next question. How do you know if this is a minimum or a maximum? Because technically, you have a slope of 0 when it's a maximum like this, but you also have a slope of 0 when it's a minimum like that. And so how the heck do you confirm or find out whether it's a maximum or a minimum? And so here's the next piece of information that you will be learning for today. We know that we first established that if the first derivative is equal to 0, you will be finding the x values where you have optimums, right? Like a max or a minimum. It's optimization, see? For this one on the left, which I will be doing in green, okay, so for this one on the left, you use the second derivative to find out, okay? You use the second derivative to find out if you have a maximum or a minimum. And so the second derivative in this case is going to be negative. And so think about it this way. The second derivative, okay, the second derivative is telling you, how do I put it? Like, whether your rate of change or slope is getting more positive or more negative. So the second derivative is telling you whether your rate of change or slope is getting more positive or more negative, okay? So in this case right here, you would have a second derivative that is negative, okay? Their second derivative would be negative because clearly one slope over is like one x value over, you suddenly end up with a negative slope. And so that is why the second derivative for a maximum is negative. So for a maximum, right, first you're going to have a derivative equal to 0 for that maximum, and the second derivative has to be negative. All right. Following the same idea for a minimum, which is what we're about to find out, you also have the first derivative equal to 0, and the second derivative, you guessed it, has to be positive because one, now I'm going to do it in dark green, ¿cierto? Because one x value over, for example, right over here, see? Right there, you have a slope that is positive. So, okay, that makes sense. The second derivative for the minimum, okay, has to be positive. All right. So once again, the biggest thing I can sort of teach you or explain is that the second derivative is telling you whether your rate of change, in other words, the slope, is getting more positive or more negative. So once you reach the maximum, okay, once you reach the maximum, from here to the right, you end up with a bunch of negative slopes, right? So that is why the second derivative has to be negative. While for the minimum, once you reach the minimum right here, one unit to the right already has a positive slope. So that is why the second derivative has to be positive. All right, so now once we understood that idea, we can fully jump onto part DI. Here we need to justify that L is a minimum when alpha equals arctan 2. So we already discovered from part B double I that when alpha equals arctan 2, you have a max or min Okay, because you equaled your first derivative to 0, you found out that it was a max or min. You found out that it was thing, like a point of optimization. Okay, there's a lot of different ways that I can sort of try to explain this. Optimization, you can think about it as a vertex. You can think about it as a changing point. So for example, if your function goes something like this, right? So your function goes something like this. Well, you found the changing point. You just got to find out if it's a max or min. Maybe you have a function that goes like that. You found all of these. Are each of these a max or min? Okay, that's the kind of thing we have to discover. So, point is, you know that at alpha equals arctan 2, you have a max or a min. The big question now is whether it's a minimum or a maximum. Here they actually give you the hint, yo, it's a minimum, right? But justify it. So how do you justify it? And so the way to justify it is that remembering that this guy on the internet told you that when you have a minimum, the second derivative has to be positive, because when the second derivative is positive, that means your slope is increasing, right? And so if your slope is increasing 1 unit over, that means it has to be a minimum, because boom, it's starting to go back up. See? All right, that makes a lot of sense. And so all you really have to do for part DI is actually using this part that says show that. You can just say that, the second derivative, okay, this is the same as the second derivative, right? The second derivative is 45 divided by 4 square root 5, which you know for a fact is greater than 0. And so that would be your justification for part DI. Yes, it is that simple, but you do have to know this whole interpretation thing. See? So for interpreting minimums and maximums, make sure you write this down somewhere. Okay? Personally, I love this diagram here along with this written next to it. See? Easier to remember, whatever floats your boat. That is my approach. Okay? That being said, we can now keep moving on to part C double I. And so part C double I now asks us to determine this minimum value of L, right? Now, let's go piece by piece, see? So, there's been a lot of stuff happening here. So on the one hand, we started with f of x, okay? Then we had the first derivative, and then we had the second derivative, see? So let's really try to organize what means what in this case, see? So the first derivative, the buzzword we will be thinking of is that it's for slope, okay? The second derivative, the buzzword that we will be thinking of is like figuring out if it's a max or min, okay? That's pretty much why you would use the double derivative, okay? And the original one, of course, is just for finding like xy coordinates. See? Technically, all of these have a xy associated to it, but you know what I mean when I say xy coordinates, like actual points that go in your graph, whatever. See? So this is actually for finding your x and y's. See? So the minimum value of L, well, for your minimum value of L, my function up here is L equals that whole thing. See? So really what you have is that you have a function of L in respects to some alpha or angle that you're plugging in. See? So when your angle equals arctan 2, what is this length? And when alpha equals arctan 2, you're going for a minimum. So basically, plug in alpha equals arctan 2 in order to find the minimum value for L over here, right? Now, as we saw in part CI and double I and all that stuff, we did establish that having an alpha equals arctan 2 gives you a bunch of information. So, just a quick recap, all right? When alpha equals arctan 2, it's the same as saying that tangent alpha equals 2, right? It's the same, right? Tomato, tomato, potato, potato. So, when you have that tan alpha equals 2, and you recall for a second that tan is for TOA, right? So opposite over adjacent, you can immediately establish, well, what's the most friendly version of tangent alpha equals 2? You will quickly conclude that the opposite equals 2, that adjacent equals 1, and the hypotenuse equals 5. Just for a quick reminder, or anyone that is skipping over to this part, basically what you're saying is that this is angle alpha, Your opposite has to be 2, your adjacent has to be 1, and so for the hypotenuse, what you can do is 1 squared plus 2 squared equals hypotenuse squared, right? And that is how we find that hypotenuse has to be square root of 5. And you might be thinking, okay, how do you find that the opposite is 2, the adjacent is 1? Couldn't you also say that the opposite is 4 and the adjacent is 2? Wouldn't it also work? And I would say yes, it would also work. But all that really matters in trigonometry is the proportions between your sides and your angles, not the actual distances, only the proportions. So pick the friendliest one. When they tell you that tan alpha equals 2, just pick opposite to adjacent 1. Why is it the friendliest? Because you have a 1 for adjacent. That's pretty much it. See? Enough blah blah. So from here, you can now sort of start plugging everything in. See, so on the one hand, because we need to put alpha, right? I mean, because we need to apply the alpha equals arctan 2 into this equation down here, right? For finding my minimum value of L, well, here you have sec alpha and cosec alpha. And from the formula booklet, you can leave this a little bit more friendly. So you can leave it a little bit more friendly by saying that sec alpha is just 1 over cosine alpha plus 6 times cosec alpha, which is simply 1 over sine alpha. See? Now, you know from some point in your life that sine theta is the same as so, ¿cierto? So is going to be opposite over hypotenuse, and you also know that so cosine, okay, is the same as ka. So that's going to be adjacent over hypotenuse, okay? So now if you plug that in, you end up with 3 over 4 times 1 over 1 divided by cosine alpha. So cosine alpha is going to be just adjacent over hypotenuse plus 6 times 1 over 1 to make it a big fraction divided by sine alpha. Sine we said was opposite over hypotenuse. See, so now suddenly becomes a lot more friendly. For finding this minimum sort of value, all you really have to do is well, you're like plugging in the fact that alpha equals arctan 2. See, and so what you end up with is 3 over 4 times 1 over 1 divided by adjacent over hypotenuse. So adjacent is 1, hypotenuse was square root of 5. Plus 6 times 1 over 1 divided by opposite over hypotenuse. So opposite we said was 2, hypotenuse square root 5. So 2 divided by square root 5. Now I like putting it in big fractions because you can do this sort of visual trick. I just really like visual approaches. So it's this times this, right? So you're going to end up with this times this gives you square root of 5 divided by 1 times 1, so just 1, plus 6 over 1 times, well, this times this gives you square root 5, and this other one gives you 2. See? So now, because it's just fractions multiplying, you do it straight across. So 3 times square root 5, it's just going to give you 3 square root 5 divided by 4 times 1. So just 4. Plus, you do the same idea over here. So this times this is going to give you 6 square root 5 divided by 1 times 2. So quite simply 2. Now you have fractions here, so you want to make sure that you can combine them as much as you can. Because you are adding fractions, you need the denominators to be the same. So what you end up with is 3 square root 5 divided by 4 plus, here you multiply by 2 on the top and on the bottom, so that you get that times 4, see, on the bottom. So you end up with 12 square root 5 divided by 4. You add all of this, you end up with 15 square root 5 divided by 4. See? So basically what you found for part D double I is that the minimum value of L, so L min, okay, is going to be 15 square root 5 divided by 4. Okay, and just to double check, because these exercises are a little bit infernal and hard, there it is, 15 square root 5 divided by 4. All right, awesome. And now for the last part, we need to do this thing that says Two people need to carry a pole of length 11.25 meters from the passageway into the room. It must be carried horizontally. And so we need to determine whether this is possible, and give a reason. Okay? Now, this is interesting. Over here, it's worth 2 points, right? And so because it's asking for you to give a reason and see if it's possible, on the one hand, you probably have like a reasoning point of figuring out if it's possible or not. And then you have to give an argument. That is why it says give a reason. Okay, so you need to figure out a way to get both of those points. Okay, don't just put the math, also maybe put a little bit of writing, etc. Blah, blah, blah. See, it doesn't have to be long, it doesn't have to be a paragraph, but just whoever's evaluating you needs to understand your thought process. Okay, that's the whole point of method points and all the and reasoning points and this or that. They have to understand what you're thinking of. Okay, they have to be able to follow that. So for this last part, really, we just need to understand a lot of context. See, we need to really sort of absorb. Okay, we need to absorb a little bit, like everything this exercise has been throwing at us lately. Okay, so let me make a little bit of space. So here we will be working for party. Okay, so first things first. In this exercise, we did find out at some point that you have a minimum or maximum when alpha equals arctan 2. We discovered that right there, it was a minimum. Now alpha, let's recall, alpha is this angle. So really what you're finding, okay, is that that is the minimum angle for you to be able to have this line AB. And that right there is very important for you to understand. So we just discovered through all of this exercise that when alpha equals arctan 2, this line AB can exist. So that is the minimum angle you need for this like sort of side to exist. And so you also discovered that when that happens, L minimum, right, equals 15 square root 5 divided by 4. See? That is the distance of AB. Like the minimum length it ends up being in order for that angle to like sort of exist or whatever. See? So basically, now two people show up and they say, okay, we need to pass through this passageway, right? And into this room. And so they're carrying a stick that is 11.25 meters long. And so they're carrying this stick that is 11.25 meters long. And basically, they need to put it into the room. And so they're going to start shifting it slowly, and they're going to try to reach a scenario where you have a horizontal line, because they do say that you need to carry it horizontally. Now, evidently, at some point, it will also end up like line AB. It will be superimposed on it. It will be right on top of it. And so at some point, what you really need to evaluate is, okay, so this pole, when it reaches this position, is it slightly longer than what it should be? Okay, so in other words, what I'm saying is that if it's, for example, larger than 15 square root 5 divided by 4, it won't fit. That's what I'm telling you. That is what I just drew over here. But if you end up with a pole that's a little bit shorter, so for example, a pole that is, I don't know, until there, so here's a bunch of like extra space that they can take, then you would say if it's actually less than the L min, so less than this, well, of course it will fit. Okay, so that is the sort of mentality we need to go over. That is what we're facing right now. Now, they did tell us that the pole, so x, right? So x for pole, I say x because it's the example used here and here, see? So for x, the pole, we established that it is 11 11.25 meters. Now, and this just gets very sort of like creative and it's very specific, but once you realize the approach, it turns out to be very friendly. So you know that the pole is 11.25 and you need to be able to compare it to, okay? You need to be able to compare it to the 15 square root 5 divided by 4. You need to. There's no other way. Like, and because you don't have a calculator for this paper one, because you don't have a calculator, you need to find a way in order to make them comparable. So how the heck do you compare 11.25 to 15 square root 5 divided by 4? How the heck do you make these two numbers more similar to each other? So on the left, you have like more of a normal number. It's a decimal, like whatever. See? On the right, you have this crazy square root. Now, this square root, can you simplify it? No, you can't. And so on the one hand, one approach that you can sort of eyeball, and it, to my knowledge, it would be good enough. You would think about, okay, what are the perfect squares that are between this? And so between this, you have the perfect square of 4, and you have the perfect square of 9, because here you have 2 squared, here you have 3 squared. And so from just that, you can sort of approximate and say, okay, yeah, I mean, square root 5 is pretty much, it's less than 3. Okay, you can establish that it's less than 3, and that's probably good enough. So you can call this like, I would say it's like 2.25 or something. See, just to make the math a little bit easier, I'm just gonna go ahead and say that it's 2.5. See, realistically, you would approach it in a different way, but you can say that, okay, it's pretty much 2.5, so you can say 15 times 2.5 divided by 4. You still have 11.25 on the left. You can end up with, this would end up being, well, of course, you're an HL, so you do quick maths faster than this boomer, but you do end up with 30 plus 7.5. So you end up with 37.5, if I'm not mistaken. Claro, that makes sense, yes. Divided by 4. And so which is bigger, 11.25 or 37.5 divided by 4? Now you know that this divided by 4 has to be less than 10 because 40 divided by 4 is 10. And so this has to be 9 something, okay? I'm sure you can do the math on your own and you'll figure it out, but basically you would end up concluding that 11.25 is actually bigger, okay, than like around 9, okay? And so that would be your justification to say that the pole would basically not fit, okay? You would be discovering that the 11.25 is a little bit bigger than the 9, okay? So that is one argument, and the main reason that would apply for your answer is this right here. So make sure you write it somewhere so that the guy evaluating you or the person evaluating you knows what's going on. So that is one way to do it. Now, I'm going to show you one more way to do it because I know some of you are probably not convinced by this. See, you're probably telling me, you're estimating, you're eyeballing, I don't like it. Although it's good enough, I'd rather show you another way because why not? We got the time. See, and you're still sticking around, you're still in this video, so hey, might as well learn something. See? So, the other sort of approach that you can do, okay, which starts from the same sort of like thought process. And so it starts from the same thought process because essentially what is troubling you in order to compare these two square roots, okay, is that you have a square root 5. And so it's just hell annoying, like what do you do, etc. See? And so try to replicate the number on the left to be as close as possible to the number on the right. Okay, clearly making it the other way around, we ended up putting that square root 5 was around 2.5, which is not even close. It's actually like 2.2, I think. But, but, so I lost my train of thought for a second, but essentially you either try to make this one more similar to that one, or you try to make that one more similar to this one. So now I'm going to show you that alternative, making the 11.25 as similar as you can to the one on the right. So one thing you can sort of notice is that here it's being divided by 4. So that means you can take the 11.25 and amplify it by 4 over 4, right? This is legal because amplifying or multiplying by 4 over 4 is the same as multiplying by 1. And if you multiply any number by 1, nothing is going to change. 4 over 4 is the same as 3 over 3, is the same as 2 over 2, is the same as 1 over 1. it's all just 1. Okay, you are multiplying by 1, nothing is really changing. So 4 times 11.25 gives you 45. So look at that. So up top, you end up with 45 divided by 4. So now you're comparing 45 divided by 4 to 15 square root 5 divided by 4. See? So now you get a little bit closer to comparing it. Up top in the numerator, you have a 15. So how can I try to get that 15? Well, here, you know that 45 has a multiple of 15. So you can actually put it as up top, ¿cierto? 15 times 3 divided by 4 versus 15 square root 5 divided by 4. And now the last thing you need to try to make it comparable is this 3 to this square root 5. So, well, this 3 is actually pretty convenient because, well, square root 9 equals 3. And so that is a little bit more of a big brain move, but what you end up comparing is 15 times square root 9 versus 15 times square root 5. And so you can immediately say, well, because square root 5 is less than square root 9, you know for a fact that the number on the left has to be bigger, because the only thing that is different from both of these numbers is that the one on the left has a square root 9, while the one on the right has a square root 5. Which one is bigger? Square root 9. So the one on the left has to be bigger. Another important thing to mention, I suppose, is that it is multiplying in the numerator. If it were multiplying in the denominator, then yeah, a bigger number in the denominator makes it smaller. In this case, it's a bigger number in the numerator, so it's going to be a bigger number in total. See? So that would be your sort of argument. Guys, I did forget to mention, in order to get full credit, make sure that on this step here, okay, just to show that you understand your thought process and that you understand what you're doing, on this step here, you say the pole could not, right, pass horizontally, which is really the same that I put over here. Like, if it's this, it won't fit. If it's this, it will fit. Make sure you write something like this. Okay, I was checking the mark scheme because I do want you guys to get like full credit. And so basically, this mathematical sort of argument is 1 point. It's your reasoning point. But the other point is literally like concluding what that means. Okay, it's giving you one answer point. All right. It's not so different when you find your p-value and this or that, and then you need to conclude the test. The same idea happens here. So this is the logic that you're following, and you do need to show you that you understand what this means. It means that the pole cannot be carried horizontally from the passageway into the room. So make sure you do that. I forgot to mention it, so it might look a little bit awkward in the editing, but I do want you guys to know because, yeah, whatever, okay? So that is another sort of argument that you can use for part E. I think both approaches work, and we ended up doing it all up top. I don't know why I put this E down here. So, ladies and gentlemen, that would be for number 11, and I will say that number 11 is pretty crazy. Okay, there's a couple things you just have to sort of know. I think the biggest thing that you gotta, like, really conceptualize is this whole max or min thing, and also, worth mentioning, this stuff right here. This stuff right here is huge, and without its knowledge, you actually can't move forward. So remember, in trigonometry, you only care about the proportions. If they're giving you one, use it, and use the friendliest version. Hopefully have your adjacent equal to 1, or whatever. See, ideally have something equal to 1 if you can pick the proportion. See, or smaller numbers better. That's pretty much it, okay? And last but not least, and this is more of a general sort of tip, this exercise had a lot of situations where they told you show that. See? And so with all these show that's, okay, you can actually skip a lot of these steps. Now, if you skip a lot of these steps and parts, there's a bunch of points that you're missing out on. That is true. But if you're running low on time and you realize that you have an exercise with a bunch of show that's, you can actually skip over to, for example, part DI. See? So part DI actually needed like nothing that you needed to do from part C or B or A. All you actually had to do was use all the show that information. Okay, so this, you know that you have maximum here. You know that the double derivative gives you that. You can just sort of like plug in, see? I mean, literally, think about it. For part di, all you had to do was say, this is greater than 0. Easiest 2 points of your life, see? For this minimum, well, you just gotta plug in the fact that you have alpha equals arctan 2 into this guy right there. So this is all straight from the exercise, nothing new coming out, see? So really watch out for that kind of stuff if you're running low on time. Otherwise, that tip doesn't really apply, okay? So enough has been said. Definitely enough has been said for this exercise. It was pretty crazy, but I'm proud of you for trying it because, I mean, it's literally worth 19 points. Like, come on, are you kidding me? This part is worth 7. This part was violent, you guys. It was nutty. Anyways, good job. I'm proud of you. I'll see you around. Alright guys, so for number 12, it will be a sort of vector problem. So, definitely not our favorite, but you gotta do what you gotta do. So, two lines L1 and L2, which are shown here and here, intersect at point P right there. Point A, which has coordinates of 2t, 8, and 3, as shown right here, where, and this might be important down the road, the IB, whenever they give us something, it's probably because it's relevant, where t is greater than 0, lies on L2. This is shown in the following diagram. Now, first things first, just a quick reminder, don't freak out. If you have a point with 3 coordinates, that means that instead of dealing with an xy plane, you're dealing with an xyz. So you probably have something that looks kind of crazy with a z value going up like that. Okay, so it does enter like a more 3D-ish sort of plane. But, I mean, especially for vectors, this is something that we have to work around with quite a bit. So, they also tell us that the acute angle between the two lines is pi divided by 3. This is also a piece of information we have to go over. When you talk about angles, you usually have 3 types, or at least in this context. You have the acute angle, you have the right angle, and you have the obtuse angle. The acute angle is any angle that is less than 90 degrees. The right angle is any angle that is exactly equal to 90 degrees, and the obtuse angle, you guessed it, is anything greater than 90 degrees. So if we're talking about the acute angle, instead of being the one that I'm putting in pink, okay, it would be the one that I'm putting in red. Okay, so that angle in red would be pi divided by 3. Now the other thing that we do have to go over is that you can express degrees, right, or an angle, right? Degrees, yeah, sure. So you can express an angle in 2 different ways. You can put it in degrees, or you can put it in radians. Okay, so this is actually the first thing that I'm really going to go over and hit hard. When we talk about degrees, it's like putting 90 degrees, 180 degrees, stuff like that, okay? When we talk about radians, it's it's like changing units. Okay, it's as if meters was in meters. As if meters was in meters. It's as if degrees were in meters and radians were in, I don't know, like kilometers. Okay, I'm just making it up. But point is, they're expressing the same thing, just that in different units. Okay, so degrees is a way to express angles. Radians is also a way to express angles. Okay, and one of the things that people have trouble understanding is how to understand what pi divided by 3 is as an angle. So if your angle equals, in this case, pi over 3 radians. How do you know it? How do you know it's radians? It's radians because you have a pi inside of it, quite literally. Now, Unfortunately for you, especially since you're HL and you're watching this video, you do have to memorize and understand the unit circle. The unit circle helps you like sort of transform all these angles and radians and stuff into a more accessible sort of like piece of information. See? So once you memorize the unit circle and you look for pi over 3 on it, you should find it right there on the 60 degrees over here. And so let me just draw the unit circle over here because it will be relevant in just a moment. The unit circle goes like this, goes like that. So this will be x, this will be y. And my pi over 3, right, is actually right there. Boom. So right here, you have the famous pi over 3, okay? Right, that is a little bit of a small drawing, but point is, this is for pi over 3 radians, okay? And you also know that it lies on the point. So right there, you have the point 1/2, comma, whoops, 1/2, comma, square root 3 divided by 2. Square root 3 divided by 2, correct? Yes, square root 3 divided by 2. Yeah, so we identified where it is in my unit circle. Technically, if you memorize that, you also know that this is the same as 60 degrees, okay? But that is not the most relevant part here. The most relevant part is the point in which it lies on, okay? Now, I'm not going to tell you exactly why, but you will figure out in like probably like 5 more minutes, okay? So it's super relevant to understand where this angle lies on the unit circle in order for you to find, okay, in order for you to find which point it's on, okay? That's like the main idea I want to transmit to you. You will see it in action in a second. So the direction of vector L1 is this guy here, all right? And they also tell you that PA, so basically the direction of P2A, right, is this right there, right? And with all that information, we somehow need to show that 4t equals blah, 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 okay? Now, this honestly has more to do with understanding the formulas that you have and seeing how you can get t from there. Now, before we jump into it, I do want to give you a quick tip that you can use for exercises like these. Whenever you have show that, then that's telling you that this right here is true. This is a fact. 4t does equal square root of 10t squared plus 12t plus 18. Why is this worth mentioning? It's worth mentioning because for part B, you do need part A, but really, for finding the value of t, you can just solve this equation there. So, if you realize that you have the buzzword show that in the question, okay, and you're having a lot of trouble, well, showing that, you can use it as factual information, see? So what I'm saying is that right here, right now, if I wanted to, or if I was low on time and stuff like that, I could completely skip part A. Yes, I do miss out on 4 points, but I have the chance of earning 4 points by finding the value of t by what I have in the pink rectangle. Okay, so whenever you have show that, just keep in mind, dude, you can skip that part and just move on, like literally, okay? So in case you're low on time, in case you're having trouble solving it, etc., know that that is something you can do. Right, so that is more of a test taking skill or strategy I wanted to show you. But for now, coming back to the actual exercise, how the heck can we show that? So, really what you should do for this sort of exercise is that once you identify that you are dealing with vectors, open up your formula booklet and see what you have for vectors. What are your tools? What can you play around with? Let's see. And so this is why what I always talk about in almost all of my videos, you guys. The formula booklet is going to save you. It's literally going to save you. You have to be familiar with it. Now notice, I'm saying you have to be familiar with it. I'm not saying you have to memorize it. It's very different. Point is, once you read the word vector, you should immediately be thinking, I know that there's a couple vector formulas in there. Okay, maybe you don't recall exactly what they are. Maybe you don't remember perfectly how they work, but you do have to know that they're in there. Okay, so the formula booklet is huge once you can identify just sort of vaguely, like, I know I have a formula for that. See, I know that this angle that they're giving me is actually relevant for formulas. Like that's the kind of thing we want to reach, we want to be able to do. So once you do that, well, you scroll all the way down and it's going to be in geometry and trigonometry. So we go to page 7 and bada bim, bada boom, now we're getting somewhere. Up here, there is the impossible trigonometry stuff that we're just not going to go over because why would we? No one likes trigonometry, but we will go over, huh, magnitude of a vector. This seems kind of relevant. Scalar product. This seems kind of relevant. Angle between two vectors. Well, you already have it, but it might seem relevant. Who knows? Vector equation of a straight line, da 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 da. There's a bunch of stuff here. Okay, it does get kind of wild. I guess you can use more than one equation here, but the approach that I will suggest has to do with these three initially. Okay, so these three initially, you might not see it right away how they're useful. So that has to do with understanding how these equations relate with each other. Okay, the first thing that you can sort of establish, okay, is that this one up here, okay, the v with the absolute value. The absolute value is the, like the walls that is in between it, right? So the magnitude of a vector, the absolute value of v, also shows up here and here. So, you can use this. I'm going to put names to them, right? So equation number 1, equation number 2, and equation number 3. Okay, so you can use equation number 1 to fill in better equation number 3, right? Now, for equation number 3, you also have v times w. And so, look at that. Isn't this just fine and dandy? You have vw right there as well. So you can also use equation number 2, right, to plug all of this stuff in, basically, right there. And now you might be thinking, okay, yes, that's how the formulas relate to each other, but how can you see that that's what you're supposed to do? And here is where the angle turns out to be a big hint. So the IB, this is the thing, the IB pretty much never gives you something that you won't use. Okay, even t being greater than 0 can be relevant here. Okay, so because they gave us an angle, you should have identified, in the formula booklet, I know there's a bunch of formulas, and one of them has the angle. So if here's my angle, well, I probably have to use it. So if you try to use it, well, what do you need to fill in? You have to fill in what's in pink, and for that you need to use the first equation, and you have to fill in what's on the left, and for that you can use the second equation. So that is our game plan. That is what we're going to do bit by bit. So let's start with what's in pink. So what's in pink is the magnitude of a vector. So let's get the magnitude of both of our vectors. The magnitude of L1, right? So I'm just going to put magnitude L1, okay? Magnitude L1, following the formula booklet, basically says you want to square root, your first value from top to bottom. See? Then you want to add it to this. Oh, yes, sorry, I'm explaining myself not the best. So you want to square root, okay, the square of your first value plus the square of your second value plus the square of your third value. Okay, that is what you're going to be doing. So how does that look in action? We will have, well, the square root of my first value, so this 1, right, squared, plus this 1 squared, plus this last one squared. So L1, or magnitude of L1, I should say, ends up being simply square root of 2, because 1 times 1 gives 1, plus 1 times 1 gives 1, because 1 plus 1, 2, right? So the magnitude of L1 is just going to be 2. Now, the magnitude of PA, okay, so the magnitude, it's really just the magnitude of L2, see? For me, it's a little bit more intuitive if I leave it as magnitude of L2, okay? So, whatever, to each their own. So magnitude of L2 is going to be the same idea. So it's going to be the square root of your first term, so the 2t squared, plus the second term, which is a 0, squared, plus the last term, which is 3 plus t squared. So the magnitude of this second term is going to be, this first term is going to end up as, well, let's see, it's going to be 42 squared plus 0 plus 3 plus t times 3 plus t, right? So 3 plus t, you're going to end up with plus 9 plus 3t plus 3t plus t squared. See? So, in other words, you end up with, so 5t squared plus 6t plus 9. So 5t squared plus 6t plus 9. So here with what I'm putting in, let's say blue, is the magnitude of L2 and the magnitude of L1. So now I'm one step closer to being able to use this third formula. See? Now for the third formula, I also mentioned you do need stuff from the second one. Okay, you do need that whole stuff in order to plug it in right here. See? So what the heck even is that? Well, let's take a moment and observe. So the v times the w, what it's doing, right, is that you're basically multiplying this guy times this guy. See, that's what's happening there. Plus this guy times this guy, which is what's happening there, plus this guy times this guy, which is what's happening there. Okay, so really you're just multiplying all of them like in a row, or so to say. So, basically just L1 like really bolded, right? So L1 really bolded times L2 really bolded has to equal 1 times 2t plus 1 times 0 plus 0 times 3 plus t. So there's a parentheses right there. Well, this is 1 times 0, so it's 0. This is 0 times something, so it's 0. Really, you're going to end up with the bolded L1 times the bolded L2. That is a 1. Bolded L1 times bolded L2 is just going to be 1 times 2t, so 2t. And now, ladies and gentlemen, we can finally go ahead and try to plug everything into the third formula, the last one. See? So with the third formula, well, clearly I'm running out of space, so I'll do it. There's a lot of space up here. Nice. So this last formula is the L1 bolded times the L2 bolded equals the absolute value of L1 times the absolute value of L2, ¿cierto? Times cosine of theta. And what's cosine of theta? The angle between V and W, which is actually what they give us right here. The acute angle between the two lines is pi divided by 3. So really, well, this is the equation, right? Now let's go ahead and plug in. So the bolded ones, we figured out that it was just 2t, right? So for the bolded ones, we can put 2t equals the magnitude of L1, which we found was square root 2, times the magnitude of L2, which we found was that whole thing. So square root of 5t squared plus 6t plus 9, okay? Times cosine theta. Now we're talking about cosine, and this is in radians, correct? Cosine of p divided by 3, see? Now we're almost ready to just sort of plug and chug and see what happens. What's annoying us the most right now is cosine divided by 3. This term right here is hella annoying, and to get around it, you need to be filling with the unit circle. So this is why I presented the unit circle earlier. It's because once you memorize, because you are an HL, so this is one of the few things you do have to memorize or find a way to remember, or etc. Once you realize that the angle pi divided by 3 in radians, or 60 degrees, has the points 1/2 and square root 3 divided by 2, then that immediately allows you to put this cosine value here as 1/2. And suddenly, that makes it so much more friendlier in order to face this exercise here. Because now, instead of having a cosine pi divided by 3 and a bunch of weird stuff, you just have a 1 divided by 2 multiplying everything. Now, how the heck did I just do that, right? I mean, that's the whole point. Let's learn what's happening. So, we usually talk about SOHCAHTOA, right? And SOHCAHTOA, ladies and gentlemen, is a way to be more familiar with sine, right? With cosine and with tangent. And so is for opposite over hypotenuse. Ka is for adjacent over hypotenuse. And toa is for opposite over adjacent. Now, if we're talking about the unit circle and we're talking about some line that goes like this at an angle of pi divided by 3, right, or the same as 60 degrees, see? And you know that this last point, okay, is 1/2 comma square root 3 divided by 2. Well, notice we are talking about the unit circle. Unit circle. Unit. One unit. And so, this point here is 0, comma 1. This point here is 1, comma 0. This point here is 0, comma negative 1. Sorry, I almost trolled. And this point there is negative 1, comma 0. Okay? Why is this relevant? Well, if you have those four sort of corners in your XY graph for the unit circle, well, that's basically telling you that the radius, and I know this is not drawn on scale, but the radius has to equal 1. And so if the radius equals 1, that means that you also have a radius of 1 right there. Actually, all along your unit circle, connecting to any one of these points, you have a bunch of radiuses equal to 1. And this is very important to understand because that means that this triangle that I'm putting now, well, what do you know about it? So that triangle right there, okay, because this is pi divided by 3, okay, and you know that all of the radiuses are equal to 1, and you know that this point, see, is 1/2 comma square root 3 divided by 2, well, the 1/2, right, is your x value, see, and the y is square root 3 divided by 2. And so you know that the dimensions of this triangle have a height of square root 3 divided by 2 and the base or whatever of 1/2. So cosine was adjacent over hypotenuse. And so all along your unit circle, all the hypotenuse are equal to 1 because your radius equals 1. And what is the adjacent in this case? Well, the adjacent, right, of this angle is the one right next to it is simply 1/2. Okay, so the hypotenuse is always the long side. It's always the one opposite of the 90 degrees. It's always the radius. And so now you can actually apply that because you have cosine of pi divided by 3, you remember the dimensions of this triangle by memorizing this coordinate, right? And through there, you can pretty much establish that, okay, so cosine of pi divided by 3 is quite simply the adjacent 1/2 divided by the hypotenuse, which is 1. So that's just going to give you 1/2. So that is why I ended up plugging in, okay, by doing adjacent over hypotenuse, that cosine pi divided by 3 is simply going to be 1/2. The other way you can think about it is that, okay, so because the hypotenuse equals 1 in this case, the adjacent has to be the x value. And so what's the x value of that coordinate? 1/2. The same thing works. If we were talking about opposite, yeah, then it would have been the y value, okay? Anyways, enough blah blah. That was just a quick but super essential explanation of how cosine pi divided by 3 ended up being 1/2. So it fully has to do with being familiar with the unit circle and understanding all the triangles that come out of it. Remember, the radius equals 1. That will make your life so much easier. So remember, sine, cosine, tangent, so ka, toa. It's going to save you. See? Anyways, back to reality. Here we can now start solving for t. And so yes, this looks nasty. Yes, it looks hard to solve, but notice you only have one variable, which is t. And you're actually pretty close to showing that this is true, right, for part A. And so notice, we have something very similar, but we're not quite there yet. And so the first thing we can sort of try to establish is that, you have a 4t on the left, So we should probably try to do that first and then see what happens on the right. See? So if we go ahead and do that, we would have to multiply 2 to both sides. This goes away with this. You do end up with 4t equals square root 2 times square root of 5t squared plus 6t plus 9. Now, how do we go from there to what we have over here? Well, it's a fairly, I mean, not simple, but it's just how square roots behave. See? So in this context, because you have square root 2 times this whole other thing, and the square roots are multiplying, this is very important because the square roots are multiplying, this is the same as rewriting it as quite simply the square root of 2 times the whole other thing. Okay, you can sort of like merge the two square roots together, but do it appropriately so that the 2 multiplies everything. Okay, that means that 4t has to equal square root of 2 times the 5t, so 10t squared, whoops, 10t squared, plus 2 times the 60, so 12t, plus 2 times the 9, which is 18. And now, ladies and gentlemen, we have something awfully similar, if not the same, to part A. 4t equals square root of blah, blah, blah. 4t equals square root of blah, blah, blah. Checks out to me. So that is how you solve part A, and I think the hardest part really has to do with understanding how the formulas work and how to get rid of the cosine pi divided by 3. Right, so I hope you learned a thing or two. That is for part A. For part B, all you really need to I'm getting a lot of voice cracks today. It's caught my attention lately. I'm not sure why. Oh well, who knows? Okay, now for part B, you need to find the value of t. Okay, so for finding the value of t, well, this equation, although it looks very, very nasty, there's one thing going good for us. The only variable you have going around is the variable t. And so because the only variable you have going around is the variable t, all you need to do from here is get t alone. Now, the most annoying thing to deal with right now, at least, okay, is the fact that you have a square root in there. And so how do you get rid of a square root? Well, in order to solve the square root, the best thing I can suggest is squaring the square root. Now, the reason you would do this is because much how like multiplying is the opposite of dividing, well, the opposite of square root is squaring whatever you have, okay? So 4t equals this whole thing. What you can do, just give me a moment because I do need to make a little bit of space. So what you can do from here in order to get rid of the square root, because it is the most annoying thing, is just literally square both sides. Okay, instead of like dividing by 2 or whatever, you can also square both sides. This is completely legal. So 4 squared gives you 16 times t squared equals, this goes away with this. Look at that, how beautiful, see? So from here, well, you want to get everything to one side. So I'm just going to go ahead and do minus 10t squared, right? And really, I'm going to minus everything else as well. So minus 12t minus 18. So after you do all those steps, you end up with 6t squared minus 12t minus 18 equals 0. So all I really did was throw everything over to the left. Now from here, you do want to solve for t, correct? Now, solving for t from here, you should be establishing like a bunch of different rules in your head because you should be recognizing this by now. You are dealing with a quadratic. Okay, and when you're facing a quadratic, there are a bunch of tools that could come to mind. Actually, even in your formula booklet, in the part of quadratics for functions, okay, you do have this right here. So solutions of a quadratic equation, which is literally what we're doing right now. The formula you can follow is this guy right there. Okay, so if you follow this guy, you will be solving this much more easily. See, now one approach you can do, right? I mean, following this equation here is just immediately establishing like, ah, yeah, well, so A has to equal 6, B has to equal negative 12, and C has to equal negative 18. And from there, you can plug into the formula that they ask you to use, negative B plus or minus square root B squared minus 4AC divided by 2A. This will help you solve for t, okay? But we're in HL, okay? We know a thing or two to make our lives easier. From here, you could have established or noticed that on the one hand, all of these are even, so you can divide them all by 2. But you can notice even faster, you can divide all of them by 6. So if you divide all of them by 6 on both sides to make it legal, on the right side you have 0 divided by 6, nothing really changes. On the left side you end up with t squared minus 2t minus 3 equals 0. And so now it's suddenly a lot easier to like solve, and you can again establish that a equals 1 because you have a 1 times t squared, correct? B equals -2 and c equals -3. And so from here you can now apply the quadratic formula, and it's going to be much faster or easier to solve, and you can also factor from here. Okay, so let me just I got time, I'm going to show both. You can skip ahead if you want, but using the quadratic formula it would look like this. So x equals -b, so it's -2 plus or minus square root of -b squared minus 4 times a, which is 1, times c, which is -3, divided by 2, parentheses 1, right? So solving all of this piece by piece, well, the negative times negative is positive 2 plus or minus square root of 4, and this is negative times negative, so it ends up being plus 12 divided by 2. So from here, x equals 2 plus or minus square root 16 divided by 2. Square root 16 is just going to be 4. So the two paths, it's literally two paths. The two paths you gotta take is the path of positive or the path, whoops, of negative. Your mentality is a decision every day. So x equals 2 plus 4 divided by 2, or x equals 2 minus 4 divided by 2. So up here you end up with 6 divided by 2, or 3, so x equals 3. On the bottom, okay, you end up with x equals -2 divided by 2, so x equals -1. So basically what you're establishing is that t, right, because I know we plugged in x here, but in this context, really what you're saying is that t equals 3 or t equals -1. So t equals 3 or t equals -1. Now, just going to check here quick. Yes, t equals 3. Beautiful. Um, which of these is it? Because this is for or, right? Like it's one or the other. So which one should it be given this context? Remember how I said that anything that AB gives you is super relevant? They did tell us 4,397 years ago that t is greater than 0. And so in this situation right now, you would choose t equals 3 instead of t equals -1. All right? So that is solving with the quadratic formula. See, if you want to solve it by factoring, you can do that too. I'm just showing all the tools that you can establish here. Now I know that I'm a little bit of a boomer, so I do factor in a different way. But you millennials or whoever's watching, right, maybe the Zoomers, who knows, I have no idea, have a quicker way of doing this. So the way that I do for factoring is that I do this times this. Okay, so the 1 times the -3. So I have to think of the factors of 3. Really, I only have 1 and 3, right? And now I need to establish, okay, in which way, because they're the only factors, ¿cierto? Can I multiply them together to give me -3, okay? Multiply them together to give me -3, and add them in order to get -2, see? And so clearly you end up establishing that you need to multiply by -3 and +1, see? Because that means that you can do t squared. I mean, really, just skipping a little bit, you end up with x, sorry, you end up with t plus 1 times t minus 3 equals 0. And from here, because you have two parentheses equaling 0, that means that either this one is 0 or either this one is 0. See, because it is two numbers multiplying each other giving 0, one of them has to be 0. So t minus 3 equals 0 or t plus 1 equals 0. So from here, t equals 3 or t equals -1. And once again, because t has to be greater than 0, we pick that t has to equal 3. See? So a little bit of a longer explanation on what to do with the quadratic part. If you don't realize these tips and tricks and you solve it from here like that, it's gonna work. Okay, don't worry. If you follow the procedure, it will work. Trust me. Okay, I think even the mark scheme does it like that. See, the mark scheme uses the big value numbers, and you're still gonna end up with the same answer. Okay, so keep it in mind. This is just a way to make it a little bit more friendly if you realize you can divide by 6, but you don't have to. Okay, follow the procedure. It might be a little bit longer, but it's still going to work. That is what we're looking for at the end of the day. Procedures that work, formulas that are reliable. So that's the one I shared with you today. And yeah, um, that is for part B. All right, you guys, and now for part C, they tell us with these very important words, hence or otherwise. So basically, using from before, hence or otherwise, find the shortest distance from A to L1. So, because it says hence or otherwise, it is key information that what we found in part A and part B is going to be 100% relevant for part C. So this is a big, big hint that, dude, whatever you used before is essential. It is very, very important. So we did find out earlier that t equals 3. Okay, and we're going to find the shortest distance from point A to L1. And so here we need to apply a little bit of logic. See? So let's think about the shortest distance from point A to L1. And so on the one hand, you have this distance that goes like this, right? But then you might be thinking, if you move the angle just a little bit, you can get there much faster, right? The black line is definitely shorter than like the purple one, right? But now when we start putting the green line, right, that's even shorter, isn't it? And eventually you're going to realize that the shortest distance is actually one that is perpendicular. If you keep moving like this visually, you will realize that the perpendicular one is the shortest distance. And this is a math rule that, for me at least, it's very visually appealing. But if you do want to memorize it or learn it in the more hardcore way, you would say that the shortest distance from a point to a line will be like when it's perpendicular. Will be when it's perpendicular. Okay, so whenever it's perpendicular, that will be the shortest distance. Okay, and so this triangle that I just drew in pink that goes like this, boom, boom, boom. Well, what do you know about it? We did establish like a million years ago that the acute angle between the two lines is pi divided by 3. So that means that right here you have a pi divided by 3. Now, what else do you know about this triangle? Well, on the one hand, the shortest distance, right? The shortest distance, which I'm now putting in, let's say, red. So the shortest distance, which I will call x, is this x right here. So we need to find that distance, okay? So we need to find that x for the answer in part C. Now, they did tell us that hence or otherwise, we need to find the answer, and so we need to use t equals 3. Now, t equals 3, where does that even go into our equations, right? T shows up there and there. So, okay. So for now, let's just go ahead and plug in. So if you plug in t equals 3 here, you're going to end up with 2 times 3, 0, and 3 plus 3. So you're actually going to end up with PA, right, is going to be 606. Now, why is this useful? Okay, well, PA, and because it has this little line, correct? So because it has the little line, it's basically like the direction vector of PA. It's like some weird sort of like concept going around. It's like the direction vector. See, so it's basically like if you put a vector, then its direction vector, it's 606 like that. Now that isn't exactly distance yet. And so how the heck do you find the distance of a distance vector? I mean, like, what's going on there, right? And so the next key sort of concept that I need to share with you is that the magnitude of a vector equals its distance. The magnitude of a vector will give you its distance. And that right there is huge. So basically, if you find the magnitude of this guy here, you're going to be finding the distance that goes right over there, which is along the hypotenuse. And so you can start really filling in the dimensions of the pink triangle and solve this exercise more thoroughly. So, of course, we need to go to the trusty rusty formula booklet because it will save your life. So, might as well learn it, might as well know what's in it. For this part, we need to go to topic 3, geometry and trigonometry, HL only because we are now part of the Cool Kid Club. And boom, here is magnitude of a vector. So this is like the thought process you have to go for. See? You drew the pink triangle. You realized you needed a couple more dimensions in order to figure out what x is. And you said, we just had that t equals 3. So you plug it in where you can, and you find that the direction vector of PA gives you 6, 0, 6. Now that's not a distance, so it doesn't help your pink triangle yet, but you can figure out the distance because this guy online told you that the magnitude of a vector equals its distance. And so you remember the key word, magnitude. You know that's in your formula booklet. You go and open it. You go ahead and find it. Here it is. So let's go ahead and plug that in. Basically, the magnitude of a vector, right? For magnitude, we put in an absolute value. So magnitude of vector is going to be the square root of the first one. That's why it's v1, right? The first one squared plus the second one squared plus the third one squared. Which one is the first, second, third? Well, it follows this order here. So from top to bottom, that's the first, that's the second, and that's the third. And so following that sort of logic, the magnitude of PA, right, which is basically just going to be this distance, correct, is going to be square root of the first one, which is 6, so 6 squared, plus the second one squared, which is 0, plus the third one, which is 6 squared. Okay? So if anyone's still a little bit lost, this is your V1, this is your V2, this is your V3. Okay? So we go ahead and plug in. What you end up with is that the magnitude of this guy is going to be, well, 36 plus 36, so square root of 72. And so this distance right here that we just discovered is actually square root of 72. And so now using this triangle, suddenly it's a lot more friendly what you have to do. So now it comes down to trigonometry. Why do we use trigonometry? Because you are dealing with trigonometry triangles. So because you have a 90 degrees here, it's very useful to consider the tools that trigonometry brings. So trigonometry, the main thing we can do from here, you guys, is what we call the SOHCAHTOA. See? So you have sine, cosine, and tangent. And so let's remember that each of these can be remembered as SOHCAHTOA. Now, why do we remember it as SOHCAHTOA? Because SO is opposite over hypotenuse, while ka is adjacent over hypotenuse, while toa is opposite over adjacent. So in this case, oh, and this is all in respects to your angle. So the angle that you have is this guy right here. And so you have the hypotenuse, all right? So we will be using so or ka for sure. So we can immediately discard toa because, well, we have to use the hypotenuse, right? And next we say, okay, we need to find x, right? Now x, is it adjacent or opposite? It is opposite to your angle, see? So because it is opposite to our angle, we will be using sine or so, see? So if you go ahead and plug in a sine, in this case, you will be doing sine of your angle. So sine pi divided by 3 equals opposite over hypotenuse. So my opposite is going to be x. My hypotenuse is going to be square root of 72, right? And now from here, it gets even juicier because we did mention a while ago that the unit circle, okay, can help you find what pi divided by 3 is as an angle. See, so this is in radians, okay? So that means that if I go ahead and open up the unit circle, which is actually something that you need to memorize because you are an HL and you do have to memorize this kind of stuff or learn it in your own way, you can see that the 30 degrees, or sorry, the pi divided by 3 is right here on 60 degrees, right? So let me just go ahead and draw that real quick because it is very relevant. So in my unit circle, right, you have here the point 1 comma 0, you have here the point 0 comma 1, you have here the point negative 1 comma 0, and you have here the point 0 comma negative 1. So we just established that pi divided by 3 as an angle is right here. So there we have pi divided by 3. And what point is it at? It's at the point 1 half. So this right here is 1 half, comma, square root 3 divided by 2. Now we need to understand the following. So this dimensions here, right, this point, the 1 half comma 3 divided by 2, is basically telling you that, okay, this is my x. So that means that over here, you have 1 half. And for your y, over here, you have square root 3 divided by 2. That's what it's telling you. So at sine pi 3 divided by, sorry, at sine of pi divided by 3 in radians, right? So sine of pi divided by 3, you have those dimensions there. Now, sine, as we mentioned, is for so, and so is opposite over hypotenuse. But ladies and gentlemen, in my unit circle, right, in my unit circle, all of my hypotenuses are equal to 1. Because the unit circle, notice, it has a bunch of 1 comma 0 here. 0 comma 1, negative 1 comma 0, 0 comma negative 1. So that means that all these different radiuses are actually just 1. See? And that includes this one here. Basically, what I'm trying to tell you is that if you have sine of pi divided by 3, and you memorize or remember that these are your x and y values at that point, okay, you can apply so. And the opposite in respects to this angle, you will see that it's this guy here. Okay, so the opposite of your angle in SOHCAHTOA, and with SO in this case, is the square root 3 divided by 2. The other way you can sort of like memorize it is that if you're talking about sine, then this will be giving you the y value. Okay, so the y value at that point is this guy here. So in other words, the so in this case will be the opposite, so square root 3 divided by 2, divided by the hypotenuse, which is just 1. So this equals square root 3 divided by 2 divided by 1, which is just going to give you square root 3 divided by 2. So all of that was just to leave clear that sine pi divided by 3 here on the left is going to give you square root 3 divided by 2 because it's the y value in your unit circle for sine pi divided by 3. Okay? That is the sort of concept jump that I was trying to make. So square root 3 divided by 2 equals x divided by square root 72. Now you want to get x alone because you want to find the shortest distance from A to L1, which we did call x. So from here, what you can do, because you have two fractions on both sides, you can cross multiply. I mean, really, you just need to get x alone, and the most common way is that you do this times this and this times this. So 2 times x equals square root 3 times square root 72. Now, from here, two interesting things happen. Because the square roots are multiplying each other, what this actually ends up being is they sort of like meld. So it's 3 times 72 inside. Okay, so 2x equals whatever that is times 3. So it should be 140, 210, 216. So square root of 216. That's interesting. So x equals square root of 216 divided by 2. Now we should probably try to simplify this as much as we can. And looking at the mark scheme, let's see how far we have to go. Well, you don't have to go that far actually. You can just leave it like this. So leaving it as square root 216 divided by 2 is good enough. If you want to simplify it more, it seems like you can. For our interests, we will just leave it like that. Okay? So there's my value for x, and that would be for part C. Alright, you guys, and now for part D, okay, they tell us that a plane, right, with this symbol, contains L1 and L2, and we need to find a normal vector to that plane. Now, what the heck is a normal vector? What is going on, etc. So, the word normal in this context is not very normal. It's actually quite confusing to say so myself. So, on the one hand, imagine you have like a sort of quadratic, okay? Imagine you have like a normal sort of quadratic that goes a little bit like this, okay? And let's say that they tell you that there is a tangent, okay, at x equals -1. Sorry, at x equals, yeah, at x equals 1. So at x equals 1, right? Right here they tell you, here there is a tangent, okay? So that means that at that tangent, and this is the main idea of tangents really, okay? At that tangent, the slope is the same as the quadratic. So at x equals 1, you have a line that goes something like that. It touches once and never again because it has the same slope. Okay, so there is my line that wasn't drawn perfectly, but point is, this is a tangent, okay, that has its slope equals the quadratic, okay? The slope equals the quadratic at that point, okay, because the slope of the quadratic does change over time, but at x equals 1, they have literally the same slopes, right? Now, similar to the idea of a tangent, you also have the normal. And so the normal is actually going, how it looks like, let's go over that first. So how it looks like is that at the same point, it's actually going to go like that. Boom. So what the heck is happening here? So here, at the same point, the slope is actually going to be perpendicular to the quadratic, okay? So when it is normal to the curve, you have a slope that is perpendicular. See? So you can actually literally just sort of say that it's like, well, it's pretty much just the inverse reciprocate, right? Point is, when you have something normal to the curve, it looks like this. It will be the perpendicular to the original sort of slope. Okay, the inverse, however you want to think about it, etc. So in this case, a normal vector has a fairly similar idea. It's basically a vector. Okay, if you have a normal vector to the whole plane, then that means that for both L1 and L2, it sort of cuts them like in the same way that it cuts this quadratic here, right? So normal to them, the slope is sort of like the inverse and stuff like that. Now, because we're talking about vectors, the approach is very different, but I did want to share the idea that that is what it means by normal. Okay, so that means it penetrates them in a certain way. Visually would be something a little bit like this. Now, because this is 2D, it's easier to explain, but if we were talking about a vector, we're talking about a 3D plane. That is why it has 3 coordinates there, so it's a little bit more different, okay? But regardless of that, I just want to share the idea of what it means by normal, okay? Now, how do you actually find a normal vector to a whole entire plane? The procedure is awfully specific, and it is actually so specific that there's only one method. So I'm just going to show you in the mark scheme. There's literally like only one way to solve it. It's right here, right? So this is a sort of specific thing that I unfortunately do have to tell you. This is the kind of thing that you just have to know, okay? So the kind of thing that you just have to know is that, well, basically, for finding a normal vector to a plane, you need to find the, let me use the same words, the vector product, okay? The vector product of two direction vectors. So, the vector product of two direction vectors. Now, direction vectors, you guys, is basically taking a line and being able to define the direction that it's taking. Okay, so it's sort of like the slope of these 3D figures. You can think about it that way, okay? And so really, the direction vector can be like from here to here, or it can also be from here to here, or it can also be from here to here, because really, they're all going in the same direction, right? And so why do I establish that? Because the moment that they give you the direction vector of PA, well, PA, they did tell us, right? PA lies on L2. And so the direction vector of PA is the same as the direction vector of L2. Okay, this you can replace it and it's going to be the same thing, right? So the direction vector of PA also gives you the direction vector of L2. It's the same idea. So what the heck is PA in this case? Well, let's recall that we plugged in t equals 3 earlier. That will give you 2 times 3, 0, 3 plus 3. So really the direction vector of PA, which is the same as L2, is 6, 0, 6. Okay? Now, that being said, right, for the normal vector, we did say we need to find the vector product of two direction vectors. So here are my two direction vectors. One is right there, and my other one is right here. So how the heck do you find the vector product of these two guys? Well, that is the next big buzzword that you need to identify. Vector product in your formal booklet is right there. So getting familiar with the formal booklet is absolutely essential. Now, looking at this format over here, well, it's obviously a little bit harder to follow. So actually, I think it might be wiser if we bring the process over here. So my first direction vector, right, the v, which we call L1, equals, so direction vector of L1 is 1, 1, 0. And the direction vector of L2 is this guy here, right? It's going to be 6, 0, 6, right? And now if you go ahead and plug into the formula that is right there for the vector product, following the procedure that they tell us, for example, the one on the top left, you guys, is V2 times W3, which is basically the second one of the first times the third one of the second, okay? So just be very careful in your approach and it's all going to work out. So the first term of your vector product on the top left is going to be V2, so it should be 1, so this guy 1, times the last one of the second, so 1 times 6, minus, okay, V3, which is going to be the last one of the first, times the second one of the second, see? It's going to be so 0, correct? So 0 times 0, actually. Look at that, yeah? And basically, you just keep going from here and you're going to solve it, see? So V3 is going to be 0, so 0 times W1, which is 6, minus V1, which is 1, times the last one of the second, W3, times 6, right? And then this last one over here, you have V1 times W2, so that's going to be 1 times W2 is 0, minus V2, which is 1, times W1, which is 6, see? So you go ahead, you do all that math, you're going to end up with 1 times 6 gives 6, minus 0 is 0, okay? 0 times 6 is 0, minus 1 times 6 is negative 6. And down here you have 1 times 0 is 0, minus 1 times 6, which is just going to be negative 6, see? So basically it's 6 and then negative 6, negative 6. So this is the vector product, okay? This is the vector product. Now I did mention earlier that, for finding the normal vector to a plane, you need to find the vector product of two direction vectors. So really, the vector product ends up being the normal vector. So vector product will end up being your normal vector. So your final answer is actually going to end up being like 6. For over here, the normal vector is going to be 6, negative 6, negative 6. See? Now, there is one observation I have to do here, okay? And that is that for the direction vectors, all you really care about is like the magnitude, see? Because in this case, they did tell us that the direction vector of PA, so from here to here, was 6, 0, 6, right? But if I, for example, found the direction vector of, I don't know, from P to some point that I'm going to make up, like B all the way up there, right? So all the way up there, see? Well, the direction vector of that would probably end up being something like 12, 0, 12. Now, what is the observation that I'm doing here? These direction vectors are the same, technically, because in proportion, they're the same, see? For example, this one, you can divide both of them by 6, you end up with 1, 0, 1. This one, you can divide both of them by 12, you end up with 1, 0, 1 as well. And so basically, the proportion of your direction is what you care about the most. In other words, it doesn't really matter if you take like the slope I know it's not literally the slope, but let's understand that it's the slope. It doesn't matter if you take the slope from here to here, or from here to here, or from here to here. They're all going to be the same slope. And so, to leave like your final answer down here, technically you can divide everything by 6. And you can end up with a nicer normal vector, which is 1, -1, and -1. Notice that the mark scheme does something very, very similar. You end up with 1, -1, -1. But it does tell you that any scalar multiple of this also gives you the point. So don't worry if you didn't notice that, okay? What I'm trying to tell you is that you can leave it like this or you can leave it like that. Both of them work. I just need to share the idea that what you really care about is the proportion of your direction vector, of your normal vector, okay? That's what vectors are really all about. It's about the proportion that they share, okay? If you're talking about magnitude or distance, then that's a different story. But if we're talking about direction vectors and stuff like that, you really only care about the proportion, sorry, that they share. So, ladies and gentlemen, that is how you do part D. All right, you guys, and now for this last one, okay, for part E, we need to do a crazy exercise that is worth 7 points. Now, the math is not that complicated, but the concepts behind it are really, really wild, okay? So better make sure you lock in because we're going to be cooking on this one, all right? So, for this last one, we have that the base of a right cone lies in basically our plane. See, so let's remember that that symbol there is for the plane that we're dealing with, and it is centered at A, so that is, quite useful. It is centered at A such that L1 is tangent to its base. They also inform us that the volume of the cone is that amount of cubic units. And so we need to find the two possible positions of the vertex of the cone. All right, so clearly there's a lot of different buzzwords going around here, and so we really need to try to identify basically what the heck is going on. Okay, so first things first, visually on this diagram, we already identified that triangle there. We know that that small sort of like height, like the x value that I'm putting is square root 216 divided by 2. We did that from earlier, right? And so what's happening now is that at point A, right, it is centered at A, we are drawing the base of a right cone. So let's remember that a cone looks a little bit like this. Boom. Okay? There is your right cone. All right? And so the right cone, actually, let me make it like a little bit of a better drawing. So the right cone looks something like that. Okay? So here is your right cone, right? And so if I'm drawing just the base of the right cone, it's just going to be a circle. And so because the base of the right cone is centered at A and is tangent, okay, with the L1 basically, because it's tangent with L1, that means that your circle for your right cone goes something like this. Okay, let me make it a little more centered, but it will look something a little bit like that. Okay, so basically, there is the base of my cone. See? And right there, it's going to be perfectly tangent. Now, that is extremely useful because since it is perfectly tangent, then this red line right there, you guys, is actually my radius. Because A is the middle of my circle, and because here it is tangent, that means that from A all the way until we hit L1, it has to be the radius of the base of my right cone of my circle. So that is the first big observation that we really need to do. Now, the second thing that we need to establish is that it is asking for us to find the two possible positions of the vertex of the cone. Now, why the heck are there two possible positions? Well, because technically this cone can either go out sort of like, I'll try to draw it, okay? So it can either go out this way, and the height is like this, okay? And basically I want you to find this location here, all right? So that would be one of my vertexes that it can take, or it actually goes out this way. Boom. And that means that my vertex would be over here. Now, the one sort of friendly thing about this exercise, if anything, is that these two heights are the same. And so it's the same height, but the vertex would end up being different. Okay? So keep that in mind. All right? Now, before I jump into like what to do and how to do it and etc., okay? We really need to establish like our way of thinking. Okay? So on the one hand, they did give us, okay, they did give us the volume of the cone. So they tell us that the volume of the cone is this amount. See? And so let's just sort of play around and see what that might give us. Okay? Whatever the IB gives you something, you probably end up using it. So I'm going to go up here and say that volume cone, they tell us that it's 90 pi times square root 3. However, what is the formula for volume of a cone? I mean, if they're giving me the volume of the cone, well, what's the formula for it? Now, you probably don't know it by memory, and surprise, neither do I. You're not supposed to because you have the formula booklet. So open up the formula booklet. Let's go ahead and find volume of a right cone. So here's the volume of a right cone. See? R is going to be the radius, pretty standard. H is going to be the height. So volume of a cone with big V, okay, to show that it's like the formula, okay? So volume of a cone is a third pi r squared times h. So if they give me the volume of the cone right there from the exercise, and I have the formula from the formula booklet, well, you can equal them to each other, see? So technically, I should have that 90 pi times square root 3 equals a third pi r squared times h. Now, I'm not exactly excited about this yet because I do have the two variables r and h. So, do you have either of these? Surprise! Yes, you do. You have it right here from the radius, which we said earlier was square root 216 divided by 2. So, you can go ahead and plug that in and end up with only one variable. So that is just fine and dandy, as some people say. So, 90 pi times square root 3 equals a third pi times my radius, which you said was square root 216 divided by 2, and all of that squared times h. And so now you only have one variable, only h. Okay? I don't know why I put an r initially. But you have only h. See? And so now you can actually, well, work this out. And although it looks terrible and it looks scary and it looks horrifying and there's square roots and squared and pi and doom, you do have only h. So you can actually find like an h equals something. See? I mentioned this because lots of times in my videos or in just in math in general, I think it's very easy to get lost in the sauce. It's very easy to like lose grasp of like, okay, why am I doing what I'm doing? Okay, and so in this case, they gave us the volume of the cone. We applied the formula for volume of the cone, and we said, okay, this is gonna give me something. See, so you plugged it in. You realized you had two variables, r and h. You slowly realized, I have r, so let's plug in r, and now you have only h. So this will give you h, which means that in this diagram you will have this value here, which is actually the same value as this value here. Okay, so that is the h that we're finding right now. And so basically, I can just start from a, apply h, and we're going to see how that works. Okay, so we're going to start from that point, apply h, and that way we find the two vertexes, okay, or vertice or whatever. That it? So how the heck do you get h from here? Well, just get h alone. See, so h is on the right side. Do everything to throw all this stuff over to the left side. See, now let's make it as friendly as possible. So basically, what I would start off with, okay, is that, well, the left side I'm just going to leave it the same, to be honest. On the right side, I end up with 1/3 pi, and I'm going to apply the parentheses. See, I mean the squared on the parentheses. So, because it's squared, you end up with square root 216 times square root 216 divided by 2 times 2. Okay, so that means you end up with 90 pi square root 3, and technically this 3 I can just pass it over immediately, so you multiply by 3 to both sides. That means over here I would end up with 90 times 3, so it's 270. Alright, so that way I got rid of the 3 right there. Pi, parentheses, 216, because square root and square root just gives you what's inside, divided by 4. Okay, times h. From here, because you have pi on both sides, that means you can divide by pi on both sides. Just get rid of it. So on the left, you have 270 square root 3 equals whatever this is. See? Now this, after a long time of thinking and figuring it out, you will discover that it's 54. So 270 square root 3 equals 54h. Divide by 54 to both sides in order to get h alone. H equals 270 divided by 54 is going to give you, let me do some big brain maths, 5. Okay, so you end up with h equals 5 square root 3. Okay, so boom, look at that. You just found that h equals 5 square root 3. Now, what the heck do you do from here? Okay, so as I mentioned, you want to start from this origin and sort of like apply h. Okay, I'm just saying it more intuitively. Start from the origin, which is a actually. Start from the origin, which is a. The letter a is right there, see? Start from the origin, which is a, apply h, and end up, okay, at one of the vertices, see? Now, when you sort of like apply h, okay, you really need to understand that you are moving along some sort of line, some sort of vector that is going this way or this way, see? Now, the big issue here is that do you have a vector that actually does that, all right? And this is where I really need to try to draw some masterful art because explaining this is actually really tough, yeah? So, this is what's happening. Right now, you have an xy plane, okay, that goes like this, okay? I'm doing it like as 3D as possible, see? So you have some xy plane that goes like that, okay? Boom, boom, boom. It goes something like this, okay? And this whole thing, okay, is plane, whatever that symbol is. Okay, so this is plane like big pi, I don't know, whatever, okay? So this is what's happening. In this exercise, we drew, okay, the base of the right cone, okay? And basically, we need to find one of the vertices that goes like that and the other one that goes like this. See? Now, in order to really do that, you need to be able to move along the plane, okay, in a perpendicular way. Because since it is a right cone, and this is another big idea I need to share, see? Because it's a right cone, that means you have 90 degrees here, and the cone going sort of like all around it, see? Now, notice, this basically, okay, maybe now it's going to be a little more clear. This down here, okay, this is your plane. This is a plane that you're trying to like draw or figure out, see? And so this right here on your circle down below is your plane, and you need to find some vector, okay, that will allow you to travel through here and also through there in order to find the other vertex, okay? That's what's happening. And so which vector allows you to do that? The normal vector. Let's remember that I mentioned a million years ago that the normal vector, exactly what it does, is that it gives you a line or a vector that's perpendicular to your plane. And so a line that is perpendicular to your plane actually helps you find that height, all right? That height for your right cone, okay? And that will actually allow you basically to travel through here and allow you to find the two vertices, see? So if I return to this drawing over here, basically your normal vector, so your normal vector, what it's really going to do is that it's going to be perfectly perpendicular to this. So it's going to call like that. Boom. There's your normal vector. And all you have to do now is travel h amount of units, basically, in order to find one of the vertexes, and h amount of units over here in order to find the other vertex. Okay? So there was a little bit of blah blah for understanding why we're doing what we're doing. Essentially really has to do with understanding the normal vector. See? So it's no surprise that for part D, we did have to find that. Okay? Now, the normal vector we found from part D has these sort of like properties or whatever. See? So the normal vector has that, you know, those coordinates, if you want to think about it that way. Okay? And so essentially what we're establishing now is like, okay, so you gotta basically take your normal vector, okay, in terms of magnitude, because for distance, see, so take the distance of your normal vector and apply it enough times so that you reach h, okay? Now apply it enough times, right? Apply it enough times. So some amount times your normal vector until you reach h, okay? Basically, if I were to like redraw it again, because I think it's very, very important that we understand this part, okay? Basically, you have some normal vector that I'm now going to put, say, like in pink, that goes like this, okay? And all you know is that you need to multiply this some amount of times, maybe 2 times, maybe 3 times, maybe 4 times, until you fulfill and reach the distance of h, okay? And so that is why you gotta take your normal vector, multiply by some amount, which we will discover now, and get h, okay? So if you go ahead and start filling in what I put on the left just now, you're gonna discover a couple of things. So on the one hand, okay, well, that's some amount, which I'm putting as u. We still don't know yet, so you can just leave it as u. Magnitude of n, when we talk about magnitude, we're really talking about distance, and we do come back to, where is this fancy formula? Ta-ta-ta. Wow, I am blind as a bat today. There it is, magnitude of a vector. See, so you go ahead and plug in this formula here. See, now we did use it for like part B, I think it was, or C, I'm not sure. So I'm not gonna go over it very thoroughly, but basically this first term is the one up top. This second term is the one on the second. This last term is the one on the bottom. See? So for the magnitude of a vector, you're just adding all of them inside of a square root, and they are all squared. So in this case, for a magnitude of n, see, knowing that n is 1, -1, and -1, ¿cierto? From here, nice. That means that magnitude of n is going to be square root of 1 squared plus -1 squared plus -1 squared. And so you're quickly going to realize that really this is just 1 plus 1 plus 1. So magnitude of n equals square root 3. So you can plug in that magnitude of n equals square root 3 right here. And h, we found from earlier, is 5 square root 3. And now it's really no surprise that u, okay, I mean really the last step you want to go hardcore is that you divide by square root 3, divide by square root 3, boom, 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 boom. U has to equal 5. Now, here's a very important thing that we need to establish. So because u equals 5, well, the vertex can either go up, like this diagram that I put here, or the vertex can be down here, right? And so u, ladies and gentlemen, basically how many times you apply the normal vector, can either go up or it can go down. It can go left or it can go right. So u has to be plus or minus 5. All right, awesome. So now that we mentioned this, for finding the two different positions of the vertex, okay? Well, first, what the heck is point A? See? So you are starting at point A. It is the origin of your right cone. See? Now, point A, something we didn't establish earlier, is that it's actually 2t, 8, and 3. And from part B, you found that t equals 3. So point A is actually 2 times 3, 8 comma 3. So point A is 6, 8, and 3. Dale? Now, so you're starting from 6, 8 comma 3. You're applying, we discovered, the normal vector 5 times either positively or negatively. So let's literally like put that in writing. See? Enough blah blah. Let's get into it. So vertex 1 basically is going to be your point A, which is 6, 8, and 3, plus 5 times, okay, n, or you're going to have 6, 8, 3, minus 5 times n. See? N as a vector, ¿cierto? So the vertex 2 is this one down here. and the vertex 1 is that one up there. See? So let's go ahead and do vertex 1 for now. So n, as we've already established a couple of times, I'm just erasing it to make a little bit of space. So n is 1, negative 1, negative 1. See? So vertex 1 is really just going to be 6, 8, 3 plus 5 times 1, negative 1, negative 1. See? Which really, I mean, if we leave it like in some fancy sort of vertex form, you can do it like this, okay? Actually, I think it's more intuitive, sorry, if I leave it as coordinates, okay? So 683 plus 5 times 1, negative 1, negative 1, see? So in this case, you end up with 683 plus 5 times 1 gives you 5, 5 times negative 1 gives negative 5, 5 times the negative 1 gives negative 5. So from here, okay, really, if you want to do like the more rigorous sort of step, okay, you would end up with 6 plus 5, which is basically this one plus this one, okay, and then 8 minus 5, which is this one with this one, okay. Let me just finish color coding, why not? And then the last one would be this one minus this one, okay, which is going to be 3 minus 5. And so this last point ends up being 11, 3, and negative 2. So this will be your vertex 1, okay? So now probably the procedure makes a lot more sense. I think the hardest thing that I needed to explain was why the heck we used the normal vector in the first place. And really, visually, it's a hell of a challenge, see? So find your own way to understand it, whatever floats your boat. That it? So that is for vertex 1. And for vertex 2, you follow an extremely similar procedure, just that instead of plus, you will be doing minus, see? So really, I can just do it from here. So instead of plus, we're now going to change it to minus. So that means that over here, I end up with minus 5 plus 5, okay? And I mean positive 5, see? So that means that when I combine everything, okay, I mean really this point ends up like this. Okay, this is like the big change that's happening. Actually, sorry. Let me go again. See? I think it got a little bit more confusing than it had to be. So from here, we are now going to do minus 5n. See? So we do minus 5n. So minus 5 times 1, negative 1, and negative 1. See? Now really, it's going to be like you're adding both of these points, but now you're multiplying by a negative 5. See? That is a small detail that I should have mentioned earlier. You're still adding like the coordinates, it's just that now you're adding like in the other direction. See? So that is why you have a negative 5 here. So really you end up with 6, 8, 3 plus, okay, negative 5 because of this times this, plus 5 because of this times this, so just positive, right? And another positive 5. Okay, that makes a little bit more sense. See? And so from here, if you let these two interact just like before, you're going to end up with this 6 minus 5, so it gives you 1. This 8 plus 5, which is going to give you 13. And then finally, last but not least, you end up with this 3 plus 5, which gives you 8. And so the second vertex, vertex 2, okay, is going to be 1, 13, and 8. So really your last final answer is that this is the first vertex and this is the second vertex. And just for checking in the mark scheme, we do see over here that one of the vertexes is 1, 3, negative 2. Makes sense, that is this one right here. And 1, 13, 8, 1, 13, 8. It's right there. See? So you guys, this last part is definitely hard. I think that the biggest challenge is really understanding how to visualize it. And the biggest sort of thing you can take from this, like something that you might apply on like another exercise and stuff like that, is why you had to use the normal vector. Okay, the IB loves to put like shapes and stuff like that in between all these vectors, and the normal vector, what it's essential for, which has to do with the word normal in this context, is that it's excellent for being a perpendicular line. Okay, so perpendicular lines can be extremely important for getting stuff like heights. Okay, so that is the biggest thing I can sort of let you guys know or write down for part E. Be very aware of how the normal vector really saves you in this exercise. All right. So you guys, party was pretty wild, but party was worth 7 points. So give yourself a pat on the back because that was very intense, even for me. And yeah, that is number 12. And that is actually the whole paper. So I hope it helped, and I'll see you around.